On behalf of the Aizer Bayrampur fraternity, I now request the students to present bouquets to the esteemed guests. Welcome everyone to Aizer Bayrampur. My name is Tushar Mauli Chakraborty and I welcome you all to this 2-day seminar program on science in the community, advancing science popularization in Odisha. This seminar is a celebration of science where we will get to hear from eminent scientists across all of India about the joys of doing science and how science has helped society evolve towards betterment in countless ways.
राज्य तथा देशर कोण अनुकोणर उपस्थित आभारग्रद बनितांको आइजर ब्रह्मपुर पक्षरु मु बंदिता आपण समस्तंको एक सुंदर सकाळर शुभेच्छा जणाउछि। आपण मानंको ए 2 दिनर सम्मेलन जहार शीर्षक गोष्ठी मध्य विज्ञान लोकप्रियता एवं अग्रगति रे स्वागत जणाउछि। विज्ञान उत्सव आपण मैंने देशर एवं लंब और प्रस्तर पहुंची विशिष्ट तथा विख्यात वक्ता मान शुणिबार सुजोग पाइबा सह विज्ञान को जीवित कर आनंद एवं किभली भाव यह समाजर उन्नति दिगरे पथ प्रदर्शक रूपे कार्यरत ताहा जानिबाकु पाइबे।
To give the welcome address, I now invite Dr. Nihar K. Patra. Dr. Patra currently serves as a librarian of Aizer Bayrampur and he is also the organizing secretary of this event. Throughout his illustrious career spanning more than 25 years in many institutes across India, he has played a pivotal role in establishing numerous modern libraries and has been actively involved in scientific outreach.
वर्तमान मो डॉक्टर निहारंजन पात्र को प्रारंभिक भाषण निमंते मंच को आसवाक आग्रह करुअछि। डॉक्टर पात्र अधुना आइजर ब्रह्मपुर लाइब्रेरियन तथा सांगठनिक सचिव रूपे कार्यरत। गत 25 वर्षर चमत्कारिक कार्यकाल रे देशर विभिन्न अनुष्ठान गुड़िकरे आधुनिक तथा विश्वस्तरीय लाइब्रेरी और पाठागार प्रतिष्ठा एवं विज्ञान प्रसारण रे प्रमुख भूमिका ग्रहण करि।
Thank you. सर्वगायन प्रसन्नाय अयम सभा समागतः विज्ञानम समाजे योजयतु ओडिशायां प्रचारयाम means this assembly has gathered to disseminate knowledge. Let us promote science in society and we are popularizing it in Odisha. With this motto, I extend a warm welcome to these distinguished guests, esteemed speakers, teachers and students, fellow members of the organizing committee. Namaskar and good morning. It is with great pleasure and profound sense of gratitude that as an organizing secretary, I stand before you today on behalf of the organizing committee of the seminar, Science in the Community, Advancing Science Popularizations in Odisha, organized under the Science Outreach Program of Aizer Bayrampur. First and foremost, let me express my heartfelt appreciation of your presence at this remarkable event. Your participation here signifies not only your dedication to the cause of science education, but also your commitment to foster a culture of scientific curiosity, and knowledge disseminations within our community. The primary goal of this seminar is to bridge the gap between the scientific community and society, ensuring that scientific knowledge is not isolated but accessible, relatable, applicable to everyday life. We believe that by making science engaging and accessible, we can inspire the next generation of scientists, spark curiosity in young minds, and fuel the desire to pursue career in scientific field. Our endeavors encompasses institutions primarily situated in the southern Odisha as well as from northern region of Andhra Pradesh. By inviting 300 students, teachers from 22 schools and colleges, we have created a diverse and dynamic platform for learning and exchange. I would like to emphasize our commitment to gender equality. We have extended invitation to both female and male participants, recognizing that talent knows and no gender boundaries. I like to extend my warm gratitude to our dignitaries of the dais, Professor Ashok Kumar Ganguly, Director IJR Berhampur, and the chairperson of the seminars, who has always shown keen interest in organizing such science outreach activities for the underprivileged citizen science, and has already conducted science outreach in more than 300 schools, colleges in several states in the country. Professor Arvind, Vice Chancellor of Punjab University, Patiala, the guest of honor, and our chief guest, Professor Arun Grover, Professor Emeritus at Punjab Engineering College, Chandigarh, former Vice Chancellor of Punjab University and former Professor of TIA for gracing these events with their presence. The seminar features a lineup of esteemed speakers such as Professor Arvind, Professor B. Ram Gopal Rao, Vice Chancellor, BITS Pilani, Professor Rajesh Prasad, IIT Delhi, Professor Uday Mitra, IISc Bangalore, Professor Deepa Khuslani, TIA from Mumbai, Professor P.S. Anil Kumar, IISc Bangalore, Professor Satyavrata Patnaik, JNU New Delhi, Professor Amlan Kumar Das, Modi University of Science Technology, Sikar, Dr. Jivan Jyoti Panda, INST Mohali, Dr. Swamik Siddhant, IIT Delhi, Ms. Sigdha Das, Vidya Bhavan Education Resource Center, Udaipur, and our Honorable Director, Professor Ashok Ganguly. These speakers will share their expertise and insights across various sessions, spanning a wide range of scientific topics. I am certain that their presentations will be both enlightening and inspirational. I would like to thank the organizing committee member, Dr. Bias Akhandi, Dr. Natasha Sharma, Dr. Rahul Sharma from IJR, Berhampur, and all the volunteers for their tireless efforts in making these events a reality. Your dedication and hard work have been instrumental in ensuring the success of these seminars. I wish all the participants fruitful interactions, meaningful insights, and above all a passion for science. Let us together explore the wonders of scientific discovery, ignite this curiosity, and chart a path towards brighter, more significantly informed futures. Thank you for being a part of this transformative knowledge. I look forward a 2 days of engaging discussions and the collective advancement of science populations. Welcome once again to the Science in the Community seminars, and let us embark this inspiring journey together. Thank you. Jai Hind.
Now, to present the inaugural remarks of this joyous event, I now invite the Director of IJR Berhampur, Professor Ashok Kumar Ganguly. Professor Ganguly is a renowned expert in the field of nanotechnology and more specifically designing nanomaterials for energy conversion and superconductivity. He has served as the Deputy Director of IIT Delhi and as the Founding Director of Institute of Nanoscience and Technology in Mohali. Throughout his illustrious career, Professor Ganguly has always taken a keen interest for promoting science in the underprivileged sections of society in several states across India. It is this passion for science popularization that has resulted in numerous outreach activities since his recent assumption of the director position here at IJR Berhampur, ultimately culminating in this grand event.
वर्तमान मो उद्घाटनी वक्तव्य निमंते आइजर ब्रह्मपुर निर्देशक प्रोफेसर अशोक कुमार गांगुली को मंच को आसीबा पई आग्रह करूअछि। प्रोफेसर गांगुली नैनो टेक्नोलोजी एवं एहार डिजाइन क्षेत्र में जड़े सुप्रतिष्ठित विशेषज्ञ। गत समय रे से आईआईटी दिल्ली उपनिर्देशक आईएनएसटी मोहाली प्रतिष्ठाता तथा निर्देशक भावे कार्यरत ग्रहण करियछंती। तांकर प्रेरणादायी कार्यकाल मध्य से समाजर वंचित वर्ग रे विज्ञान प्रसारण तथा अग्रगति निमंते देशर विभिन्न राज्य रे जरूरी इच्छाशक्ति एवं प्रशंसनीय कार्य करियछंती। आइजर ब्रह्मपुर निर्देशक रूपे कार्यभार ग्रहणर मात्र 6 मास अवधि मध्य से विज्ञान प्रचार एवं प्रसार निमंते केवल कार्य नुहे नेतृत्व नहीं एक उदाहरण मध्य सृष्टि करियछंती।
Good morning, everybody. Good morning. It's a great pleasure for me to see all of you, all young people here, for this great occasion for outreach at a large scale. So I really want to do outreach in Odisha in a very grand scale, and this is the first of its kind. We have done some small outreach programs. And to all of you, I must say that the list of speakers that you have, it is very difficult even to get all of them in Delhi, Mumbai, etc. or Bangalore together. So I am very happy and glad that such distinguished people like Professor Arun Grover, Professor Arvind, Professor Uday Maitra, Professor Deepa Khushlani, Professor Amlan Das, Professor Snigdha Das, and several who are not here right now, they are arriving. Some people are on the way from Bhubaneswar. So I must tell you, see, Berhampur to travel, people take, they have traveled nearly 12 hours. Somebody has started 7 o'clock in the morning from Patiala and then come and reached here 1 o'clock in the night. Who normally will not be going other than Delhi, Bombay, Bangalore, maybe Calcutta. These are the places they go mostly, Pune, Hyderabad. Very rarely they would come to sometimes to Bhubaneswar, and very rarely they will come to Berhampur, right? I think this is one of the first occasions. I'm sure maybe Berhampur University has had some international meetings, etc. Probably there are, but not so many of the same kind of experience, the kind of experience they have. Like Professor Grover was telling me that 50 years back he came to Berhampur University. Imagine 50 years back what this place was, and he has come to Berhampur University to give a talk in 70, right? 75 he said. So 75, many of you, your parents would be just growing up or something like that, right? So I am really, I want Berhampur to become a real educational hub, and lot of great people, including Nobel laureates, I want to bring to Berhampur, which I did when I was in Mohali. We were a very new institute, but with the help and support of many senior people in Punjab and all, one of them is of course Professor Grover, we got highly distinguished people to our new institute in Mohali within the first 6 months of my joining. Here also I finished only 6 months, but I am trying to make Berhampur ISER well known in the world. And with that I have my cooperation of many distinguished faculty that we have. We are outstanding faculty, around 50 faculty we have. You should go our website and see all those who are students. See what are the areas of research people follow. ISER Berhampur is a small part of the huge grand challenges the world faces, and some of the areas our scientists are working. So you should look at the website, people working in biological sciences, physical sciences, mathematical sciences, then chemical sciences, earth sciences, environmental sciences, and maybe very soon we will start computer science, humanities and other areas. So all of you who are growing up, You can come and visit our laboratories. You may join ICER one day, you may join IIT one day, or any other place in any other institution, but you can start coming to know what great research today is done in India. Then only you will know what great research is done in the world. In India, we have the best machines you can get. In IISERs, IITs, the government spends a lot of money to buy machines which you cannot think of. 30 crore machines, okay, that kind, 20 crore, 10 crore. You can't believe that kind of expensive machines that we have to do ultra fine granular research. That means you can do very fine, high quality research in biology, like microscopes, all kinds of microscopes we have. Then you know X-ray machines, NMR machines, if you have heard of what is NMR or X-ray. And maybe soon we will have a lab of optics, you will see lasers going from here, what lasers can do, what telescopes can do. We will have a club for astronomy very soon. I think Vyas is sitting here, he is one of our faculty who works on astrophysics. He is a PhD from RRI, I think, right, or IIA, Indian Astrophysics. So we have faculty from very top institutions. Rahul is sitting, he is from Cornell University. He is working on ultra low temperature STM. If you know, it's a very, very top of the line facility. Very few institutions in the world, in India, have. So IISER Mohali has, Professor Arvind knows, Professor Gautam Sheet is recognized in the world as one of the top guys in UHV STM, where we can see atoms moving, etc., play with atoms, etc. So we are going to build one in Behrampur, in our coastal main campus. And someday, maybe soon, in 3-4 months, we are going to inaugurate our main campus. And we believe Prime Minister is going to come. And after that, we will open to all of you to come and visit our campus. So it's a growing campus. We already have 1,000 students. They study BS, MS. After school, you can give joint entrance examination like IIT JEE. You can come through JEE exam, but you have to give advanced JEE and you have to have a rank below 15,000. Apart from that, you have what is called the ICER admission test, IAT. With that also you can come. This is after class 12. So what do science do? What do scientists do in this world? Because most of you have heard engineering. Everybody wants to become an engineer. Everybody wants to get a job as a computer scientist. But do you really know what scientists do? Suppose this, COVID vaccine had not been made by scientists. How people in the world would live? Imagine thousands of people died in Italy, Spain and all. India had much less actually deaths. We handled it very well. India, is the world's largest exporter of vaccines. Hyderabad alone produces more vaccines than any place in the world. It's the largest producer of vaccines. So like that, you must know what India's capabilities are. And you are a part of that growing up generation. When I grew up, when I was in school in the, say, late 60s and 70s, India was very different. Today, any machine you say, which is available in world's top universities like Harvard, MIT, etc., will be available here in India, in some institute. May not be in all institutes, but some institutes in some central universities, etc., which you can use if you want to work in that. So you must have a dream. At this age, you must have a dream what you want to do, because you have only one life. So if you don't start dreaming today, tomorrow you cannot dream. Your class 10th gone means you will never do class 10th again. Your class 11th gone, you will never do class 11th. So unless you start dreaming today, you will never be able to do something later and catch up. So if you want to be a good scientist, this is for science. But of course, you can do good music or good literature, that is up to you. But you have to start dreaming of what you want to do. So this is our effort to open your eyes to the world, what good science is. That is why we have brought these talented luminaries to Berhampur. That's what I try to do. Instead of bringing students from the village, I go to the village. I have traveled to many villages. The idea is, even if one student of that village changes his life, which happens, he will give back. You know how many people donate to their villages? Those who have done, there are lots of stories you hear. I know of many cases. They have become engineers, they have gone to US, they have become great entrepreneurs, then they have donated things in their whole village they have changed. I know stories in Bihar, in Karnataka, of one person changing the whole village. Built a school, built a college, etc. So all of you can do that. It is, if you do well, one person does very well, he can contribute to the growth of lakhs of people. So for us, even one student from you becomes outstanding after 20 years. This program is successful. So we have 500 people, I don't know how many, 300. 300 plus maybe 50 teachers. If one of you become outstanding after 20 years, our program is a success. That's why government wants outreach to be done very well. We want to connect to the masses. We want to connect to school children, because that is where your building starts. You have to have a dream, because who will study theoretical physics today? What people do? Many of you will know. You will know what engineers do, right? And get a job and get a salary. But many people will not know what a theoretical physicist do. That is, somebody has to tell them at the childhood level, right? And then their eyes open. Then one of them will become a bright, right? So you have heard of Homi Bhabha, you have heard of C.V. Raman. They had a spark. At that time, India had nothing. 70 years back, 80 years. Still they did great things. So today you have so many things. You have so many things. You all have smartphones in your pocket. You have computers, you have laptops. Every student, I think, has a computer or laptop at home, more or less, right? So I must say that you are from a different generation. So if they in 80 years back could do things for which India is proud today, then imagine what you can do 20 years later. Okay? So with those words, I want to thank all of you who have come here. Especially I want to thank all our visitors for coming here and interacting with you. And I want to make a change in Berhampur. I have only 4.5 years left. My 6 months is already over. So I count backtrack. So I joined ISER Berhampur on May 2nd. My 6 months is over. But I want to create an impact in Berhampur, southern Odisha area. We should grow, because Odisha mostly is known in Bhubaneswar, Cuttack, Sambalpur, that part of area. But this part of area, not too many outstanding people are coming. So we have an aim to bring them to southern Odisha and northern Andhra Pradesh. So we'll club with universities like in Vizianagaram, with Vishakhapatnam, and say Berhampur University. Anyway, we have good collaboration with Berhampur University. So with that, we'll bring up a cluster here, and we do regular meetings, and you can look at our laboratories. Some of you can come and do internships with us. We can take student interns from high schools. Many of these things happen in many IITs and ISER. School students go work for 1 month, 2 months in the laboratories. So they get a feeling of what is research in the lab today. And then they go for advanced studies in BSc or MSc and then PhD. Okay, so with all these words, thank you once again. Thank you. I want to thank all our colleagues. We have our 2 deans sitting, Professor Jaydeep Mukherjee, Professor Vishwas Chavan, and our convener, Professor Patra, and his team, Dr. Rahul Sharma, Dr. Shanti sitting behind, Dr. Natasha is sitting right in front, and Dr. Vyas is sitting, and several others whom I can't see here, but they are doing a lot of work behind. And congratulations, and thanks to ITI, because we are using their auditorium, and thanks to the principal, who is not here, I think, Dr. Padi. Right? So thanks to ITI for giving us this auditorium. Thank you.
Thank you, Professor Ganguly, for your inspiring words. I now request the guest of honor of this event, Professor Arvind, to give his remarks. Professor Arvind currently serves as the Honorable Vice Chancellor of Punjab University in Patiala. He is an eminent theoretical physicist whose research in the fascinating realms of quantum physics, with emphasis on quantum optics and quantum information processing, has garnered wide acclaim. Professor Arvind has also served as a faculty in many prestigious institutes like IIT Madras and ISER Mohali.
वर्तमान समय पहुंची कार्यक्रम सम्मानित अतिथि प्रोफेसर अरविंद को आमंत्रण करिबार मु तांको तांकर वक्तव्य निमंते मंच को आसीबा पई आग्रह करूअछि। प्रोफेसर अरविंद वर्तमान पटियाला स्थित पंजाब विश्वविद्यालय कुलपति रूपे कार्यरत। से जणे सुप्रतिष्ठित तात्विक विज्ञानी। तांकर प्रमुख गवेषणा क्वांटम पदार्थ विज्ञान, क्वांटम ज्योतिर्विज्ञान, क्वांटम तथ्य विज्ञान अटे। गत काल से आईआईटी मद्रास एवं आइजर मोहाली रे मध्य कार्य करियछन्ति।
First of all, I thank the organizers for organizing such a wonderful program where so many school students are present and we will have the opportunity to talk to them. ISAs, you know, as they have come up 2006 onwards, first Calcutta and Pune, then Mohali, then Bhopal, Trivandrum, Behrampur and Tirupati, so on. So these are new institutions which are focused on science education and research, and they offer lots of opportunities to young students like you. The realization that we are not emphasizing science enough started in 1980s with the Planning Commission document which is 1985, which actually talks about starting institutions focused on science, because unless you nurture basic sciences in society, many other things cannot happen. And it was also realized that maybe we have underemphasized science and overemphasized many other disciplines, and therefore we must kind of do a corrective measure. So I actually see coming up of ISAs which happened in 2006-07 onwards as a corrective measure to bring back that emphasis on basic sciences which any society which is progressing needs. I was fortunate to be associated with ISAR Mohali from its day one when the institution was set up, and it has been a learning experience for me at Mohali. In that period, another set of institutions came up. One of them was the Institute of Nanoscience and Technology, whose founder director was Professor Ganguly, and he set up a very interesting science outreach program based at INST. And his coming to Behrampur clearly has brought that whole experience, which very much fits into the vision of ISAs of connecting science with society, and you see that outcome of that is maybe the today's program. So I really would like to congratulate him for organizing this program, and more than you giving us an opportunity to talk to all of you this morning. I am not just saying that I want to sound humble. Whenever I talk to young people, I am actually looking for that one or two those questions, those things which are coming from the young minds. Because you see, I talk to peers all the time, I talk to my PhD students all the time, and more or less I know how conversations are going to go. But when you talk to young bright minds, so many things get talked about, but there are always those one or two things which are useful for me, and therefore I like to learn from the audiences and students. Because as you grow older, your opportunities to learn actually diminish, and I consider this as an opportunity. I could see that whatever was being talked about was being translated into Odia. I could actually follow. So which means when I speak after this inaugural session, I will not be able to speak in Odia. I normally give these popular science lectures in Punjabi and Hindi. I am comfortable with those two languages when I talk to school students, but Odia is a little bit away from my knowledge of languages. But if you ask a question in Odia, I'll be more than happy to answer that, because you will see that, you know, as you grow, science itself is a language. And this whole idea that people who are good in languages, they are different from people who are good in sciences and mathematics and all that, is all a myth which is created in our school system, which needs to be remedied, because at the end of the day, it is human desire to understand and communicate. There are other domains of understanding where communication of that understanding is not important. Science is not one of those. So science is communicable knowledge. It is human knowledge which we all create and then we communicate, and therefore it is nothing but a language. It has a set of rules of its own, grammar of its own, and way of interpretation which is its own. Anyway, since my lecture is going to come after this inaugural session, I will be brief. It's also an opportunity for me to interact with the people outside my domain. There are so many distinguished scientists. Some of them I know, some of them I don't know. And they will be talking to you, and I will also get an opportunity to listen to them, because normally you listen to people in your own areas, and there also scientists are quite cryptic with each other, because they also want to keep the ideas hidden to some extent because they want to publish them in journals. But when scientists talk to young people, they open up a little more, and it also gives a very interesting opportunity for peers to see the point of view that those scientists have. So all said and done, it's a very nice 2-day program. Whatever of it I will be able to attend will be very useful for me, and I think it will be extremely useful for you. As Professor Ganguly was mentioning, that it is that passion that is within you that you must explore. Idea here is not to bring people together and then convert them into doing science, or for that matter anything, because I think worst you can do is convert someone to something. That is the biggest damage you can do to another human being, is convert. You should communicate and let the individual younger than you, if a student of yours, figure out what is inside them and let that come out. I always give this analogy about education. Is education process like a potter who converts the raw mud into identical vessels, or is it like a gardener who diligently nurtures the plants and each one becomes whatever is inside that plant? So whatever fruit has to come will come, the plants will grow in their own way. I think the role of education is more like gardeners to invest and give resources and opportunities to the younger generation, and let the individuals in that younger generation figure out what they want to do. So it may happen that this 2-day exposure to science makes you do music. Then the job of this program is done, because it prompted you to think within these 2 days what is within you. And if the answer is it is not science, that is as important as the answer which is yes, it is science. Because it's extremely important to distinguish between what you want to do and what you don't want to do. And there is no such systematic program in our school education system where this is done. So each one has to do for themselves. So this is a journey, and at your age, I can see that most of you will not even be knowing what you will be doing 5 years down the line, and that is the whole excitement of living a life, which, as was mentioned, you live only once. So with these words, I would like to close these remarks, because anyway, as I said, there is a talk on quantum physics I'm going to give after this. Once again, I thank IISER Berhampur, particularly the director of IISER Berhampur, for organizing this very interesting, exciting program at a very high level for all of you, and in some sense for all of us. Thank you.
Thank you, Professor Irwin, for his enlightening words. To present the concluding remarks of this inauguration, I now invite the chief guest of this event, Professor Arun Kumar Grover. Professor Grover currently holds the esteemed position of Honorary Professor at Punjab Engineering College in Chandigarh. His domain of expertise is multidisciplinary physics with a focus on fundamental issues such as magnetism and superconductivity. Professor Grover's extensive career includes serving as the former Vice Chancellor of Punjab University in Chandigarh and as a former professor at the prestigious Tata Institute of Fundamental Research in Mumbai.
ଏହି ଉଦ୍ଘାଟନୀ ସଭାର ସମାପନୀ ଟିପ୍ପଣୀ ନିମନ୍ତେ ମୁଁ ବର୍ତ୍ତମାନ ପ୍ରୋଫେସର ଅରୁଣ କୁମାର ଗ୍ରୋଭରଙ୍କୁ ମଞ୍ଚକୁ ଆସିବା ପାଇଁ ଆଗ୍ରହ କରୁଅଛି। प्रोफेसर ग्रोवर चंडीगढ़ स्थित पंजाब इंजीनियरिंग कॉलेज रो सम्मानित प्रोफेसर रूपे कार्यरत। से चुंबकीय तथा सुपर कंडक्टिविटी विज्ञान रो महारत हासिल करियछंती। पूर्वे से पंजाब यूनिवर्सिटी रो कुलपति भाबे एवं प्रख्यात टीआईएफआर मुंबई रे प्रोफेसर भाबे कार्य करिथिले।
Please welcome Professor Grover.
Good morning all. So I am delighted to have this opportunity to share the dais with Professor Ashok Ganguly and Professor Arvind. I met them very long ago. Ashok, when he joined for PhD with Professor at IISc, okay, and then I have this magnificent photograph given to me by Ashok, okay, with Professor Rao in the middle and Ashok and myself on the side. This hangs in my home at present. Professor Rao, you know, received the Bharat Ratna, I think 2015 and 2017, along with Sachin Tendulkar. They both received the Bharat Ratna on the same day. I also have an opportunity to meet old friends. Deepa Krishlani is here from TIFR, and I was a part of the team which inducted her in TIFR, I think 18 years or 19 years ago. And then Uday Maitra, whom again I have known for long. I organized his lecture for the young people like you as a part of the Olympiad medal winners at the Homi Bhabha Center for Science Education. And Professor Patnaik is here. I have written papers with him in superconductivity, and Jyoti is here from INST Mohali. She is a part of Indian National Young Academy of Sciences, and as a retired professor and a fellow of the Science Academies in Chandigarh partner with the INIAS chapter of Chandigarh, and we hold events like the one in which we have gathered here today. Now, science popularization is a passion with me, and I think Behrampur is very lucky that you have someone like Ashok Ganguly, whom I call the Ruchiram Sahni of 21st century. Who is Ruchiram Sahni? Ruchiram Sahni was a science popularization of Punjab, and when Vigyan Prasad published its first book in 1994, a little after the celebration of the birth centenary of Birbal Sahni, the son of Ruchiram Sahni, they brought out this biography of Ruchiram Sahni. People had forgotten about Ruchiram Sahni, but Ruchiram Sahni was the original popularization of science in Punjab from 1885 onwards. That is the time when she got motivated from Mahendralal Sarkar, who had created the Indian Association of Cultivation of Science at Calcutta in 1876. So, long story, but Ruchiram Sahni, for a brief while, studied in Calcutta University. He was a contemporary of famous Ashutosh Mukherjee, the Vice Chancellor of Calcutta University, who actually gave a great push to the scientific research in Calcutta at the beginning of 20th century. So Ruchiram Sahni returned to Lahore and created Punjab Science Institute, and he had delivered 500 public lectures at all sorts of places all across North India. He used to go to the village festivals and tell about science in everyday life. The water that Lahoris drank, how electricity works, how the wireless works. It is on such things that Ruchiram Sahni used to give public lectures in Punjabi, in Hindustani, English, whatever. He had a science workshop in his house, and he used to make these instruments for physics and chemistry experiment at his home, and which he used to distribute to the school teachers and so on. So, why do I call Ashok Sahni as a Ruchiram Sahni of the 21st century? So when Ashok came as the first founder director of INST Mohali. It is January of 2013. I had been there in Chandigarh 6 months earlier. Arvind was a founder member of ISAP, this thing. And when I came here, we created this platform called Chandigarh Region Innovation and Knowledge Cluster, which brought all the institutions on a common platform so that the staff and the students can share the facilities and do science better than what they can do individually. So after creating that platform, the first thing that we did was to commemorate the 150th birth year of Ruchiram Sani. Ruchiram Sani had been born in 1863, roughly at the same time when the first college came up in Punjab. So we said we will commemorate 150th birth year of Ruchiram Sani, and via that celebrate the progression of 150 years of higher education in Punjab. So we launched all this great event, got a stamp released, and we went to all sorts of places in Punjab to give public lectures. Most of us gave few lectures, but Ashok took upon himself that 80th birthday of his guru, Professor Rao, was in 2014. And Ashok said, to commemorate his guru's birthday, he will give 80 public lectures in one calendar year. And he took it as a mission, and he went all across North India. Later on he went even to the Northeast. Every weekend he will take his Innova, few people with him, go to remote schools in the rural areas of Punjab, Himachal and Haryana, and pitch himself there and do this demonstration of experiments. And Uday Maitra is here with us today, and he is going to repeat what Ashok used to do. So at the end of that 1 year, Professor Rao came to Chandigarh. He stayed in Chandigarh for 4 days, and he gave 4 public lectures in Chandigarh city. I don't know whether Ashok you remember. 4 lectures he gave. He gave one on the PU campus, he gave at once at ISA, one in the city, and we also took him to Manali. Right? So this was a grand way of celebrating Professor Rao's 80th birthday. Professor Rao's 90th birthday, I understand, is going to be commemorated next month. And so this is Ashok Ganguly for you. Someone who did what Ruchiram Sani did in Punjab for a period of 15 years from 1885 to 1898. So Ashok can do it, and I think he will bring people together, and with his personal enthusiasm, things will start to happen in this part of the country as well. And only yesterday we have dreamed of having an Infosys Science Prizes event, which happens once in a year in the month of January. So if things go right, in 2025, the Infosys Science Prize ceremony hopefully would happen in this part of the country, maybe in Bhubaneswar or Behrampur, and this is what we are aiming. Yesterday, the Infosys prizes were announced, and one of the prizes has gone to Jahnavi Phalke, who is engaged in science popularization. I think she is a part of NIAS now, and she is at Bangalore. So even the Infosys Science Prize jury has recognized in the field of humanities someone who is helping spread the message of science and technology in the contemporary times. So I am looking forward to exciting things happening here, and hopefully I'll come back again in the near future. Thank you very much.
Thank you, Professor Grover, for your enlightening words. With this, we conclude this inaugural session, and just allow us some time, so we set up for science to take the main stage. Thank you.
Where's the point?
Yeah, 2 pointers are there. One is inserted in here.
One is this, one is
Yeah, but now we have to shift this to one side, right? Laptop open रखना पड़ेगा.
सर चेयर भी निकाल देंगे.
पता नहीं.
बोल.
हेलो.
जिसका टॉक है उनका रेडी होना है.
उनका सब है.
उनको माइक नहीं दिया जो.
Hello. He will introduce you.
Hello everyone. I'm sorry for the slight delay. So if you all will please settle down, we will start it in just a moment. Hello everyone. I am Indra Kumar Banerjee and I am a third year PhD student in the Department of Physical Sciences, IISER Berhampur. And I have been given the privilege to request and introduce Professor Arun Grover as the chair for the first session of today's talk. So I would like to welcome Professor Arun Grover.
So I am very happy to have an opportunity to chair this session, which will have two talks. One by Deepa Kushlani, who was my old colleague at TIFR, and the second one by Arvind, who is my present colleague at Punjabi University Patiala. He is a Vice Chancellor and I am a member of the Senate and Syndicate, courtesy Arvind, at Punjabi University Patiala. So to introduce Deepa has a very rare career profile. She did her undergraduation and post-graduation in Canada. She was a teaching faculty in UK when she applied to TIFR, and we were all very surprised. But she wanted to come back to India, reverse of brain drain. Someone who is educated in North America, was working in England, returned to TIFR to set up a new group of trying to do nanochemistry. And this is what she has been doing for the last 18 years. She has outstanding science to her credit, and now she is applying that knowledge and that she has helped generate to solve societal problems. And today she is going to speak us on issues of societal concern which are connected to her own knowledge and research. So with this, I welcome Deepa to give today's talk.
Is there a handheld mic that I can use? ये वाला ये बंद कर दो शायद फीडबैक होगा फिर Okay. Um, Lots of different mics. Okay, I think this will work. So, good morning, everybody. And first of all, it is very humbling to be standing as the first speaker today in front of all of you and more, and also in front of this fantastic elite set of scientists who are also going to be giving you a talk today. And I get to be the first one to give, and I am absolutely humbled. So I want to thank Professor Ganguly, and I'll put the collar. So I want to, you can hear me, right? So I want to thank Professor Ganguly, everybody at ISA Behrampur, for creating this fantastic environment and workshop to allow you an exposure to kind of science that we do. And I hope by the end of my talk, you might have a little bit of appreciation for what drives us at TIFR in my group as to why we do what we do. So, the next slide, I will just, where is this? This is not working, so we shall try doing it this way. So first of all, where do I come from? I come from a very small institute. It's on the west coast of India. It's in Bombay, and if any of you are in the vicinity, please do drop by. I'll be happy to show you around. I thought I would just show you the very institute. It's also right by the waterfront, just like the new ISER campus is. Thank you. Now, the title of my talk is on energy. So I thought I would sort of show you, energy is sort of a very bizarre word. People don't really know what it means, but we have various forms of energy. When you're in school, you get to learn about various forms of energy. Things like mechanical energy and electrical energy and so forth. You also hear of the words like potential energy and kinetic energy from a point of view of fundamentals of science. But from practical point of view, this is what energy is. So let me make it perfectly clear. The reason you are getting to sit here is because you've eaten in the morning, so you have eaten food and that's given you chemical energy. Food has chemical energy and it releases energy. There's lots of biological processes involving ATP and so forth that allow you to function and move. So that's a different kind of energy. Plus you have perhaps taken an auto or a two-wheeler or a car or a bus to get here. That needed energy for you to get here, right? It was burning some sort of fuel that allowed the internal combustion engine to work, and therefore it did the work for you as you came here. By the same token, sitting in this room, we have lights, we have air conditioners, we have a projector. All of this is using energy. Again, some form of electrical energy that allows you to be able to listen to me and me get to talk to you, right? So it's a very valuable entity, as it were. So, and I'm going to put it in perspective as to how valuable it really is in a different way. Let's talk a little bit about a socialist aspect. So we're talking about the population of this country. Currently, I think all of you know, I think India has surpassed China as the most populous country in the world. Yes? I do not know the exact number. This is from 2000. So second place, but I got this projection 65, and you see India is the most populous country and it will continue to be the most populous country in the world. Now, I'm talking about the population of this country because what I'm trying to get at is the problem we're addressing is really, really crucial to this country because of its population. Now, there's another thing I'm going to show you. This is a graph of something called the Human Development Index. It was a number created by the United Nations, and it encompasses everything from the quality of life, the education, the earning capacity of a human being, the GDP basically, the medical services, the life expectancy. Everything goes into what is called the Human Development Index number. What you want is this number to be as high as possible because it means that the people of that country have a really good lifestyle. If you look at these names over here, which have this high HDI number, you will see it's all the countries that Indians want to emigrate. Correct? When you want to go, because you know intrinsically that they have a better quality of life. Why we want to go to USA and Canada and so forth and Europe. Now, whereas India highlighted that on the as a circle. Now I've not shown you. So on the y-axis is the HDI. What I've not shown you is on the x-axis. What is HDI sort of dependent on? Okay? I'm now going to show you what it's dependent on. And I'm not sure if you can read it at the bottom. It says the electricity consumption by that country per capita. Alright? So think of it in terms of the energy that each human being is consuming to provide themselves, to provide their environment with that HDI index. Means as a country in India, if we want that number to rise, if you want the level of education, life expectancy, money and quality of life, better roads, bigger buildings, what do we have to do? One of the things we have to have an expenditure on is the amount of energy per human being consumes. Alright? I'll put it in perspective. Think of it, when you earn more money, what do? You want to basically buy a bigger car or buy an AC or a better mobile phone, and that leads to other issues. If you have access to internet, you will be more educated. The quality of life will improve. But to run those devices, you will spend more on electricity. Therefore, your energy consumption is increasing. Your quality of life is increasing, but your consumption of energy is increasing. All right? So, now, question is, where is all this? And remember, so just to remind you again, we are the most populous country. So as a whole country, if we want to improve and increase the energy consumption of this ever-growing population, the energy requirement of India is going to be mammoth, very large. Correct? Everybody fine? Now, where is this energy coming from? For example, where does electricity come from? All this lovely, you switch on the switch, light comes on. But where are those electrons coming from, if you think about it? How is the government providing you that electricity? Anybody know? Where? Who knows where the electricity comes from? Electricity predominantly comes from something called thermal power plants. What are thermal power plants? They are nothing but a place where coal, C-O-A-L, coal gets combusted. Alright? Coal is made up of carbon-carbon bonds. Those carbon-carbon bonds hold a lot of energy, chemical energy. Thermal power plants convert that chemical energy into electrical energy in some respects. Is that fine? Right? What am I showing you by that pie chart? You see that black of the pie chart is the energy that is coming from coal for the entire country. The little other colors you see there are the other kinds of energy. What other sources of electricity can be there? Can anyone tell me? Solar energy, someone said, which is very good. So those are solar cells. Very small fraction of our country's requirements are being met by solar cells. Someone said something else. Fantastic participation. I'm sorry, everyone's speaking, so I'm having a hard time understanding. There's also wind turbine engines, for example. Anything else? Hydroelectric power, right? All of those are lovely words. They make us feel good. But reality is the black part. Okay? And I'll also tell you something, a bit of a reality check. Thermal power plants are not decreasing in quantity with time. It's not like next year this pie chart will be smaller. It won't. Governments want to ensure that their population has 24-hour electricity supply. So what do? They make and install and commission new coal power plants. All right? Even as of a few years ago in Maharashtra, they had commissioned a new power plant. Means they're burning more and more coal with each passing year because our population is increasing, plus we want electricity supply because we want a good quality of life. Correct? Everybody understand the relationship. What happens when we burn? This slide kind of gives you a nice idea. It isn't only about burning coal in a power plant, it's also about burning any carbon-based material. And this includes gasoline in your car, this includes diesel in your truck, all right? This includes a lot of construction. So there are lots of sources or points where we burn carbon-based material. Problem is when we get energy out of that. Lots of cheap energy, cheap being the operative word, but this is the side effect of that. All right? And what I want to show you is, by the way, the image on the right was not something like 20 years ago. This is obviously from Delhi, so forgive me. You know, it's the most polluted place in India. It's been in the news lately. The image on the right, for those of you who you can't read, I'm sorry, the figure caption, it's from April 2020. What was happening in April 2020? Lockdown. What happens in lockdown? We were not living our day-to-day normal life. We were having a less, but I'm sure some of your parents would have found their electricity bills slightly altered, or the cost depending on their gas, right? There was a direct, you can say whether it's direct or indirect, but you see the difference in the quality of air, for example. This is just one aspect. There are many, many other aspects of burning carbon. Everybody okay, right? What do we want? We want the stuff on the right. What do we not want? The stuff on the left. What is reality? The stuff on the left. And is the left image going to improve with time at the current way of living? No. It will continue to deteriorate. Now, just a little bit of fundamental science, fundamental chemistry to help you understand. Those of you, I hope I won't bore you, and I don't want any students to go to sleep, but the equation I'm showing you, when you burn carbon-based, the reaction on the top is what is called complete combustion. All right? So you take a carbon-based thing, in this case is CH4. Anyone know what CH4 is called? Fantastic. I love this crowd. So methane and oxygen becomes carbon dioxide and water. Very good. Carbon dioxide is a problem, but that is a complete combustion. Many times you don't get complete combustion, you get partial combustion. And that leads to the carbon particles, the soot in the air. And that also has sulfur dioxide, nitrous oxide, nitrogen dioxide, SOx and NOx we call it. X means it could be any little number. These, if you look into literature, if you start reading upon pollution, air pollution, people talk about PM 2.5. What is PM 2.5? It's 2.5 micron size particles, because that is what is suspended. They're the ones scattering light, makes it look like you have a foggy day. And those particles we breathe in cause issues, give us cancer, give us asthma, give us lots of other health. Now, so that is the problem, right? Not to make everyone very upset, but I'm trying to put it in perspective about the current reality as of 2023. Now, how do we try and deal with this problem? One way is we can say, okay, everybody stop driving your cars, stop putting on your AC, stop, consuming so much electricity. but that is not the answer, right? There has to be some other way of dealing with the problem. I'm going to highlight a few ways that we try and tackle this problem that will hopefully inspire you to see how simple science that you hopefully can understand at your level, can make perhaps a contribution, substantial contribution. So, one way that we can think of is, let's say we stop burning fuel, right? So means let's stop burning carbon-based, oil, diesel, coal, what have you, right? Let's worry about the crude oil that is coming. So, that means, so now, what do we burn it for? We burn it for energy. Means how many kilojoules? It's a little interference. At least I'm getting a lot of interference this way. But it's me. I'll hold it. So, so the main thing is we want to get as much energy per mole or per gram of material. We want to basically release energy from some chemical, right, that can give us energy equivalent to what is available from burning carbon-based things. This is all from Wikipedia, in case you're wondering. So I want you to look at the stuff on the column extreme on the right. And I want you to see how much energy is stored in a very simple molecule called the hydrogen molecule. It's substantially more than what's in your conventional carbon-based material. Now, so what ends up happening, just so you understand the combustion reaction, it's a very simple combustion reaction. Look at the top reaction, which I'd shown you already. And then look at the bottom reaction, which is a combustion reaction of the hydrogen molecule. What is the main difference? Carbon dioxide is not there. Fantastic. Carbon dioxide, is that a good thing or a bad thing? No, the fact that carbon dioxide is not there, it's a good thing. I am still releasing energy. I am breaking that hydrogen-hydrogen bond, and I'm releasing a lot of energy, right? Substantially more. Means the amount of hydrogen actually I need to burn would be a lot less than I would use diesel fuel for. And the best part is, I am not making any pollution in the world. What is the product? Product is water. Water is a nice product to play with, right? So you'll say, fantastic. We'll take our car, we won't put diesel inside it, we won't put gasoline, we will fill it up with a hydrogen molecule, right? And do the same reaction that diesel does, that gasoline does. We will have to change the way our internal combustion engine works, but the fuel we are using is hydrogen molecule, and the byproduct of that is water. Therefore, there is no fumes coming out of that vehicle. And these vehicles do exist. All right? It's not unheard of. This is a bus. This particular image is from a bus in Canada. What does it say at the top? Zero emission. Good thing, right? That's why they have green leaves on it, making you feel very proud and very happy. If you think this only happens abroad, it also happens in India. And what you see here, bus, in case you can't read the title, I will read it for you. It says, India's first ever hydrogen powered by Tata Motors is here. And this is March 2018. You can look at it. It's on India Today. You'll go, fantastic, right? These buses exist. They work on hydrogen gas. There's no pollution. Why don't I see it outside parked? Why did we not take it from Mysore Berhampur to come to this transit campus? Why did you not use it in your auto? What is, there must be some issue. Tata is making it. Any guesses for what the big problem is for mass commercialization? Engine mechanisms, storage of hydrogen, transportation of hydrogen, and source. Lots of issues. It's expensive. Why would it be expensive? Okay, we can come back to that. Engine mechanics, this is a fuel cell. It's not difficult, it's been done. All right? Money to paisa bahut hai is duniya mein. You guys are buying iPhones, no? Expensive stuff is there. Transportation of hydrogen, okay? Hydrogen cylinders exist, you know, people do you think diesel is not flammable? Diesel is flammable. Your CNG gas is flammable. Gas cooking का gas flammable है. हम transport करते हैं, हाँ? उसमें कौन सी problem हो गई? He brought up something very interesting. Sorry? I didn't hear the first word. Deficiency. You see, hydrogen molecule आएगा कहाँ से? There is no lake under Saudi Arabia that we can say, hydrogen lake है, वहाँ से हम extract करेंगे, right? There is no large deposit of naturally occurring hydrogen molecule that is easily accessible for us to use it by the whole humanity of this planet. So you'll say, well, that is a problem. It's a lovely molecule. It's going to solve our problems. But we have to, the planet is not providing it for us. Therefore, we have to make it. Okay? So this is the issue. Now, but you will say, well, hydrogen cylinders तो मैंने देखे हैं कहीं research lab में, कहीं ना कहीं तो hydrogen cylinder होगा. It's a molecule you're familiar with, right? You know it's flammable, it exists. So we must be making it somehow. How do we make it currently? We make it through this technique, all right? It's again a version of partial oxidation of carbon-based resources, all right? The equations are given there. I've highlighted in circle. I apologize, the projector thoda itna bada nahi hai. But you make carbon monoxide and you make hydrogen molecule, hydrogen gas, and you get this happening. So, you think this is the way to solve our problem of making large-scale hydrogen? If I'm going to be making pollution, to make the hydrogen molecule is not the answer, correct? We need to find another way of making it. So, how do we do this? So this is where science comes in, and then we look around us. All right, we look around us and say, well, wait a minute. There are lots of interesting things going on around us. Can we get inspiration? So I'm going to tell you about a certain kind of inspiration. What is this inspiration? Photosynthesis. What is photosynthesis? Photosynthesis is a very interesting thing. Plants do it all the time. What are the reagents? What does the plant take from the environment? Carbon dioxide and water. Carbon dioxide and water. And what does it make? Oxygen and glucose. Fantastic. All of you know your funders very well. Right? This is the equation I've written at the bottom. You know, if you think about it, this room has a lot of carbon dioxide. I am breathing out carbon dioxide, right? And we also have lots of moisture. Thodi humidity hai, right? I don't see glucose dropping out of the air. There is CO2 and there is water. Right? Correct? CO2 and water reacting together is not a spontaneous reaction. If it was spontaneous reaction, glucose gir raha hota abhi. Right? But this is only happening inside the leaves of the plant. Question is why? Why is the the chloroplast, right, have chlorophyll in them, and inside Chlorophyll is a fantastic, complicated set of reactions. Don't worry about all of this, all right? But what I want you to do is, I'm going to highlight two circles in the corner. What is happening is the carbon dioxide participates in making glucose, right? And the water participates in making oxygen. So that's the part I want you to pay attention to. Water participates in making oxygen. H2O, which is water, is making oxygen. वो हाइड्रोजन क्या करता है? वो हाइड्रोजन ग्लूकोज को दे देता है. पर हम कुछ और करना चाहते हैं. हम करना चाहते हैं water splitting, which happens inside photosynthesis. Photosynthesis का primary product is glucose और food, fruit and vegetables बनाता है. हमें वो नहीं करना. We want to take water, but we want to make hydrogen gas. Now, if you think about it, it's kind of like what you already know in chemistry, that every reaction is reversible, correct? Therefore, the top reaction is our combustion reaction. It will release energy. But to make the hydrogen molecule, why don't we do the reverse reaction? The reverse reaction is called water splitting, and we are splitting water to make the hydrogen molecule. But now we have to give energy, right? It's a thermodynamically uphill reaction. The top reaction is it endo or exothermic? You may or may not know this. And upper wala reaction is exothermic. Thank you. Excellent participation. And the bottom reaction is therefore endothermic. Endothermic reaction need energy, right? Because the energy is getting stored inside the hydrogen molecule gas. Now, I'm going to make life a little bit more complicated for you guys. That water splitting reaction is a slightly complicated reaction, and it's called a redox reaction. So, एक oxidation half reaction होता है और एक reduction half reaction होता है. वो दोनों unison में काम करते हैं. They work together to give you the net reaction which I've written at the bottom. All right? I hope everyone's okay with this part. So what it is there's an oxidation reaction occurring and there's a reduction reaction occurring. And therefore, if we want to do water splitting, we have to drive a redox reaction. Now, I do not know how many of you are familiar with this, but अगर आपका reaction redox है ना, if this involves electron transfer like this, आप इसको electrochemically कर सकते हो, electricity supply कर सकते हो. These are three ways. I will not spend too much time, but I want you to, I will talk only about the fact, because it's endothermic, it needs energy. Therefore, we kind of write it like this. How many of you are familiar with this sort of a diagram? Nobody. All right. So just keep this in mind. This is my the reagent. इसमें एनर्जी चाहिए, एनर्जी डालनी है इधर पहुंचने में. इधर पहुंचने में दिस इज कॉल्ड द एक्टिवेशन बैरियर. कुछ एक्टिवेट करना है उसको. दिस इज व्हाट chlorophyll does in plants. Chlorophyll drives CO2 and water to give us glucose. It activates those molecules. What is chlorophyll called by another word? It's a enzyme, catalyst. Suna hai those words? Yes. So it's a catalyst. What does it do? It basically lowers the activation energy. ठीक है? जैसे वो mountain cross करना है ना, उसको कम कर देता है. तो हमें catalyst चाहिए. नहीं आ रही क्या बात? So, okay, I'm having a lot of issues today for some reason with the mic. Yeah? So this is where we have to find catalyst to bring the energy requirement. नहीं तो energy चाहिए उस redox reaction करने के लिए, ठीक है? So this is what we do, and how do we provide this energy to activate the catalyst? Just like in photosynthesis, the word is photosynthesis, the energy comes from sun. You see, and देखो काफी complicated है if you think about it. I can take a leaf and I can take chlorophyll out of the leaf. I can put it in a beaker. It will not get glucose, correct? It's a much more complicated life. But that is what we want to do, but I don't want to make glucose, I want hydrogen molecule. So I also want a catalyst. I also wanted to drive a water splitting reaction, and I want to do it efficiently, and I want to drive it with the energy given by sunlight. Okay? I'm going to skip the next slide, which talks about the kind of materials people use, and these are called semiconductors. Semiconductors are man-made materials that sort of have similar characteristics to the function of chlorophyll. Okay? And there are a variety of semiconductors. I've shown you some fancy words here, fancy diagrams. Here's a review paper, just so you understand. It lists a whole bunch of research that many scientists all over the world are doing. Okay? All over the world. And they have listed various materials, catalysts. A beaker of water. Alright, that's it. It's a solid material. You take a beaker of water, you put the solid material, it's suspended in water. Water is the reagent. You shine light on it. And what you see are bubbles of hydrogen and oxygen coming out, in principle. Okay? It's a very simple experiment. And it lists the kind of hydrogen output you get. Now, you say, well, it's been done. I know you read this slide. Despite having all these fancy taking hydrogen gas in such a simple experiment, having a beaker with water, shining light, and the water is getting used up and making hydrogen gas. The problem is what research does. You think you've solved one problem, there's another problem to be encountered. The water they use is something called deionized water, or how much water is present on the planet? A lot. How much of it is fresh water? 4%. Now, are we going to use that water to drive the use it to quench the thirst of society? It's a no-brainer, right? So this becomes the next problem, which is the type of reagent that goes into that chemistry has to be deionized. Why does it have to be deionized? Because you have ions present. With third time lucky. Yeah? All right. How am I doing with time? Oh my gosh. He's giving me 10 minutes. All right. So what is the problem? Because this is the slide I wanted to show you. There are ions present in that water. Those ions also participate in the redox reactions. For example, Cl minus, chloride ions, will become chlorine gas. So problem is we can't use seawater because there is a chance that we will oxidize the Cl minus into Cl2. Now, no one wants to be breathing chlorine gas. We want hydrogen and oxygen, correct? So we don't want interference. So, cutting a very long story short, this is the kind of experiment we do, and I'll just show you the last slide. So we have evolved the catalyst. We have changed the chemistry of the catalyst. We have done it in such a way that despite chloride ions and sodium ions and potassium ions being present in seawater, okay, basically it's not desalinated seawater, it is real seawater. We can use And when we use our catalyst, we suspend, so the diagram I'd shown you before, this sort of experiment, which is just a beaker of water, catalyst suspended, shine light, the water is now seawater, and what we find is not only can we split seawater and make hydrogen gas, but the best part is the efficiency of the catalyst is far superior in seawater as opposed to water, deionized water, right? So it's a nice, cheap energy. What energy we're using? We're using sunlight. I'm not using electricity or any other kind of light. Therefore, in principle, anybody can make hydrogen gas as long as sun is shining. If you're making hydrogen gas as long as sun is shining, you can use that hydrogen gas to power your fuel cell. And the fuel cell you can put in any of the devices you want, right? We're still not there yet. Just so I put things in perspective. If you want to be richer than Elon Musk, if you want to be richer than Bill Gates, this is a very nice problem to tackle because it will give free energy to every human being on the planet. Think about the potential of that, right? Catalyst means you reuse the catalyst. You don't have to make the catalyst over and over. But in principle, it has the chance of giving people access to energy to improve the quality of life without creating pollution in the process, right? We're not there yet, but something for you to think about. By the same token, there are other ways of generating. I will quickly go through one project that I think will interest you. We work on solar cells. I won't bore you with solar cells, but I will tell you a little bit about a project that might excite you a little bit. This image shows you a solar cell farm. What you need to keep in mind, solar cells generate electricity, but the minute the sun stops shining, what happens? They don't generate electricity. Solar cells do not store the energy. You have to couple the solar cell with what is called a battery setup as well. And you can see there's a large amount of storage batteries there that have been kept next to the solar farm so that you can store the energy, because actually we use the energy more at night when the sun is not shining, correct? And that happens right now in your day-to-day life. Your cell phone, if it runs out of charge, you have to rush to the nearest electrical outlet. If you're in the car and you don't have your charger, you are lost because you don't have charge in your battery. Wouldn't it be nice if we could charge our battery with sunlight directly? The concept being solar battery. I'm not saying put a solar cell on your phone. I'm saying directly the battery material that you're using, not only is it redox active because it does the storage function and gives you charge when you want it, but or discharge, it discharges for the work you want it to do, but it can get charged directly in sunlight. So that is what we work on. Just so you understand, I'll give you a little graph. So this is a solar cell. You see the yellow part? That is when we irradiate it with sunlight. And you see the potential go up, but the minute we switch off the light, the potential comes down. Right? Everybody fine? Now I'll just show you one last graph. Sorry. यहाँ पे मैंने अपने sample, our material, I've irradiated with 20 minutes of light. So the potential has gone up. But after 20 minutes, I switched off the light. Now I want you to see the graph. You see it's not dropping down immediately. There is a plateauing going on. It's going on up to 16 hours. Means there is no loss of charge in that material. And I can discharge it as an electrical impulse in my battery. So, hopefully in the future, if our work comes to fruition, your laptops and your phones will have a transparency on the bottom so that when you're driving in your car, you just stick the battery out in sunlight and it's charging away for you without any issue. Okay? This work is far from fruition. That is what we're working towards. This is our charge and discharge cycle and so forth. We work on lots of other things, but I'll end here because I've run out of time. So we work on lots of different projects. I don't do anything. I have a fantastic set of students. There are a couple of them who come from Orissa, and they do all the work, and I wouldn't be here without them. And there's some people who give us money, and especially you guys, they give me support and encouragement to continue to do what we do, and I'll be happy to answer any questions. So thank you.
So we have time for questions. Up to 4 or 5 questions we can take. So do not hesitate. Ask whatever you wish to ask. Please go ahead.
There's one hand over there.
Yeah, okay. Stand up and speak. You can come forward.
Or you can shout. Oh, yahan pe bhi hai. Okay.
Come forward.
Yeah, come.
Good morning, sir. Good morning, ma'am. I have a doubt that if we already know the solution, then what is the problem in executing it?
Okay. So this is what happens in science. We talk about all the positive things. There are lots of negative things. The thing with the catalyst for seawater is I can use it about 4 or 5 times, and then I have to regenerate it. It starts degrading with time. Okay? The other thing is the efficiency is not as high as I want. I'm making more hydrogen gas, but the cost of making the catalyst is a little high still. So I need to find cheaper ways of making it, and I want to improve what is photon to electron conversion efficiency. Think of it, photons are in sunlight se ek photon se meko ek electron generate karna hai. That efficiency of 1 to 1 is not happening. It's a little less. So industry बोलता है थोड़ी और मेहनत करो, पैसा कम हमें invest करना है, because consumers, just like solar cells exist, correct? You and I do not have it in our house. Science exists. Money is the issue now, right? Solar cells have been around for 60 years. NASA puts it in their satellites. Rich people in America put it in their homes. I am not sure everyone in India is doing it still. About the cost. Okay? That
Thank
part
you,
of
ma'am.
life. Yeah.
As we know, every chemical compound, no matter taken from any source, is made up of same type of elements. Similarly, water is also made up of hydrogen and oxygen, no matter taken from seawater or it is fresh water. So if we can generate electricity by splitting water into hydrogen and oxygen from fresh water, then why can't we use the seawater then?
Okay, there's a little issue here. What I'm doing is I'm taking seawater, I'm splitting it to make hydrogen gas. So H2O goes to O2 and H2. This H2 molecule is my source of energy. This reaction needed energy. It was an endothermic reaction. पर मैंने जब H2 बना दिया है, H2 को मेरे को combust करना है. So H2 plus O2 gives me back water. That is now a exothermic reaction. Energy is getting released. That happens in a fuel cell. Okay?
I am asking why we can't use seawater to generate electricity.
Why can we not use seawater to generate electricity? Why seawater cannot be used to generate electricity?
Yeah.
Right. So seawater makes the hydrogen molecule. Hydrogen molecule then has to be combusted, like diesel gets combusted. Okay? So hydrogen molecule is the replacement for diesel or gasoline. वो combustion करता है और वो खुद से पानी बनाता है. So it's like a cycle. पानी से मेरे को H2 बनाना है, H2 combustion के लिए वापस पानी आता है. फिर पानी को मेरे को एंडोथर्मिक प्रोसेस से H2 बनाना है, H2 एक्सोथर्मिकली वापस पानी देता है. साइकिल है पूरी. Why sea water? So the issue is sea water में वो chloride ions है ना, तो chloride ions की वजह से H2 इतनी आसानी से नहीं बनता, O2 नहीं बनता.
Is there not any method that we can remove those chloride ions or
So
can
something called
purify?
desalination. Desalination के लिए क्या चाहिए? Electricity चाहिए और महंगा हो जाता है वो process. तो मैं बोलती हूँ desalination की जरूरत नहीं है. We will not desalinate. We will not remove the ions. We will use seawater directly to make H2. ठीक है?
Yes, teacher. Thank you.
Trying to cut the cost.
Yes,
Sorry.
please go ahead. Yes, young girl.
मैम प्रेजेंटली हाइड्रोजन प्रेजेंट है तो हम उस एलिमेंट के द्वारा जो हमारी दिक्कतें हैं उसका एक सोल्यूशन सोच पा रहे हैं. इफ वी इमेजिन अ वर्ल्ड जहाँ पे हाइड्रोजन या वैसा एलिमेंट प्रेजेंट ना हो, सो इज देयर एनी ऑल्टरनेट सोल्यूशन कि ऐसी कोई एलिमेंट या कंपाउंड के पास उतनी कैपेबिलिटी है वैसा सोल्यूशन देने की?
तो यू सी हाइड्रोजन मॉलिक्यूल मैं एनर्जी के लिए यूज कर रही हूँ. दैट्स अ केमिकल सोर्स ऑफ एनर्जी. सनलाइट इज देयर. सनलाइट कन्वर्ट्स एनर्जी, सोलर एनर्जी डायरेक्टली टू इलेक्ट्रिसिटी. तो वो है सोलर सेल. ठीक है, तो वो तरीका भी है. देन यू हैव समथिंग कॉल्ड हाइड्रो इलेक्ट्रिक पावर. क्या होता है? वो पानी ऊपर होता है, नीचे गिरता है. वो जब नीचे गिरता है उसके पास एनर्जी होती है, किनेटिक एनर्जी. वो किनेटिक एनर्जी ड्राइव्स अ टर्बाइन इंजन. ठीक है, वो टर्बाइन इंजन से any other element. Okay, so this is the other issue. We should also have a large source of that element. We should not create pollution. And if you think about, so right now hydrogen molecule is the closest one that's coming to solve. Sorry, chemical energy की हिसाब से hydrogen molecule has the largest amount of energy that we can use and that does not create pollution. पानी बनाता है.
थैंक यू.
Sorry? N2 से अमोनिया बन सकता है, ठीक है, पर फिर you have to deal with ammonia issues. Ammonia is another energy carrying molecule.
मैम मैम जैसे कि आपने बताया कि मनी और अदर इश्यूज के वजह से हम ये सब यूज करके हाइड्रोजन प्रोड्यूस नहीं कर पा रहे हैं.
लार्ज स्केल, छोटे स्केल पे हो रहा है.
हाँ, तो जब वो मनी और अदर अवेलेबिलिटीज होगा, क्या सबके लिए उतना क्वांटिटी है कि सब लोग उसे यूज कर सके?
देखिए, we have to hope for a better future. I am not saying I have all the answers right now. I am just showing you some of the thought processes today. You see, 100 साल पहले जब इंटरनल कंबशन इंजन बनाई गई थी, उस वक्त उन्होंने सोचा नहीं था कि अगर हम कार्बन को बर्न करेंगे तो इतना पोल्यूशन होगा आगे जाके, राइट? Maybe they knew, maybe they didn't know, I don't know. You know, we all try and do things for the betterment of society along the way things happen. So right now, इस सोच के हिसाब से I'm giving you various options that we're trying to do to alleviate our dependence on carbon. And एक चीज सब कुछ replace नहीं कर पा रही है. We looking at different methodologies, different ideas, different ways of doing things. And the idea is that to decrease, the main aim is कैसे ना कैसे ये pollution को कम तो करना है हर हालत में. We cannot continue, especially in India. That was my introduction, guys. Especially in India, I don't care what's going on in the rest of the world. Especially in India, with the population, with the kind of GDP we have, with the kind of hope that we have, that we want a better life. And I'm sorry, I do not want all of us to rush to America and Europe to have a better life. I want to have a better life in this country, right? We have to start tackling these problems head on. And we have to do it with this kind of science and other ideas, which we want you to come up with.
Ma'am, how and when can we start doing these ideas?
If I knew the answer, I would be richer than Elon Musk. If I knew the timeline. But hope होनी चाहिए, कोशिश होनी चाहिए, मेहनत होनी चाहिए, integrity होनी चाहिए, ethics होनी चाहिए. जो science करो आप ढंग से करो, अच्छी तरह करो, समझता ये होनी चाहिए. And mass scale होना चाहिए. ठीक है? एक तरफ से हर चीज लोग पैसे के पीछे दौड़ते हैं. I'm trying to inspire you to have different focus in mind as well.
गुड मॉर्निंग एवरीवन. सो मैम मेरा क्वेश्चन सिंपल है. अभी हम सोलर एनर्जी को यूज़ करेंगे, अगर इन फ्यूचर वी वाज हैविंग फैसिलिटीज, हम उसे यूज़ कर रहे हैं, हम उसका भी तो कुछ ड्रॉबैक्स होगा ना, मतलब उसे भी तो एक्सटेंड तक ही यूज़ कर सकते हैं. सोलर एनर्जी लाइक इट्स वंडरफुल रिसोर्स, बट उसके भी कुछ ड्रॉबैक्स होंगे यूज़ करने के.
बिल्कुल. The drawback is not about solar energy, it's about the solar cells we make to capture this energy. Those silicon solar cells have a lifetime of about 20 years. Okay? The silicon comes from China. In India only assembles it. We don't mine our own silicon. You know, there are lots of issues.
Lack of
Worldwide, geopolitical, this, that. And it's not the answer. So we want to make cheaper solar cells. That I didn't talk about our project towards trying to make cheaper, better, more efficient. The silicon solar cells are about 20% efficient. On the day you buy them, 22%. मतलब हर photon के हिसाब से आपको only 1/5 of those photons are going towards electricity. All right. that gets stored in lithium basically.
But
in
we
a
are
lithium
using
material.
the alternating current in our home appliances.
In your home appliances, you don't have a battery, right? So unless it's plugged into the socket and the copper wire that is giving you electricity, unless it's plugged in, you won't be able to use your appliance, right? So that is a direct electricity coming in a copper wire. The electrons are coming in a copper wire, okay? And where are those electrons coming from? From the city's thermal power plant, जहाँ पे भी वो situated है. अच्छा, you want to talk about DC and AC power? Oh my gosh, in the battery concept, even I don't know. This parts I don't know in terms of, obviously this is an alternating current. In your battery it will be a, you help me out, you're a physicist. Yeah.
Yeah, you know, the batteries do give the DC output, but when we want to use it in AC, like what is done in inverter, you need an equipment. But then if you think about it, most of our current appliances actually run on converted DC power. All the cell phone chargers that you are using, the TV, the stereo, if you have any of one of those, actually run on DC. So there was in fact a proposal to provide a 50-volt DC supply to all houses so that you don't have to use so many of these converters which consume power. You know, if you keep a adapter plugged in, it gets warm, whether you are consuming power or not. So that was one of the thoughts that I heard in a talk, but I think that has not happened. But yes, it is true that for many appliances like motors, we use AC, but then nowadays many fans which use a BLDC supply, BLDC technology, they use direct current. So they are also in the fan, there is a AC to DC converter. So in some sense, it will actually make more practical sense to have a DC supply rather than converting back to AC, at least for some appliances.
Fantastic. See, that's why it's important to have, you know, excellent scientists, because of which, you know, they help each other, we help each other out. Yeah? Thank you.
Yeah, so I would like to call our director, Professor Ashok Ganguly, on stage to felicitate the speaker and the chair for the session. Okay, so now we have a tea coffee break. So I would request all the students to go outside and have tea and coffee. And also, there is an amazing thing going on right outside the auditorium that is called the waste to wealth theme. So they have taken different kinds of parts which are usually called waste, and they made amazing structures out of them. So please do visit that as well. We meet back at 11:45. Thank you. I would like to request everyone to please take your seats. We are going to start the session now. Everyone please take your seats. Settle down. Hello? Yeah. So I'd like to request everyone to settle down, please. We would like to resume our session. This is to all the students. Please settle down as soon as possible. We would like to resume our session.
So welcome back. I think it's time for us to start this session, and we have a very interesting talk which awaits us. The talk will be delivered by Professor Arvind. Professor Arvind, as we learned in the morning, he is currently the Vice Chancellor of Punjabi University, Patiala. There are only two universities in the world which are named after a language. One is the Hebrew University in Israel, and the other is the Punjabi University, Patiala. So it's a heritage university of Punjab, and Professor Arvind is the current Vice Chancellor of it. Arvind had his undergraduate education at Guru Nanak Dev University, Amritsar. Thereafter, he was a topper there. He moved on to do his masters from IIT Kanpur. Thereon he moved on to Indian Institute of Science, where he did with his PhD with a very eminent theoretical physicist who is also very active in the field of physics education. He is the founder editor of Resonance, Professor Mukunda. So Arvind did his PhD with him. Thereafter, he had taken up a job at GNDU. From there he went to Carnegie Mellon. From Carnegie Mellon he came back as a faculty at IIT Madras, and when the IISER Mohali was created, he is one of the founding faculty members of IISER Mohali. Okay, that is 2007. And he is currently on deputation from IISER Mohali as the Vice Chancellor of Punjabi University, Patiala. And just last week he got elected as a fellow of the National Academy of Sciences, and Arvind is a very popular physicist in Punjab because he delivers many talks for the general audience. I have listened to him in English, Hindustani, Punjabi, whatever. So we just had a very wonderful talk from him last year on the occasion of Nobel Prize in Physics, and he delivered it in vernacular in Punjabi. And today he is going to speak to us a glimpse into the quantum world, and given his facility to speak in multiple languages, okay, Arvind can even speak to you on this topic even in Hindustani if that is your desire of the audience. You can ask him any question in whatever language of your convenience, and I am sure Arvind will oblige all of us. So with this, I welcome Professor Arvind to deliver his talk.
This connection की HDMI आ गया. Shall I get my laptop? नहीं वहाँ आ ही नहीं रहा ना. The problem क्या है? But then something is not working. माउस है आपके पास? कुछ हुआ तो सर? यू हैव अ माउस? माउस लगा लीजिए. Well, things can always fail, so the computer has failed, we'll wait 2 minutes. This mouse is not coming here. लैपटॉप दूसरा लगा लीजिए. All right, so I think set, and I'm glad it took some time because some students were walking in. Well, in the morning session, I had said the broad things. I once again thank the organizers for asking me to speak to you, and I thank Professor Grover for such a kind, detailed introduction. So I am going to talk to you about the quantum world with a view to give you a glimpse. For example, if you want to learn quantum mechanics properly, it takes several years. So the idea of this talk is not to teach quantum mechanics, it is to excite you about quantum mechanics and quantum world view and give you a glimpse so that if any of you get interested, can then pursue this area. So that should be very clear. आप जिस भाषा में भी अपना कुछ प्रश्न पूछना चाहें पूछ सकते हैं. इंग्लिश, हिंदी, उड़िया में भी पूछेंगे तो मुझे समझ आ जाएगा क्योंकि आप क्वांटम फिजिक्स के बारे में पूछ रहे होंगे और उसके मुझे आइडिया मिल जाएगा कि आप क्या बात करना चाहते हैं. ये पूरी जो स्टोरी है क्वांटम फिजिक्स की, वी कॉल इट अ 20th century science, and the 20th century is very important for many reasons. One of the reasons is that quantum physics was invented in 20th century. So we will begin with that story. Another aspect of this talk is it can be stopped anywhere. So I have no really material to complete. When the chair says 10 minutes are left, we'll kind of roughly begin winding up. You can interject in between. आप कुछ भी पूछना चाहते हैं, आप बीच में रोक के भी पूछ सकते हैं, क्योंकि उस समय जो आपके दिमाग में आ रहा है, उसके साथ जो एक एक्सचेंज होता है, जो वार्तालाप होता है, उससे बात क्लियर होती है. और इसलिए आप जो भी पूछना चाहें बीच में भी पूछ सकते हैं. लेकिन अगर आपको लगता है कि लेक्चर के बाद आपको सवाल पूछने हैं तो उस समय हम काफी समय रखेंगे बातचीत के लिए. I have divided the quantum revolutions into 3 parts. So I call the first quantum revolution, which took place from 1900 to roughly 1922. And this is a very important period of physics, because if you look at physics as a subject, it was a very well developed subject in 19th century. Why? Because we had the seminal work of Galileo, Newton, which had unfolded 200 years earlier. We had thermodynamics, engines, all that had already been developed. And in 19th century, the great physics which happened was the electromagnetic theory, which Maxwell put together towards the end of 19th century through this beautiful formulation which we call electricity and magnetism. And even now, we all learn that even up to MSc, we learn a lot of physics which is 19th century physics. even in the MSc Physics programs. So physicists used to think that they have really come very close to understanding the entire world. And to mark that, Lord Kelvin gave a lecture in which he said end of physics. He pointed out a few issues which were left in physics, and his point was very soon we will know everything about the world and physics would be a complete science. But as you now know, in 21st century, that statement was far from true. We have done so much after Lord Kelvin, but still we are not really close to understanding everything about the world. And maybe we have changed our point of view, that we have realized now that there are too many things in the world and understanding everything is a very big challenge. However, the backdrop at that time is that physicists are thinking that they are very close to solving all the problems and understanding the world completely. Now when Lord Kelvin is saying this in a very important lecture that he gave, physicists don't believe physicists. So while Lord Kelvin is doing this, there are other physicists doing things in their laboratory, trying to turn around phenomena, or they are looking at, if I do this, what happens, this I do, what happens. So they are doing experiments to explore nature. So that's extremely important, because at the end of the day, science is about developing and understanding about nature. And therefore you have to go and explore nature. Science doesn't really come out of a human mind as an abstract thought, it is developed in the laboratories. So while the all open questions are being considered to getting closed, you see that new experiments are being done, and that is the time in the beginning of 20th century. So simple things like, what if you heat something, what kind of light should come out of it. Now as you know, heat is random energy. So random energy means things are moving in a Brownian motion, some direction, this, that, so on. And out of these thermal processes, light is being emitted. And then, if there is a random thermal process behind heating of atoms and molecules, then light which comes out should also be of that nature. However, you heat neon, you get those crimson lines, you heat sodium, you get that sodium doublet. So the light which comes out of materials when you heat them is very characteristic of those materials. And from those colors, actually, if you have done chemistry, there are these flame tests. Now I know in schools, labs have become weak. In my time, in 11th and 12th, we used to do flame test. So in the flame test, from the color of the flame, you can identify the element. Every element has a characteristic color. However, flame is random thermal energy. How such random thermal energy gets converted into precise spectral lines? 19th century physics cannot tell you. Why is it that when you look at thermal radiation, say radiation coming out of sun, why is it that certain frequencies have certain intensity, certain other frequencies have certain other intensity, the black body radiation curve? Why is it like that? Classical physics of 19th century cannot tell you. Why a photoelectric effect has a threshold in the beginning and then suddenly you begin to see a current, and why is that current dependent on the frequencies in a certain way and on the intensity in another way? 19th century physics cannot tell you. Now if you look around, 19th century physics cannot tell you why some things are semiconductors, others are conductor, others are insulator, why some things are solid, others are liquids, why mercury is a liquid, it's a metal, where all other metals are solids. So you try to ask almost any question about the nature. Now the answer will be that 19th century physics is not good enough to answer those. Whereas at the end of 19th century, people had exactly opposite view, and that tells you there is another principle in science: more you look, more you see. Even the question you are asking are conditioned by the previous knowledge, and you are constrained by that. Once you open up your mind, you can always ask questions which will not be answered by the existing knowledge, and that's what happened. So a plethora of experiments were produced in the beginning of 20th century, which questioned the classical physics. Classical physics, I mean, is Newtonian mechanics, dynamics, and thermodynamics, and also relativity. Relativity is very much a classical physics. So none of these could explain, and slowly people realized that not just they could not explain, the classical physics were inadequate and a science had been invented, and that new science first came as early quantum theory, where people started talking about discrete energy levels in atoms and such concepts, which now you have been exposed to some extent in school also. Now there are some unique things about quantum physics, as we will see a little bit of it. As I told you, I'll give you a glimpse, that it is not just another way to calculate things, it changes the way we think about the world. The picture of the world which emerges in your mind of the quantum world is very different from the classical world, and classical world is roughly same as our intuitive world. So that is a fundamental change in our point of view. Therefore, quantum physics change is connected with the philosophy also. The way we extract information from quantum objects is philosophically and practically very different from the classical world and so on. Another important thing, which in some sense I would say is the beginning of modern science, is that quantum physics is not one person's creation. It is not, Einstein's relativity. 4 or 5 people are involved, and then we say Maxwell's theory of electromagnetism. We say Newtonian mechanics. It's not like that. There are so many people from, Bohr, Einstein, Schrödinger, Heisenberg, Dirac, Pauli. So many people are involved in constructing this new platform, or I would say framework, to understand nature. So therefore, these years were very exciting when the quantum explanations led to a framework called quantum understanding of the world. Then comes the second revolution. The second revolution, well, I put these dates, I'm not a historian of science, I put these dates from a physics point of view. So second phase was that now that we had the quantum framework, we should use it to understand the world. So applications of quantum mechanics to atoms, molecules, nuclei, particles, solids, neutron stars, you name it. And on all scales, objects which are very small inside a proton, quarks are inside the proton, they also are understood using quantum framework. I'm saying quantum framework because we sometimes say quantum mechanics, other time we say quantum field theory. All these come into something called a quantum framework. So quantum framework can be used to understand, on the one hand, quarks, on the other hand, objects like neutron stars. On the one hand, you are wanting to see how a particular molecule reacts with another molecule. All chemical reactions at the end of the day are quantum processes. Classical physics doesn't even have these orbitals and so on and so forth. So all chemical reactions at the end of the day have quantum explanations on the one hand. On the other hand, if a large current is flowing, current could be 1000 amperes, it could be even 10,000 amperes, such a large current flowing through a superconducting wire, that also is explained using quantum framework. To cut the short story long, this period or the second revolution was to discover and explain very large amount of phenomena in nature using the quantum framework. Now, in this period, of course, quantum framework also has some open problems. Quantum framework itself is not fully understood. We will see that. And I will tell you that trying to understand the quantum framework better is leading to new things now. But this period, people were so excited about the quantum framework and its success that almost most of the 20th century, we have been busy trying to see how quantum framework can tell us this, explain this, all that and so on. And in terms of technologies, if you see, most modern technologies have come out of this. The most important being semiconductors, for example, out of which all computers and these things have come out. Even lasers, at the end of the day, the laser sources have to be explained using quantum mechanics and so on. Now, the third quantum revolution begins in 1984, and that is a very different kind of revolution, because now we have done so much, we have understood so much about the world using quantum framework that we can relax and see what other implications quantum framework may have. And two people, Barrett and Brassard, at Institute of Science, Bangalore, in a conference in electrical engineering department, announced a protocol called BB84 protocol, where they showed that secure communication between two people can be carried out only using quantum framework. That was a fundamental work which got announced in an audience where nobody knew quantum mechanics, so did not get that much attention at that time. Now, of course, we say that the birth of quantum communication as a subject is in the BB84 protocol, which was announced by Bennett and Brassard in 1984. In that period, it's also, people had started asking questions about if you do a computation, how much energy. The previous talk was about energy. What are the energy requirements of computation? Or are there fundamental limits on how much energy a computer must need to do a certain computation? Such questions are being asked, and since word is quantum at the end, it was Feynman who built a model. I mean, I hope you have heard the name of Feynman. He was one of the most decorated and brilliant physicists of 20th century. He built a model, a toy model, which we now call a quantum computer, which he built to show that there is no lower threshold. There is no lower amount of, there is no energy that you have to spend in doing computation. Computations can be done reversibly, and these reversible computations, in principle, if you do them slowly enough, can be done without consuming any energy. Of course, they will, if you don't consume energy, they will take infinite time. If you want to do them in finite time, you have to bring in certain amount of speed that will need energy, but there is no minimum quantum which is needed anyway. So that's how people started thinking that maybe we could use quantum framework to build new kind of computers. It was in late 80s that David Deutsch came up with another toy model, and later on in 1996, Peter Shor came up with the factorization algorithm, which revolutionized the field and showed that in case we are able to build a quantum computer, which is a computer based on the Feynman's toy idea of doing computation using quantum framework, you could actually solve problems which cannot be solved on a regular computer. And therefore, the third quantum revolution is all about trying to build new technologies, quantum computers and quantum communication devices, which are fundamentally different from the existing devices and which will revolutionize the way we process information. So this is the third quantum revolution. I know I have limited time, so I will not show you that slide, but in 20th century, I can put things here. Another revolution happened in 20th century, which is not quantum revolution, which is the revolution of computing revolution. There were no computing devices in 19th century. Whole idea that machines can calculate and compute is a 20th century idea. And that also has developed along with quantum mechanics parallelly, but not really at a conceptual level talking to quantum framework up to 1980s. In 1980s, the two grand frameworks, the framework of quantum mechanics or quantum physics, and another framework which we call Church-Turing framework of computer science, they kind of come together and you have a quantum information processing framework, which is a much broader way to think about or conceptualize computations and calculations. And the third quantum revolution is all about exploring this and building these new devices, and this is a very exciting time for this field. Now, let me tell you that at the turn of the century, from 20th century to 21st century, if you look at the years between say 1998 and 2002 and read about people's articles on quantum information, most people have said this is very nice, it was a toy idea, it is a good theoretical construction, but it is very difficult, nobody will be able to build quantum devices. Even people like Landau wrote an article saying that quantum devices will never be built, they are too difficult to build. But within 10 years, between 2000 and 2010, the situation changed so much that in 2010 people said in about 15 years, 50 years, these will be built. And by 2020, we even have the prototypes. So the development in the field has happened very fast, and things which were thought to be 22nd century things. See, when something is 22nd century, it's important, we should do it. But it's clear it is not going to happen in my lifetime or your lifetime. Even 50 years for me is too far away. But it's exciting because it is not far away for you. But when something becomes accessible and the progress becomes fast, that it comes to 10, 20, 30 year scale, then you begin to see that it's actually going to happen in your own lifetime, within the professional lifetimes of your students and so on and so forth. And that's where this field is now. So the situation and the status of the field has transformed drastically in the past 15 years. And now everyone is talking about building devices, and prototype devices are already available. So this is what I wanted to say about 3 phases of quantum revolution, and we being in a very exciting phase, which is the 3rd phase. And I am primarily going to talk about 3rd phase because the origin of 3rd phase is in the counterintuitive ways quantum mechanics looks at the world. It is not in the practical nitty-gritties of quantum mechanics. It is the philosophy of quantum mechanics which is fueling the new technologies. So let's see how quantum world is different from the classical world. Classical world is predominantly continuous. So things are continuous. If you are measuring wavelengths, you imagine that at every wavelength there will be light. If you are measuring mass, you will feel that every mass there should be some particle of that mass. This is the classical thinking. If you are thinking of energy, you think of continuous energy and so on. Whereas quantum world is discrete. So things come as packets, whether it is a photon, which is the packet of energy, whether it is the energy gap between 2 levels of an atom, or it is the electron mass. These are things which are quantized quantums and packets. The world quantum world is discrete and not really continuous. Of course, space and time are considered continuous in the quantum world also, but people are also questioning that because nature of space-time is connected with the nature of gravity, and a full quantum understanding of those things are still being researched. Now, there is a very interesting feature in the quantum world, and this needs to be understood because this is one of the most bizarre features that says that if a situation A is possible, you can conceive of situation B. Situation A being, for example, that you are attending my lecture here today. But then at 12 o'clock today on 16th November, you could have been in your class and attending your class also. So that is also conceivable possible. So there is a possibility you are here, there is a possibility you are there. In the quantum world, a superposition of these two can also exist, where you are there in both the classrooms. Of course, you are not quantum particles, and I am not alluding to the fact that this can happen to you, but this can happen to quantum particles. For example, when you say that a single electron is in the p orbital, where is the electron in the p orbital? It is everywhere in the p orbital. It's a single electron, but it is present in the entire p orbital. And you don't doubt the existence of a p orbital or an s orbital, or for that matter for a d and f orbital which have these complicated structures. So a single object, if it can be conceived to be in 2 different situations, then in the quantum world those different situations can also be thought about to be superposed. We call it superposition principle. So they can thought to be superposed, which means it is there together. This looks bizarre, but this is true. So many experiments have been done to verify this, and the quantum world hinges upon this principle. Now the third is also a very interesting feature of quantum framework. Let me explain this in some detail. That's why I said that me finishing my 20 slides is not important. Once the time becomes 50 minutes, we'll start a discussion. See, what is probability in the classical world or our normal world? Probability represents lack of knowledge. So if I don't know something, I assign a probability. For example, if you have a molecule which emits IR radiation, little bit. I have a single molecule and I hold it in my hand. You can't see it. It's in my hand. These days you have these tweezers which can hold single molecule. Then I release it. And after some time I ask you where it is. Since you are all science students, you will say it was being hit by various other molecules in the air. So it has now gone around in the room. It has almost equal probability to be found anywhere in the room, quoting the Brownian motion and the argument that if you open a scent bottle, scent smell spreads all over the room, the molecules are transported, the single molecule is now, since the room is closed, it can't go out, so it has equal probability to be found in this room after some time. Right? This is the correct scientific logic. However, if any of you have as a lens through which IR can be seen, that person will see and say, oh, that molecule, it is here or it is here. It's a single molecule, it occupies a single position. We have no doubt in our mind that a molecule can occupy more than one position. We are assigning probability to represent lack of knowledge. This is how we assign probabilities in the classical world. In the quantum world, it is not like that. Probabilities are fundamental. How are they fundamental? I give you two nuclei of a radioactive material. So those two nuclei of the radioactive material, let's assume that these flowers. So all these flowers are radioactive. These pink flowers. So there are these, 1, 2, 3, 4 pink flowers in this row are radioactive. And whatever material this is, this has half-life of 5 minutes. Alright? So quantum mechanics tells me, if I do a proper calculation, that after 5 minutes, half the pink flowers would have decayed. Decayed means they will decay to something else, some other material because of radioactivity. Now this is a precise calculation, half of them will decay if the number is large. But which half will decay? I take these two pink flowers. Will this decay first or this decay first? I would say no. The probability is equal. It is in 5 minutes probability for anyone to decay is half. But quantum mechanics doesn't tell me which one will decay when. And quantum framework says that actually nobody can tell you. And there is inherent probability in nature. Our world is probabilistic. It is not deterministic. Which is a feature which is not there in classical physics. In classical physics, indeterminism or probability is introduced just as a matter of convenience or to express lack of knowledge. So this is a fundamental departure that probability is to be considered fundamental. We will see how this has disturbed stalwart physicists like Einstein, who did not want to agree with this aspect of quantum mechanics. Space in which we do quantum mechanics. So so quantum mechanics is a meta framework. By meta framework, by mean is that the calculations which you do to understand the quantum world are done in a complex linear vector space of some dimension. It is not the three-dimensional regular space, and we don't use vectors and particles as not like that. You have to map the world to a theoretical space which doesn't look like the world. You do calculations there and then you bring them back and compare them with laboratory observations. So that's another aspect. I can go on and on, but idea was to give you a glimpse into the framework and not really begin teaching you the entire framework. Now, three features of quantum mechanics: the superposition, which is where exclusive becomes non-exclusive, which means that two things, in classical world we think if I am here I am not there, but in the quantum world I can be in both the places. Then measurement. Now measurement is another very important aspect of quantum framework. See, in the classical framework, we don't even teach measurement theory. There is nothing called classical measurement theory because measurement is trivial. You just go and find out, measure, come back. So it's very passive. There is a particle somewhere, you go and find out where it is, you come back and note down. You never worry about you interacting with the particle, learning about its position. You don't do that. But in the quantum world, what happens is the very act of measurement disturbs the system. So when you make the measurement, you learn something, but the system gets changed. So my favorite analogy is that if there's a quantum book in the library, you issue and read. You learn something, you put it back. Next student goes and reads. The book will be little different. A book which has been read by someone else will now be a slightly different book compared to the one which you are reading, because it is not the fresh book. The book has been read by someone. So any measurement on a quantum system leaves a mark on the system. And once you take this forward, what really happens is, if you don't make too many measurements, you actually destroy the information. So there is it's called quantum law of diminishing returns. You try to ask too many questions to a quantum system, it gives up and starts giving you completely random answers. Which means the quantum world is very delicate. You have to question little bit. And question in a way that you disturb little bit, learn something and be happy with that. Ask too many things, things will get disturbed. Let me give you another example. And let me use one of you as volunteers. Let's see. So row 3. आप बताइए आपका क्या नाम है? 1, 2, 3. Yes. Yeah. आप yeah. खड़े होइए. What is your name? Okay. Rajaswi. What is your class? 12th. Which subject have you taken? Science. What is your name?
Rajasri Panda.
You see, you are a regular classical answering machine. So I ask you name, then I ask you class, then I ask you subject, I ask you name again. And your name did not change. If you are a quantum particle, since I ask so many questions, when I go back and ask the first question, the answer can change. So if you are an electron, for example, I ensured you are here. Then I measured your energy. Then I measured your momentum. Then I measured your angular momentum. Then I go back and ask you where you are, and I find you are not here. You are actually here. Because in this process of asking all these questions, you have decided to change your position. So the quantum world, sit down. So the logic has to be modified. You cannot depend on this logic that I will keep on asking and keep on getting more information. Your previously collected information may actually become invalid. Alright. And third is quantum entanglement, which most of the rest of the discussion is going to involve it. That is a very, very, very interesting feature of quantum mechanics, that okay, in one line it is like this, that you know what is a correlation? Correlation is two things are connected. If I measure about one, I can tell you about the other. For example, very close friends normally remain together. So if I am taking attendance and I know these two students are very close friends, if one is present, other is present, I know, because they missed the class together. So there is a correlation between their attendance. So this is correlation between objects. Correlations can be defined in mathematical ways and all that and so on. But this is the basic idea. Learning about one gives me information, some information, may not be complete information, some information about the other. Now, correlations require interactions. After all, friends talk to each other, that's how they find out, I am not going to the class, you also don't come, we will bunk the class, don't tell the parents, go to the film. Now this requires interaction to organize this activity that we are bunking the class. So you need to interact. In the classical world, this interaction has to be maintained to keep the correlation strong. In the quantum world, if you have interacted in the past, that can keep you correlated in future as if you are classically interacting, quantumically. But there are quantum correlations which if you want to explain classically, then you will have to imagine that you are continuously interacting. But you are not interacting, you had interacted in the past and never met after that. So the student example would work like this. You were friends in 11th and you were very good friends. You got correlated. Now you are not friends, you went to two different schools. So you are studying in one school, other one's parents have now in the 12th class put the other student in another school. However, when you bunk the class and go for the film, it always is the same film and you happen to be in the same cinema hall. But you are not communicating, you don't even have each other's phone numbers because you were friends earlier. So the past interactions can lead to very, very strong, unexplainable correlations in future. That's another feature of quantum physics. So, I think I've excited your imagination enough, and now I should tell you what kind of things have been happening around these features of quantum mechanics. But since I ventured into telling you a little about history of science and history of quantum mechanics, that's why you are not quantum particles. I am giving analogies. These things are not applicable to you. They are applicable to quantum particles. So these were just analogies. I think you are big enough to understand that I was giving examples and not actualities. I will come back to that. What if can quantum mechanics become applicable to large objects? This is a very active area of research today. Okay, and people have shown that buckyballs, these soot particles which have large number of molecules can have these properties. Now people have even gone beyond that. People are talking about a bacteria to be present in two different places. So we are not very far, Professor, from the situation where we might, think about quantum superpositions of large objects. Anyway, so physicists did not pay too much attention to these aspects because they were worried about this. So it took time to understand the importance of these things. Only a small group of physicists were worried about these features, their philosophical implications and so on. So the most worried person about this was Einstein. Einstein, though he was the person who participated in the early parts of quantum mechanics, because you know that photoelectric effect explanation came from Einstein. But when the quantum framework was put together, Einstein was very unhappy. He did not like the world which is probabilistic and which doesn't have determinism and all that and so on. So he started looking at quantum mechanics very critically. And he wrote this very famous paper in 1935 along with Boris Podolsky and Rosen, which is motivated by his earlier statement that God does not play dice with the universe. He did not want probabilistic universe. So his thing was quantum mechanics, okay, not wrong, but must be incomplete, at least. So in this paper he argues that quantum mechanics is incomplete. And therefore we must try to build completer theories better than quantum mechanics, which should not have probabilities. Alright? So this was 1935. Some people even got motivated to work on such theories, but as I told you, most physicists were busy applying quantum mechanics to nature and not really trying to see to get, we have got such a good framework, so why is Einstein talking about going further? Let's first explore this. So not too many people worried about it, but some people did worry about it. And that I am not going to tell you because this is the whole story of Einstein's paper. Immediately Bohr wrote back a reply with the same title. The title of the paper is that is quantum mechanics description of reality complete? Question mark. That is Einstein's paper in Physical Review 1935, famous paper. It's available in openly actually. It's now open access. You can download in 2 minutes on your phone. Then Niels Bohr writes a reply with the same title. Now, Bohr's reply is something which when an undergraduate student comes to me to do a project, I give him these two papers and normally says, tell me what Bohr is trying to tell Einstein. Very difficult to find out what Bohr is saying. So people these two papers were written and it's very difficult to figure out Bohr's response. Anyway, so this is how it was. Then came John Bell, that is 1964, after 29 years of Einstein's paper, John Bell comes and does a fundamental piece of work which is called Bell's theorem. Now you see, theorems are there in mathematics. In physics there are no theorems. Why there are no theorems in physics? Because all physics is wrong. Why all physics is wrong? Because next generation physicists are going to find some fault and do better physics. See, Newton's laws, Einstein came and said they are valid for small velocities. They are not valid when velocity is close to velocity of light. They are not wrong, but they have limitations. So you can't prove Newton's laws. Similarly, classical physics was such a strong physics, quantum mechanics says classical physics is okay, but it doesn't work for very small objects. It doesn't work for very small energies. It doesn't work for certain situations. So scientists are very humble. We don't prove theorems, we improve the previous science and do better. But in mathematics you have theorems. Of course theorems have assumptions. So this is a theorem, it's a mathematical result which has implications for physics. Not that theorems are not important, mathematical theorems are used in science. So theorems always have assumptions. So theorem means you say if A, B, C is given, X is right or X is wrong. That can be proved. But you see, it depends on A, B, C being given. But if A, B, C is not given, the theorem is not valid. So theorems have this structure. I think some mathematician will talk to you during this camp and you can ask further. Now what did Bell prove? Bell said, all right, let us assume Einstein is right and such a theory exists which does better than quantum mechanics. Very good. He didn't say which theory, he said let's assume such a theory exists. Then he does mathematical analysis, logical analysis, and then he shows that such a theory may be right or wrong, he doesn't know, but it cannot be consistent with quantum mechanics. Now that is now very interesting. So what Bell is saying is, alright, quantum framework works for so many things. Einstein is saying quantum framework is incomplete. Alright, some quantum disturbance. So what Bell is saying is, quantum framework is working very well, okay. Einstein has a doubt that we should do better than quantum mechanics. Let's assume we have done better than quantum mechanics. Is it really better? If we assume that we have built such a theory, it cannot just be better than quantum mechanics, it will contradict quantum mechanics. That means we can test Einstein's idea. Because nature will give one kind of answers, contradict means experimentally contradict. So therefore it opened up the whole idea which was very theoretical, that about the incompleteness of quantum mechanics and nature not having probabilities, was brought to the domain of experimental physics, where experiments can be set up to test whether quantum mechanics is right or possible theories based on Einstein's idea, they are right. Alright, how much time do I have? Very good, I think I am doing very well on time. Now the stage is set. When the stage is set, things can be done quickly. So John Clauser, who got the Nobel Prize in Physics in 22, was the first guy who ventured to do experiments to test this, whether quantum mechanics is right or Einstein is right. And he did preliminary experiments which showed that quantum mechanics is right. However, his experiments were not perfect, they had loopholes, and people could argue that maybe the experiments are not right. You see, if you do an experiment which concludes something, there are three possibilities. Of course, one possibility was quantum mechanics is right, other possibilities is Einstein is right. But there is a third possibility is this experiment is wrong, so therefore the conclusion is not valid. So lots of people put a lot of doubt on these experiments which were done in 1972. And I must also tell you this, that this gentleman was a young man at that time, and now he has written, after the Nobel Prize he gave his speech and he has written articles. The physicists didn't like the idea that he was working on these things, so he was not given tenure track. He was kicked out of academia. He never became a professor. He set up a company and went to industry. So he says that, well, I am connected back to physics community formally after I have got my Nobel Prize. Because dominant laboratory physicists thought that there is no need to do such experiments. So this also tells you that when you have something in mind, it's important to explore that. It should not matter that much that what other people are saying. Then came, well, this is his experiment, let me not get into the details. If the questions I will. So second person who tried refining the experiments of Clauser was Alan Aspect. Alan Aspect, what happened? So Alan Aspect was a French physicist and is a French physicist, he is very much alive. He did these experiments in the 1980s and he refined Clauser's experiments. And part of the refinement, which was technologically very, very challenging, was the following, which you will be able to understand, so I will tell you. So I told you that these past correlations, 11th class friendship should last even if you're not meeting in 12th class. Now for that, you have to be put, to test this, you have to be put in different schools. You have to be not been able to make phone calls. What if you have a secret phone? So the two situations in Aspe's laboratory. What happened? This has stopped working. Well, maybe something has gone wrong. Anyway, can you? Yeah. No. You just maybe pull this out and put it back, or pull this out. No. Okay. No. Where is this connected with? So just put it back. Okay. Anyway, yeah, good. So what he had to do was that these two friends, these two photons, what are you going to measure? Which cinema hall you are going to send them? That should be decided after they have left home, so that they cannot secretly talk from the home landline or send a chit or whatever. But this had to be done very, very quickly because light travels very fast. It is 3 lakh kilometers in 1 second. So you can see what kind of technology Aspe invented to do his experiments. But he improved the Clauser experiments drastically, and his conclusion also was that Einstein's viewpoint is wrong and quantum mechanics is right. But there's a very interesting story connected with these experiments. Say, Aspe went and met Bell at Geneva, CERN, and said that I want to do these experiments. Since Clauser's story was well known in the physics community, Bell asked him, do you have a job, permanent job, or are you looking for a job? If you have a job, do these experiments. If you don't have a job, permanent job, don't do it, because you may not get a job if you engage yourself with such experiments. So this also he has written in his memoirs about his engagement with these experiments. So this was a further refinement he did, and people started now more strongly believing that quantum mechanics is right and Einsteinian thinking is wrong. Then came Anton Zeilinger, who also shares the 22 Nobel Prize. He refined these experiments further and brought in many more aspects of these quantum correlations, which are not just the Bell kind, which can be very, very different kind of situations where these quantum aspects of entanglement, superposition play out, and you can show that Einsteinian thinking cannot work in nature. Not just that it is not consistent with quantum mechanics, you can construct many more situations in the laboratory where you can show that quantum mechanics is right and this way of non-probabilistic Einsteinian thinking is wrong. So these three gentlemen got Nobel Prize in 1922, and that can tell you that now the community of physicists have recognized their work after so long, and now of course these are considered landmark experiments, the experiments for which Clauser did not find a job, for which Aspe was told by Bell that if you have a job only then you do them. Of course, Zeilinger was already well known before he got into it, because, by the way, Zeilinger has a very interesting Indian connection. Before he became a quantum optics experimentalist, he was a neutron interferometry guy, and he used to work with Dr. Wag and Dr. Rakhecha from BARC. So they had a collaboration going. But suddenly Zeilinger left that field and then became a quantum optics person. That also tells you, in India I see very few people taking such drastic decisions of leaving something and doing something else. So he did that. He never did neutron interferometry again. Became famous, became so famous, and even got a Nobel Prize. So this was not the field in which he worked on originally. By the way, now that I am telling you, Alan Aspe also, he likes India very much. He likes to travel in India. So if you invite him to Bahrampur, he'll come. He likes Puri. I mean, last time he came, he disappeared for a month and traveled in India and so on. So after Nobel Prize, he has not come, but people are thinking of inviting him. Anyway, so this is the story. I am very close now. So all I am trying to now tell you is that these aspects of quantum mechanics which were considered philosophical in nature, which were considered to be the aspects which only a few worry and regular working physicists need not worry about. They are the ones which are making quantum computation possible. Because in quantum computation, you need to use those kind of correlations. And it was Peter Shor who gave this algorithm for factorization of large numbers, which can be done only on a quantum computer, which basically shows for the first time that there is a quantum advantage. This word is being used. If you search on Google quantum advantage, it has a specific definition. So first quantum advantage was shown by Peter Shor in his algorithm, and second quantum advantage was shown by an Indian, Love Grover, who was a BTech from IIT Delhi and was working in Bell Labs, and he wrote a famous paper that database searches have a quantum advantage. And again, very similar story. In Bell Labs, his job was as an engineer, and Bell Lab bosses did not want him to work on quantum ideas. He was not being paid for that. So he was doing this in his off time. So whenever bosses would come, he will close his notebooks. So Grover says that this was a work done completely in his spare time and not as part of his job at Bell Labs, and he became famous for this. Then of course there is cryptography, which is the BB84 I told you, that if you want to set up a secure communication system, answer is that you have to use quantum particles. No classical system can be fully secure. The security of classical crypto systems is algorithmic, which means that the security is based on we not having fast enough computers. It is not fundamental. Whereas if you build quantum crypto devices, which is called quantum cryptography, then you can, this is a quantum crypto device, you can show that this security cannot be broken in principle. Even if you have a quantum computer, it cannot break the secrecy of a quantum crypto device. Well, quantum technologies come in three different guise now. People are talking about quantum communication, which is called quantum key distribution, building secure quantum communication devices. Quantum computers. Now quantum computers are quantum computing machines which have a quantum advantage, which means they can do something which regular computers cannot do. And quantum sensors. Now quantum sensors is a very interesting field. Today I am not going to talk about it, but I will tell you the history of quantum sensors actually goes back to early 80s in the famous paper written by Carlton Caves and Kip Thorne. Kip Thorne is a person who works in gravity, and you know gravity wave detection is a very important field. In India we are building INDIGO, Indian Gravitational Wave Observatory. They by the way have summer programs and all that, and they associate young students. The whole idea is that if you want to really measure quantum gravity waves, you need quantum detectors, and those quantum detectors were proposed in early 1980s, and now people are thinking of building those. There are other very interesting quantum sensors where you take a diamond and put a nitrogen vacancy, a single nitrogen atom inside the diamond structure, and that can be used as a detector for very small magnetic fields. Several groups in India have set up these things, and they are working in this exciting field. So quantum communication, quantum computing, and quantum sensing, this is the revolution, third quantum revolution that is now unfolding, and I hope one of you or some of you will get excited and get involved with that. Let me not tell you about the technologies being used. These are those slides. Now in India, the situation is very exciting. We had Quest, Quantum Enabled Science and Technology Program, which was a 300 crore project, coordinated pan-India project with 4 verticals, and these are the 4 verticals. I happen to coordinate at the national level the first vertical, the vertical 1 of quantum technologies, which is quantum communication with photons. So these 4 verticals were given 300 crores to do things from 19 onwards. These projects are now closing. So Quest is closing after these 3.5 years. And now we are moving into, originally we called it NMQTA. It was called National Mission on Quantum Technologies and Applications. Now it's called National Quantum Mission because people found this name too big. So National Quantum Mission, Government of India is thinking of funding of the tune of 6,000 crores to build quantum technologies in India. So if that happens, we will definitely take up some leadership role in developing quantum technologies. So you may think about looking for contributing to these. You may also think of looking to contribute projects like Indigo, the Indian Gravitational Observatory and so on, whatever catches your fancy. This was just a diagram about Quest Theme 1 to tell you that scientists who are working in quantum technologies are all over the country. So they are not, I am actually closing. So it is not, this is very nice. This is like that early days of quantum mechanics. This is not one man's show. So these PIs which are distributed all over the country are everywhere. I think we have one Quest PI in this institute also. You can find out who it is. Well, he's a mathematician, so he looks at only the theoretical aspects. But I think soon either Berhampur would have someone or the other who looks at experimental aspects of quantum technologies. So this is where we are. Maybe it's a good time to stop and take questions if you have any. Any questions, किसी भी भाषा में आप पूछ सकते हैं, are welcome.
Sir, as you said, if we ask too many questions to quantum particles, then the answers are very bizarre. So how do we even study about quantum particles?
A good point. So don't ask too many questions. Ask a few questions and then build a picture. So don't just say, okay, I will ask all my possible questions. Try to guess other things. Guess means there is something called a quantum state. So by asking questions, you try to guess the quantum state. And if you guess it rightly, then without making measurements, rest of your questions can be answered. So you follow a very different route. You first ask a few questions, make a guess about the quantum state, then use quantum state to answer rest of the question. And then you only see, are things getting contradicted? If things are getting contradicted, you go back and change your guess for the quantum state. So the game is complex.
Why quantum theory is not applicable in daily life, as on the routes we all are quantum particles?
That's, I knew that question will come. That's a very important and interesting and exciting question. And currently it's the topic of very active research. That since we all are made up of quantum particles, why does the description change at some scale? So how does the classical world emerge out of the quantum world? Lot of interesting work is happening. There are at least 15-20 groups in the world who are actively working on this. But very nice thing is that answer is that we don't know yet. So maybe you can participate in answering this question.
My next question is, how quantum theory is correlated with spirituality?
Okay, that's another interesting question, and let me answer it in a different way. This question was asked to John Bell, because he worked in philosophy of quantum mechanics. So he used to go to Krishna consciousness parties and groups and so on, and somebody asked him the same question. He said, well, you know, I do quantum physics, they do something else. I don't understand what they do. They don't understand what I do. I like their music, I like their food, I go. They see a connection, I don't. So I don't see a connection, like John Bell.
Thank you, sir.
But I don't mind going to places where there's good music and good chanting and so on. And good food. This is a documented answer by John Bell.
My formal greetings to you, sir. Excuse me.
Thank you.
So my formal greetings to you. Sir, my question is, you mentioned that every time we take down any observations in quantum, it changes with whenever we go back to that observation. So sir, in future, whenever there would be laid any hypothesis or any other stuffs given by scientists, is there a probability that every time there will be limitations or it may be proved wrong by others in near future?
Well, again, I think I alluded to this, that all science gets updated. Because as they say in computer science, that can you say that this program is correct? To prove the correctness, you have to run the program on all possible infinite inputs. And since that will take infinite time, you can only say probabilistically. So science is a tentative knowledge, and the new generation always asks questions which cannot be answered, and so science keeps developing. So that's why science humbles you, should not make you arrogant. I mean, I spent so much time saying Einstein was wrong, Einstein was wrong. Who am I? But that is where we are today. So this is what science is about. It's not about gurudom, that guru is always correct and somebody is always correct. Einstein doesn't mean that he was not a great scientist. Even the fact that he brought this question in this way to the community that we could prove him wrong is an advancement in science.
Thank you, sir.
Sir, my question is, how do I become a quantum particle? Is there any possibility?
Very interesting. See, what happens is, this is what the question was being asked by the gentleman here. Now, for a large object to behave quantum mechanically, what are the problems? Main problems is environmental interactions. See, we as collections of large number of atoms are continuously interacting with our environment through photons, through collisions, all that and so on. So this takes away the quantumness. So you have to isolate the quantum system from the environment completely, which is a technologically very difficult task called quantum control. If you look at the history of Nobel Prizes in physics, past 10 years, 2 years Nobel Prizes have been given for developing technologies for putting larger objects into quantum states. Alright, so you look for this paper by a scientist called G-San, G-S-A-I-N. He wrote a paper about 15 years ago. What if one to quantum mechanically teleport a human being from one place to another, asking the same question? He tells you what technology we need. So you read that paper, it's a very well-known paper.
Thank you, sir.
There was I don't know. Yeah. Yes. So somebody should, or two people are standing up. So whoever has the mic, yeah.
Can you measure black hole by using quantum theory?
Well, see, black holes are far away and they don't emit any radiation. So you only gather indirect evidence about black holes. So of course, one indirect evidence you get about black holes is that black holes have gravity and they pull. So if there is a part of the universe where you can't see anything and things are getting pulled in that direction, there is a possibility that there is a black hole. But black holes have some quantum properties. There is something called black hole radiation, and that process of black holes radiating a certain kind of light is a quantum process. But you know, doing measurements with black holes is impossible because there are no black holes around us. And of course, if they are around us, that would not be so safe. So there is indirect evidence of existence of black holes. Currently, most of that evidence comes from classical physics. However, if black holes are interacting and producing gravity waves, and those gravity waves are being detected by quantum sensors on Earth, that way quantum mechanics can get involved with measuring signals which are emanated from black holes.
Thank you.
Good afternoon, sir. I wanted to ask you, as we talked about the effect of superposition, it sounds quite unnatural, and also wider mass having a knowledge about it might quite have an adverse effect on the natural conduct of the world. So I wanted to ask you, sir, what do you think? it is important for some treasures of the quantum physics to be kept hidden, or do you personally suggest a wider market?
No, I don't think so. See, what are many things which we call as our human intuition are actually imbibed. I think quantum ideas should be taught to children very early so that they can think about the world with an open mind. As Delbrook says, you should read Delbrook. He talks about where have we got this intuition which we consider is normal human way of understanding. That is basically interacting with the world at the time scale and mass scale and length scale of our size. But now we have technology to see the world at very different scales. This should actually change our worldview and broaden it. I don't see any harm. There are other things which can be harmful, which again some people do not think. But this whole idea that I should try to put certain kind of genes into my children that they become taller or smarter and all that, those are technologies which require your kind of scrutiny much more than expanding people to quantum ideas. Quantum ideas will only open your mind.
Greetings, sir. So my question was, when we measure a quantum particle or take any measurements, you said that they would change. So is there any way to know what is changing, how or when it is changing?
Interesting. You can only measure the amount of change. That change is not deterministic. See, if you could measure the change, then there's not really a change. Then you can say, all right, this happened. That change which occurs is not a deterministic process. It is a random process. So, cannot be tracked. That's why you lose information. See, any change which can be tracked, there is no loss of information.
And also, do quantum particles behave differently for different people or something like that?
Different people means different laboratory experiments, not to do with the people being, their consciousness and all that. If I am looking at the atom at 600 nanometers, it looks different. I look at the atom at, 500 nanometers, it looks different. At femtoseconds, atoms move differently. At attoseconds, this year's Physics Nobel Prize, you can even see an electron move little bit inside. So, yeah, for different laboratory observers, the world looks different, but not for different human beings.
Thank you, sir.
A very good afternoon, sir.
Wherever the organizers want to stop.
सर मेरा क्वेश्चन है कि आपने हम क्वांटम वर्ल्ड या क्वांटम फिजिक्स को अगर किसी भी साइंटिफिकली एक या दो टर्म्स में डिस्क्राइब करना चाहें
कहाँ से आ रहा है क्वेश्चन? I can't out there.
A very good afternoon, sir.
They have put light in my eyes that I can't see you. Yeah, come.
सर अगर हम क्वांटम फिजिक्स को या क्वांटम वर्ल्ड को साइंटिफिकली किसी एक या दो टर्म्स में डिस्क्राइब करना चाहें तो वो कैसे हो सकता है?
मैंने कोशिश की आपके सामने. It is probabilistic. It has superposition of classical possibilities. It has correlations where past interactions are not forgotten. But there are so many other things. And the quantum framework, the calculations are done in a space which is very different from the physical space, which is a complex linear vector space. These are some of the aspects which I exposed to you, but it's a glimpse. At the end, you have to do two courses, Quantum Mechanics 1 and Quantum Mechanics 2, and then you will know the quantum framework.
Thank you, sir.
Thank you very much.
As they say, that listening to music, you don't become a musician. You have to sit and practice those notes.
Okay, thanks very much. Actually, we would like to break for lunch so that we ensure that everyone is well fed. And for the questions, I would suggest that you please ask in the tea break during the lunch time. And also our volunteers who you see, they are actually research scholars. So you can ask them also and they would be excited to answer. We would be excited to answer. So please keep asking questions. That's why this session is here. So I would encourage you all to please do that. And with that, we would like to thank Professor.
And then again he said yes. So thank you for saying yes.
We have the collar mic. Lapel mic.
ମୁଁ ସମସ୍ତଙ୍କୁ ସ୍ୱାଗତ ଜଣାଉଛି। Good afternoon. Thank you, Professor Ganguly, for the very generous introduction, mostly accurate, not completely. You gave me too many awards, so that's what I wanted to correct. And I'm delighted to be here with the students group. Before I begin, I would also like to thank my students, Gaurav, Nandita, Simpa and Arindam, for preparing many of the materials that I have brought with me. I would also like to thank Dr. Palani Raja Subramaniam of Merck Sigma Aldrich, who have supplied some of the more expensive chemicals, which I would not have otherwise brought here. And then ISER Berhampur provided a lot of support, starting with Professor Rahul Sharma and other colleagues in the faculty side, and staff volunteers, Dr. Balaram Mahapatra and his team. And last but not the least, my group of student volunteers. Please come here. I may or may not have all the names, but I would really like to personally thank all of you. You can also come, both of you, for giving the support which is really needed for doing the experiments that I'm going to show you. Thank you very much. You can probably split yourself to both sides, and I may need your help from time to time. Thank you very much. One of the things that I would like to begin with before even the title is that it's very, at your age, you are mostly studying and answering questions in the tests, okay? And most of the time picking one correct answer out of 4 answers, right? Basically identifying 3 wrong answers. All right. It is important that you ask questions. And I'm very happy to see that in the previous 2 talks, many questions were asked. Because it is only through asking questions that you really learn the subject better. If you don't believe me, this gentleman said, you remember your sort of elementary school days when you come home from school, and whoever is at home, maybe your mother, if she is not working, maybe your grandparents, they would typically ask you, what did you study today? Or what did you do? So this gentleman says, not my mother. My mother would always ask me, did you ask a good question today? And then he goes on to say, that difference, asking good questions, made him become a scientist. And who is he? His name is I. Rabi. Okay, but as I said, every experiment comes with a question. And this is a question which is very important question. How much liquid water will be formed by condensing the steam from the 2.2 liter balloon? Imagine that each balloon was 2.2 liter. So how much liquid water did we make from 4 balloons? Would it address Bangalore's water problem? Okay, all right. Next experiment. I think you have some job to do. Yeah, open this. Chemistry often looks like magic. Do volunteers. Or gloves are chashma ready. Okay, yeah, one second. Let them come. Okay, chemistry often looks like magic. Yeah, come here. You hold it with your, this you can remove. Left hand at the top, hold it with your right hand at the top. This you can remove. Okay. Make sure. Yeah, hold it high. And can we have the lights on, please? These 2 lights. Come a little bit forward. Okay. If I were a magician, I would say nothing is written here. Yeah, you can do that. Spray from the left side. Let's see what happens here. Little bit, come closer. Okay? You see something magical happen? So one spray and 2 different colors. Okay? The spray is a brownish liquid and 2 different colors. Clearly these 2 have been written with 2 different chemicals. So there are 3 chemicals involved, 1, 2 and 3. Any answer? No? Yes? No? I can give you a partial answer. The first one, the liquid that I sprayed or he sprayed was ferric chloride. Okay? Alright, thank you. You both can go and we won't need you again, so you can remove the gloves. See, the important thing about it is that they were both wearing gloves, they were both wearing safety goggles. So it's very important that you protect your eyes and your body whenever you are doing a chemical experiment. This is ferric chloride, pretty harmless. This is paper, dry paper. This is also harmless, but it is important to take the precautions. And you also know that, yeah, you take care of that. You also know that, in case something goes wrong here, where the exits are. Right? Do you know where the exits are? There are 2 in the front, 2 in the rear. Okay, I am announcing like a flight crew. Okay. Let's move forward. Now lights off, please. I may have to ask you repeatedly for switching lights back and forth. So this is the chemistry that we saw just now. The letters which turned blue were written with ferrocyanide, which produces Prussian blue, whereas the ones which turn red were written with thiocyanate, okay, and that with ferric chloride gives you a complex and produces a red color. You can even think of creating 3 different colors if you study chemistry a little bit more. Those who are in the corner, maybe you can shift to that side because you may not be able to see this one very clearly. Okay, you might have heard about optical activity. How many of you have heard about it? Okay, quite a few. Optical activity is a property of molecules which rotate the plane of polarized light. Okay, and optically active molecules are those like our right and left hands, which are mirror images, but they do not superimpose. So they are called chiral. Is there any pure chiral substance in your home? Pure chiral substance, 100% pure. Chiral substance, only one enantiomer. Water is not chiral. Glucose. Well, not every household has glucose, but every household will have sucrose. Okay, so sometimes you read about it in books. For example, these are molecules of a mirror images of a molecule called limonene or limonene. Okay, the one shown on the left comes from orange. If you take an orange peel, the skin of the orange, that has R-limonene. That smells like orange. S-limonene smells like pine. Whereas a similar molecule is called carvone. That smells like, this one smells like pudina. This one smells like the small jeera, shah jeera, that is used in biryani. Okay, so sometimes in textbooks these are the examples that are shown, but you really do not know whether what you read is what really happens in life. So I don't think that for such molecules seeing is believing, but smelling is believing. So I brought samples of R carvone and S carvone, and he will pass it on to you. You can smell R from your right hand, S from your left hand, and compare the smell. So this will be passed on, and this can go in the background. Okay, that's a background experiment that will be done. I will not come back to this slide again. Okay, so you can smell it and pass it on to the next person. But one should smell like purina, one should smell like jeera. All right. Did any of you notice that I am wearing a tie in this hot weather? Why? This is a periodic table tie. Right? I have got the entire periodic table here just so that I don't forget some of the elements. All right. Jokes apart, periodic table is one of the most important tables in chemistry, not this one. And as you know that Mendeleev came up with the present form of periodic table in 1869. That's why in 2019 we had a celebration of 150 years of Mendeleev's periodic table. There is another important periodic table that was launched by IUPAC that was mentioned by Professor Ganguly in 2016, and that is called isotopesmatter.org. This periodic table not only lists all the elements, but also talks a lot about the isotopes. All of you know about isotopes? This periodic table website, if you go to, it will tell you what are isotopes, why they are important, and how you can understand chemistry, biology, geology, and whatnot by isotopic measurements. I will not go into that. What is the simplest isotopically substituted compound you have heard about? Hydrogen. What is the isotope called? And what is the most common compound made from deuterium? D2O. Right, correct answer. But then many of you answered it correctly, so no chocolate, sorry. Okay, now D2O has this properties. The D2O density is 1.1, H2O is 0.998, close to 1. So that's why D2O is also called heavy water. Excellent. Now, can you think of a simple experiment by which, lights on please, I can show with a small quantity of D2O, like 3 ml, that it is indeed heavier than H2O. What experiment do you think I can do so that everybody in this hall can see indeed D2O is heavier than H2O? If I weigh it here, even the front row people will not be able to understand. I can weigh 3 ml of H2O, that will be 3 grams. I can weigh 3 ml of D2O, that will weigh 3.3 grams. But only I will be able to see the balance. None of you would be able to do that. Can you think of something else? Flowing it. Blowing it. No, it is liquid. H2 and D2 have very similar properties except melting point and boiling point. Okay. Yeah. Yeah, I think you got the point right. Ice floats on water. More precisely, H2O ice floats on H2O. D2O ice will float on D2O for similar reason. What about D2O ice in H2O? Yes, let's try that experiment. I need a glass and some ice chips, fresh ice. You have a beaker? Get me the beaker. Yeah, get me the beaker. Just give me 1 minute to set up the experiment. Yeah. And give me my pink box from there. And I'm going to add some RO purified water here. I will tell you why I'm using H2O. I'm using ice cold water. Right. Thank you so much. And here are samples of H2O and D2O that my students have prepared, but these are packed in a different way. These are packed in little syringes, and my students always play this trick with me. They have 2 different colors, but I don't know what is the color code. One is orange. All of you can see this. This is exactly 3 ml in a cut 5 ml syringe, and the other one is green. But I don't know which one is which. But by doing the experiment that I'm going to show you, we can figure out which one is which. Okay. Alright. So here are the samples, and I'm going to put ice cold water here. Do you know why I'm putting ice cold water? And that is because D2O melts at close to 4 degrees. H2O will melt at 0 degrees. So what we will find is that the ice that sinks, either the red one or the green one, I don't know which one, the one that sinks will take more time to melt. The one that floats will melt faster. Not only that, the one that goes at the bottom will slowly melt but it will produce liquid D2O. And then you will see the remaining part of the D2O ice will float in its own melt. That will prove that it is indeed D2O. Alright, let's do this. You hold this one here, and nowadays I have two ice, one is orange, one is green. Let's go green first. See whether it is H2O or D2O. So I'll melt this one little bit from the sides. Yeah, this is nicely frozen in our poor man's deep freezer. Poor man's deep freezer is what people use for making kulfi. Ice and salt. Alright, you hold it here like this, so that everybody gets to see. This is much better than simply weighing it. So sometimes there are multiple experiments you can do to prove the same point. But again, like Occam's razor, I am going to do the one which everybody can see. So it will either float or sink. Oh, what happened? It sank. So the green one is D2O. And let's do the same experiment with the other piece. Unless my students have used D2O in both of them, sometimes they do that to play a trick. Unless, oops, it broke. Sorry. It is floating, right? It will not go down. But now you see that H2O at the top, D2O at the bottom, and that proves our point that H2O and D2O have very different densities, and D2O ice is heavier than H2O. Okay, so I will keep this one here, and one of you should keep an eye. When it partially melts, you take it around and show it to everybody. Okay, so that experiment is done. And let's see what we have next. Lights off, please. Yeah, somebody has to do quite a bit of work today. Since we talked about periodic table, here is the periodic table of your smartphone. Smartphone contains about 46 elements of the 118 in the periodic table. Okay? And remember that many of the elements that are being used in smartphones are actually getting depleted on the surface of Earth. So after a few decades, you will not have the same smartphones that we make today. So we need to conserve, reduce, reuse, recycle, and use your phone till its last day. Don't keep changing phones just because a newer phone has come out in the market. Okay, now back to nature, but actually chemistry. Some of you might have seen this experiment called, what experiment do you think I am going to show? Elephant toothpaste experiment, correct. Now that is a fun experiment, but it teaches you a principle of chemistry, and that's basically what I would like to emphasize today. What does it teach you? It teaches you about catalysis. Hydrogen peroxide has a weak bond between the two oxygen atoms. In other words, in simple terms, H2O2 has more oxygen than H2O, and any bond between similar atoms is generally weak. OO bond, FF bond, NN single bond, and so on. But H2O2 does not decompose on its own at room temperature. That's why it is used as a disinfectant. If you go with a cut to the health center, they will normally wash it with dilute hydrogen peroxide solution. But the decomposition can be catalyzed by many processes, many catalysts, including sodium iodide. And it is the iodide that acts as a catalyst. So if I take H2O2, add iodide, it will decompose into water and oxygen. But to make the experiment more interesting, what we are going to do is to take liquid soap. Can you remove this? We'll take liquid soap and mix that with, do you have the hydrogen peroxide here? Hydrogen peroxide and oxalyl chloride. You have not brought those? Is it in the ice box? Ethanol. Okay, I think we have to postpone this experiment because it's still in the fridge. Okay, so we'll come back to this and do this experiment a bit later. So let's move on to the next part of it, as and when they bring it. Lights off, please. I'll now go to the video part. Okay, remember we'll come back to this and do the experiment, but one of the things I would like to share with you is about bonding. All of you have written, all of you have studied Lewis dot structures. Right. So you might be familiar with this kind of depiction also for bonding. This is like two orbitals interacting, making handshake. But then if the sizes are dissimilar, like what you see here, one small, one big, it is like shaking hand with a small baby. Okay. It's not a very strong physical bond. And such bonds are formed between a small atom and a large atom like nitrogen and chlorine, nitrogen and iodine, and these bonds are very, very weak. Why are people interested in making weak bonds? Because weak bonds pack a lot of energy. Okay? So those who would like to use explosives like Air Force, they want high powered rockets. Okay? They would like to have molecules with lots of weak bonds, because such molecules will be packed with a lot of energy. On the other hand, if the bonds are strong, the orbitals are of similar size, good firm handshake, and strong bonds like C bond, CF bond, CO bond, and so on. Okay? Alright, that is fine. But I said the nitrogen is small, iodine is big, so the bond is very weak. If I have Ni3, nitrogen triiodide, it's a very, very powerful explosive, because not one, there are 3 Ni bonds, and it is so shock sensitive. You know, just now Diwali is over, many of you participated in fireworks, and some of you might have used the explosives, the bombs which you throw on the ground and they explode. Because of the shock, they explode. But this fellow, Ni3, is so shock sensitive, it will explode if you touch it with a feather. Okay, and let's do that experiment. I hope the audio is okay. No, the computer audio. Let's see. One second. ये लगा है ना? One second. Let us try it again. It's actually playing here. It's playing there, na? So I will change it to the, okay. Just give me a second. I will change it to the proper output, and then it should be okay. It is on the display audio. Okay, let's try again. No.
Or detonate. One detonation causes another to occur.
Okay, I'm sorry.
One product of...
Let's try again. Okay, from the beginning. We'll explode it multiple times.
When nitrogen triiodide, the dark-colored solid, is dry, it is very sensitive to touch or any vibration. Simply touching it with a feather causes it to explode or detonate. One detonation causes another to occur. One product of the reaction is violet iodine vapor.
Okay? Alright. So a question that comes with it is that if it is so shock sensitive, how do you keep it on the filter paper? Okay? Because by the time you put it on the filter paper, it can explode. So think about it and come back. One of you should remind me about the questions I'm asking. I may forget at the end. Now there is another type of bond called hydrogen bond, which is formed between two electronegative elements. How many of you have heard about hydrogen bonds? I think all of you. Okay? It's as shown here. Now, why is hydrogen bond important? It is important because it is important in chemistry and in biology both. And of course, physicists study the details of the nature of the hydrogen bond. It holds the alpha helix of the proteins that we have in our body. It holds the double helical structure of DNA, double helix. Okay? It holds the two strands together. And not only that, it is because of hydrogen bonding in water that we are alive. Otherwise, if there was no hydrogen bond between water molecules, water would have been a gas at room temperature, just like ammonia, and life would not exist on Earth. And here you can see that what happens is, this is liquid water, this is ice, this is liquid water, lot of hydrogen bonds, is a very compact structure, but when it freezes, it opens up like a diamond-like structure. So the volume increases, and that's why the density goes down, and that's why ice floats on water. Alright? Now, many of you have done this simple experiment at home. Yeah, how does it look now? Aha, I think you should take it to the lights on please for 1 more minute. You may or may not see that the D2O ice is now floating on liquid D2O. You take it around and show it to the students before entire thing melts. Okay, lights off please again. Many of you have done this experiment at home, that you take a full bottle of water and keep it in the deep freezer. What happens? Volume expands, the bottle gets distorted. If it is a glass bottle having a soft drink, you have put in the freezer for quick cooling, what will happen if you forget? It will break. We are going to do an experiment, not here, because it's too dangerous to do it here. We are going to take a steel case, put water in it and cool it to minus 80 degrees so that it freezes instantaneously, and let's see what happens. Okay, this is also.
The ice bomb illustrates the fact that the volume of ice is greater than the volume of an equal mass of liquid water. Some cold water is poured. The threaded plug is screwed into the bomb so that the bomb is tightly sealed.
Okay.
The bomb is then placed into a dry ice acetone slush, which is at negative 77 degrees Celsius, and will cause the water inside the bomb to freeze. A wooden box is placed over the top of the bomb and slush bath. It takes a short time for the water to freeze. When it does, the bomb explodes. Some of the dry ice acetone slush is blown onto the explosion shield. Little bits of the cast iron bomb are left. When the water freezes, tremendous pressure is produced. The pressure is enough to cause this cast iron bomb with more than 1/8 inch thick sides to burst.
So what this experiment shows basically is that you can confine water in a small space, and if you freeze it rapidly, there is sudden expansion in the volume, and that can expand with an explosive force. So for making a bomb, you really don't need RDX or TNT. Just plain water will do if you know the right chemistry. So be careful with such experiments. Okay, our H2O2 experiment is ready, and we go back to the catalysis experiment. Did you get H2O2? Okay, so let's do that experiment now. Elephant toothpaste. You open this one, have a dropper ready. So I'm taking this liquid soap here. I take about 20 ml of this liquid soap. Any brand will do. This is not any identified brand. Any liquid soap that you use at home will be okay. And we'll pour some hydrogen peroxide, which is not always easy to open. We have, in our chemical suppliers, many of the bottles are very user unfriendly. Very hard to open, very hard to close, as the volunteers are finding it. Don't break your nail. I have not the right gadget, but it can help. Yeah, be careful with hydrogen peroxide. Now one question, one problem I have, it says sodium iodide I will add and it will form oxygen, or foam in this case, because it is oxygen foam. But it can be either sodium that is a catalyst or iodide as the catalyst. How do I know whether it is sodium or iodide? Huh? No, how do I prove that it is the iodide that is the catalyst and not sodium? Sodium can be? I can add another sodium salt, right? I can add another sodium salt, and if that works as a catalyst, then sodium is the catalyst. Okay, wonderful. Thank you. I need to be careful about this. Oops, not this one. I think that quantity is fine, but you keep some more out. Okay, and I need to be very, very careful. I'm not doing it the right way. Unlike the volunteers, they are wearing gloves. I'm not wearing gloves. This is about 40 ml. Yeah, you add another 10 ml here. Might as well do it well. That's fine, thank you. I will give you a recipe for something that you can do at home, because 30% hydrogen peroxide is too dangerous for you to play with it. Okay. So I'm going to add some sodium bicarbonate first as another sodium salt. And let's see what happens. Nothing happened. So neither sodium nor bicarbonate is the catalyst. Alright? Next, I am going to add sodium iodide. And what I will do, I will add as a solution. Okay, I'll add a bit of water. Can you give me some water? Nothing is happening. What could go wrong? If those of you who have watched Sholay would remember the dialogue, "Ye bhi bach gaya." Okay, but then sodium iodide should have reacted, right? Let's see what could be the reason. Aha! I think I added sodium acetate. There were 3 here. I added sodium acetate by mistake. So it is not the chemistry, it's my mistake. Now we are going to add, this is sodium iodide. That's why it's very important to read labels. At home, you don't have to differentiate between sugar and salt. You know the difference. But in a chemistry lab, everything is a white powder, 90% of them, unless they are labeled properly. Okay? It's very difficult sometimes to figure out what is what. This is sodium iodide, unless the label is wrong, and some water. Now something should happen and will happen. I can guarantee that. Okay, we'll have an oxygen foam coming out here. And it's a very safe experiment. Just like burning H2O produces only H2O, this reaction produces H2O. As you see, the steam is coming out. And what else? Oxygen. And you know, there are so many of you here. It's good to have little more oxygen supply. Right? And you can confirm it is a oxygen flame. Do we have the matchbox? It is oxygen. By burning, sometimes we can use a incense stick, agarbatti. You will only see that the flame, sometimes it will catch fire, burst into flame if I have the bigger size stick. Okay. It will continue to glow. If it were carbon dioxide, it will immediately extinguish. Okay, so that part is done. Lights off, please, again. Let it be there, let it be there, don't touch it. This, by the way, those who are going to clean this up, there is a lot of unreacted hydrogen peroxide here. So you have to wash it very carefully. You can wash it down the drain, no issues. Okay? Let it be there because, you know, the students can actually see what's happening here. Can you break very strong bonds? We are talking about weak bonds so far. OO bond, Ni3, then what else? Hydrogen bonds. Can you break very strong bonds like CO2, C double bond O? You know, these are some relevance to what Professor Deepa Koshalani talked about again. This bond is very strong. It's a double bond, 190 calories per mole, kilocalories per mole. But let's see whether it can be broken. How many of you have seen or heard about dry ice? Oh, at your age, I've never seen dry ice. Dry ice is called dry ice. Why is that? It's a it's a solid form of carbon dioxide, but there are solid forms of many things are available. Not everything is called dry ice. Because it doesn't form a liquid, it forms a vapor directly, and that process is called sublimation. If you study a little bit more about chemistry, you will know why CO2 why CO2 sublimes, but why H2O does not sublime. It forms a liquid. So let's watch this video about dry ice and its reaction with a metal. What happened to our audio?
The magnesium is ignited.
So you put dry ice in a cavity of, magnesium in a cavity of dry ice, ignite it and cover with another block of dry ice.
And covered with another block of dry ice.
So the burning magnesium has nothing but dry ice around it. Okay? Normally it should not glow. But let's see what happens.
Despite the absence of air, the magnesium continues to glow due to its reaction with carbon dioxide. Because of this reaction, carbon dioxide cannot be used to extinguish magnesium fires.
If you have a metal fire, never use carbon dioxide because they will continue to burn CO2. And let's see what's inside. Open. Yep.
The reaction products are white magnesium oxide and black carbon.
So interestingly, what Mg has done is to extract O2 out of CO2. Exactly what we want for converting atmospheric carbon dioxide back into carbon. All the carbon we are using in coal-fired plants forms carbon dioxide. And if we burn it with magnesium, I'll get back carbon and MgO. Now, what is the catch here? Why are we not doing it? Because magnesium metal is too reactive. It's not found in nature. It's found in ores like dolomite, and magnetite, not magnesite, magnesite and dolomite, and it is Mg2 plus. So to get to magnesium metal, you have put in that much of energy. So unless that much of energy is put in, you will not get magnesium metal. So we are back into the situation. But this gives some idea about how much energy you require to convert CO2 back into elemental carbon. Okay, I will now close this. What about breaking nitrogen-nitrogen triple bond? Somebody in the morning said, what about using nitrogen as a fuel? It doesn't work because N triple bond is one of the strongest bonds, 227 kilocalories per mole. And to make ammonia, you need hydrogen, right? And that's an endothermic reaction because you have to break a triple bond completely, okay? All right, but then it can be broken, okay? So I'm giving you hints to a question I asked in the beginning, okay? Anyway, we'll come back to that. Now, the last few experiments will be about color. So this first experiment, I will not show any, as a demo. I will simply say that there are certain solvents which are called polar solvents. Can you name a few? H2O, methanol, ethanol. What about non-polar solvents? Benzene, petrol, hexane, kerosene, and so on. There are some colors or dyes which show very different colors even with a small change in solvent polarity. Okay, and here is the world record holder. This particular dye is called Reichardt's dye, named after a German chemist, Reichard, who made this dye first. And it shows such a solvatochromic behavior, that is change of color with solvent, that methanol, ethanol, isopropanol, acetone all show very different colors. Okay? Particularly striking is the methanol and ethanol color difference. Okay? So, as you know that in India, many poor people die because of drinking methanol thinking it is ethanol. Methanol is toxic, ethanol is also toxic, but at a much higher concentration. And it would be nice to have a quick way to distinguish whether a tanker, for example, is transporting methanol or ethanol. And here's a quick test. You can simply distinguish by the color. Okay, so that is solvatochromism. There is another type of color change with temperature. That's called thermochromism. Okay, so do we have the thermochromism? Yeah, I think this can be removed now, and you put the thermochromism tray here. That's not the one which is the plastic glass. Yep. And where is the hair dryer? Here. Okay, excellent. But before that, I need some water. Can I have some water, please? Thank you. It's not cold enough. I need some ice. Oh my God. Do you see what is happening with the glass? Turning red. Is it the glass that is bad or the water that is bad? Water may have gone red. How do I prove it? See, always there is an experiment to prove your hypothesis. And now the hypothesis is that I pour, can you hold it? Ooh. I pour it to prove whether there is a very trivial experiment, but experiment nevertheless. I pour it out, and then I do another experiment. Exactly. This is the temperature sensitive surface. This is a magic glass which has a thermochromic material. Okay, I don't know what it is because I got it from a publishing house in 2011, which was the International Year of Chemistry. You know why 2011 was the International Year of Chemistry? A very famous woman got a Nobel Prize in Chemistry in 1911. Who could that be? Marie Curie, right. So this glass has a dye, thermochromic dye, which changes color below 10 degrees. But it is reversible as it becomes warmed up by my hand, which is hopefully at 37 degrees. It goes back to the colorless mode. But I've got two more examples of thermochromic materials. One is, I will show you in the next slide. One is this banana, and one is an apple. It's actually meant for high school children. Okay? No, the idea is that this is a salt, silver salt of HgI4 minus. So this is Ag2HgI4, which is yellow in color, and you will see that at about 50 degrees it turns orange. An apple is made with a corresponding copper salt. You know, it's fascinating that you go from silver, yellow, to copper, which is red. And this becomes orange at 50 degrees. This is not hot enough, but then you see it is becoming orange. Do you see it is becoming orange? But it will become yellow when I wave it in the air because it is now getting cooled. Okay? So this is a very simple way to make this salt, but then since it uses mercury, it is absolutely essential that you take supervision for making it. This is the silver salt. And this happens because of a change in the crystal structure of these materials as a function of temperature. So to understand why the color change and why the specific color change happens, you have to read a paper by Kanishko Biswas from JNC ASR in Bangalore. Now this is a hair dryer for human beings, and no man or woman would heat his or her hair beyond 50 degrees. So this may not go to 70 degrees, and we are waiting for the hot air. Let me try by keeping it close, see if it turns black. In fact, I am testing whether this hair dryer produces air above 67 degrees. It doesn't. Because if it were, then this material would have shown a change in color. You know, that's why certain materials are very important to detect hot surfaces. Sometimes pizza boxes used to be delivered with a thermochromic material which would say hot if the pizza is hot, and when it is cool it becomes black. Okay? So we will come back to this once the more powerful lab heater comes to us in the next few minutes. Okay, so let's move on to the next slide. So this is something you have seen. Yeah, this is just to show you that this is the silver salt, yellow to orange, whereas copper salt goes from red to black at 67 degrees. Okay, now some more experiment with light. The next one. Measuring cylinder, drinking water glass. Yeah. Okay. So while we are waiting for this one, lights off please. Let me see how we are doing with time. Okay, we have another 35 minutes. Professor Ganguly, did I still have my hour and 45 minutes? Or you want me to finish a little sooner? Only thing is that, are you getting bored? Are you sure? Yes, okay, because the last experiment is going to be the most important one. So in case we have to cut short, you will miss the most important experiment. Why is the sky blue? Why is the setting sun red? Again because of scattering. Okay, so when light interacts with matter, many things can happen. What all are the possibilities? Transmission, reflection, refraction, diffraction, absorption. Right? if it gets absorbed, then again many things can happen. When a material absorbs light, it is basically absorbing energy. So it can emit, it can lose the energy in the form of heat, and then another important thing can happen, it can emit the energy as light of another wavelength, and that is called absorption of light and re-emission. That's called fluorescence. Of course, scattering can also happen. And the third thing that can happen is that light gets absorbed, but it transforms into chemical reaction. And again, Deepa mentioned about it in the first talk. That's why we survive on Earth, because Earth, the sun's light or the energy makes photosynthesis and we get food. Okay, small distraction here. Light please. This is a very powerful heat gun, and you will see it is turning. Oh my God, this apple looks rotten. But the nice thing about this thermochromic material is that it is reversible, so I can bring a rotten apple back to its fresh state. It would have been nice if this could happen in real life. Thank you very much. Okay, so those are the two thermochromic materials. Now going back into the experiment with light, lights off please. So I'm going to show some experiments, but first let's have some drinks. How many of you have heard about Indian tonic water? Not many. I had to bring it from Bangalore. It doesn't seem to be available in Berhampur. You know why it is called tonic water? There's an interesting story. When the British came to India, they were not particularly welcomed by people, but they were certainly not welcomed by mosquitoes. So they all got malaria. And the only known medicine at that time was quinine. And quinine is very bitter. So they dissolved quinine in water and started drinking it in small quantities as a potential precaution against malaria. And you know, the British people always find a lot of innovative techniques, and they used various other things to add to it, to the tonic water, to make it more palatable. But since most of you are, I think all of you are below 21, we will not talk about it. But tonic water contains this molecule quinine, and what is interesting is that quinine was the first molecule which kind of triggered the study of fluorescence. So quinine absorbs light and emits at a shorter wavelength. Now, as a drink similar to tonic water but not having quinine, I have this small can of Sprite. Okay? All lights off please. So I have Sprite here. All lights off please. What's that? I don't need that. I don't need salt water here. And I have put tonic water here to the same level. Not bad. Okay, so one is tonic water. They both look similar, right? They both look similar. Now I will ask one of the volunteers to turn it around so that I don't know which one is which. Okay, I'm not looking. I don't have eyes on my back. Turn it around in a way that I don't get to see that. All lights off please. But as I said, this row and that row, quinine would show fluorescence. That is, tonic water will show fluorescence, and the other one, Sprite, will not show fluorescence. So you guys have turned it around. So I don't know which one is which. This is Sprite, and this is beautiful tonic water showing the fluorescence of quinine. Okay. And what I have is a small UV torch that you can buy from Amazon for about 300 rupees. Yeah, we are not going to going to drink any of these liquids today. Okay. So let me put this one back into this. All right. I will show you some more experiments. All the measuring cylinders and this one. Okay. You set the 4 measuring cylinders. You have the milk. Yeah, thank you. When light passes through a medium, it gets partially absorbed. And some of you may have heard about Lambert-Beer's law. If not, you will study it later. And this basically tells you about how absorption and concentration are related. So this is absorption of light. Emission of light is when, let's say, green light falls here and light of a longer wavelength comes out. Okay? So what we are going to do today is to convert green light into yellow light and blue light into green light. Okay, so to do that, can I have the lights on for a moment, the front 2 lights? And we will put water in each of these measuring cylinders. 1, can you pour in all of them? And then now let me ask the students, very stupid question, what is this? You know, in science, you have to be accurate, brief and clear. You are not accurate when you say it's a highlighter. It's a pink highlighter. That will give you 110 out of 10. Similarly, this one, great, thank you. Okay, so I need a dropper. This is milk. Give me a dropper. This is water. And I'm going to add a couple of drops of milk here. That's all. And then here I'm going to put this yellow highlighter which contains a dye called, anybody knows? It's called fluorescein. You can see it's fluorescing, right? And the last one I'm going to add some of you may have seen my experiments except this. This is a new addition, especially for Professor Ganguly and Professor Das. Because otherwise, you know, if I don't add or modify experiments, those sitting in the front row, they said, oh, UM is showing the same old experiments. Now, this contains a dye called a rhodamine dye, whose name is solvent red 49. And what I would like to do here today is to show you specific absorption and emission of light. And this, of course, is milk, so that will show scattering of light. Oh, but I need light source. Where are my light sources? Aha, here. Can I have the lights off, please? And then I have got, press B on my computer. I've got 405 nanometer. Okay. I have got 545 nanometer and I've got 700 nanometer, 3 lasers. So first one will show only this water is not clean. Okay, it is showing a little bit of scattering. Okay, and let me pass the red light also. You see, this is pure water, so there should be no transmission. But you also notice something interesting. Blue light, do you see much scattering? Green light, not much. Red, not significant scattering. Whereas in blue light you see more scattering. Because because there is a reverse wavelength dependence on scattering. 1 by lambda to the power 4, and that is why the sky looks blue, because blue light gets scattered more than other parts of the VIBGYOR in our atmosphere. Okay, and when we see the sun, it comes through a long column of atmospheric air, so blue and shorter wavelengths get removed from the spectrum, and what is left is red. So here's a quick way by which we can explain indirectly why the sky is blue. Now interestingly, what you see here is that fluorescein, that is yellow highlighter, I pass red light, I see nothing, because it neither absorbs red light nor it scatters. For pink highlighter, there is no absorption but there is scattering, right? Because the highlighter also contains silica-like particles which can spread the ink on the surface. Alright? And let's see what happens when I pass the blue light to the pink. Again I see only scattering. But notice blue becomes green now. This is blue, but this is green. On the other hand, when I pass the green light here or here, I see no absorption, but no scattering. Well, I will say scattering in milk, no absorption with yellow highlighter, but notice something interesting. Now blue becomes yellow, and here, this is not blue, this is green becomes yellow, and what you notice is that the transmitted light is actually, well, you don't see the transmitted light here, but what I'm going to do, can you throw half of it away and pour some water in it? I'll make it more dilute so that less light gets absorbed. And that is basically the principle of Lambert-Beer's law. That is, absorption is related to the concentration. I'll quickly show this one because we are kind of running out of time. Thank you. That's enough. So we have now diluted this, and I'm going to pass the green laser through it again. It shows yellow, and the transmitted light is all still very less, but the transmitted light should appear green. Okay? So here you see a very interesting effect of fluorescence. Blue light becomes green and green light becomes pink. Now where is our tonic water? Tonic water is here. See, in the dark I cannot identify which one is tonic water. Now it turns out that yellow and blue are complementary colors. So if I now mix the pink highlighter with tonic water and shine blue light through it, what should I get? I should get a mix of yellow and blue, and that should give me white light. Why don't we do that experiment? So can you pour some of it out? My tonic water is already gone, but I'm adding the pink color, and let's see what happens. See, it is turning whitish. It's no longer blue. I'll add a little more pink color. This is like doing a titration, and it should now show me a whitish color. So it is no longer blue, what we saw before. So my purpose of doing this experiment, you can clear everything now. Can I have the lights on, please? My purpose of doing this experiment is basically to highlight that it's very important to understand the effect of light on different types of materials, absorption, emission. I have excluded photochemistry. You can also do interesting thing about photochemistry, how color changes with light. Some of you might have seen these photochromic lenses. Is it rain? Is it fan? Okay. Okay, I think I have skipped one experiment that is on the SN1 reaction because I think time is a little tight. So I'll skip one reaction, but I can leave the materials here. Some of you can show it later on. So the last experiment is not about conversion of light, but about conversion of chemical energy into light. Now, you said that happens in many places when you burn coal, when you burn gas. In the old tungsten lamps, you heat the tungsten filament, it gets very hot and it emits light. So, but then there is a chemical energy gets converted to heat and then light. Lights off please again for a moment. On the other hand, what do you call fireflies in Nodia? So fireflies called jugnu in Hindi, right? So fireflies emit light at room temperature, at the body temperature, because, silence please, by conversion of chemical energy enzymatically into light, and that is called bioluminescence. And fireflies are not the only ones. Hey, please wait, because I am going to do the most important and the last experiment now. Okay, just give me another 2 minutes to set things up. We are going to get our old friend. Can I get the oxalyl chloride and hydrogen peroxide here? And 2 droppers. Okay, rest of the things I will manage. So what we are going to do is to react our old friend hydrogen peroxide with something very nasty chemical, but it will not reach you, I assure you that, oxalyl chloride, to produce what looks like a carbon dioxide on the top and carbon dioxide on the bottom. 2 carbon dioxide stitched together. Now this has an OO bond. It's a 4-membered ring, extremely strained molecule. So when you have, for example, an extremely strained molecule, like you compress a spring, it will try to release energy, right? So this molecule also, when you make it, it breaks into 2 carbon dioxide molecule. One of them is normal carbon dioxide, which you and I breathe out. The other one contains a lot of energy. But the problem is that energy is lost as heat. So conversion of chemical energy into heat is no fun. That we all know happens for exothermic reactions. But in the presence of certain molecules, fluorescent molecules, which have the right kind of energy between their lower energy state and the higher energy state, technically called electronically excited state, they can trap this energy. Now if we choose these molecules carefully, they can lose their energy not by thermal means but by radiative transition. In simple words, they will emit light of an appropriate wavelength specific to the nature of the molecule A. That is basically difference between this energy and this energy. So for today's experiment, we are going to use 4 different dyes, DPA. The exact, the names and the structures are not important to you, but this will give you a blue-violet light, this will give you an orange light, this will give you a sky blue or a cyan color, this will give you a green color. So give me 2 or 3 minutes to set things up, dichloromethane, oxalyl chloride, and put droppers in those. And where is my other, here. Okay. Okay, put a dropper here also. Put that dropper, okay. EDCM, excellent. I think some of you can also come this side. Because I skipped one experiment, so ethyl acid I don't need. That is for a different scheme of things. Okay, all right. Can I have these 2 lights on just for 1 minute? so that I know what I'm adding. Thank you. So I will add from your left side some diphenyl anthracene here. To the second one, I will add rubrene. This requires a little bit of preparation, that's why I ask you to wait patiently. Third one, I will add something called perylene. If you like the bright red color of some cars, I'm sure many of you like that, that would normally have a perylene derivative because that's a very stable hydrocarbon. And the last one, I will add something called tetracene, which looks like two naphthalenes stitched together. That's a very expensive part, and I must thank Dr. Palani of Merck Sigma Aldrich for supplying this, because 100 milligrams of this, 100 milligrams, cost about 15,000 rupees. Okay, so that is not something that is easy to do, DCM. This is for H2O2. So I will dissolve these molecules or these dyes. These are very strongly fluorescent dyes into dichloromethane. Okay, 1, 2. This works very well in a completely dark room. I will do 2 at a time, okay? Okay, so this is done. And yeah, you can close it, remove it. Okay. So I will add oxalyl chloride first and then hydrogen peroxide. And one of you can hold the torch. Lights off, please. And I just want to show you that, no, it's okay, that if I shine the green laser, blue laser, I will see this color. Okay, the fluorescent color. But that is light into light, and here again you see the orange color. And you will see the cyan color here. But we are not going to use light as the energy, but we will use chemical energy as the energy. Okay, so I add some oxalyl chloride into the first one and into the second one. And then can you press B on my computer? And then, now lights off. I think there is enough light. In fact, this experiment works so well in a completely dark room. Now, are we ready? Okay, so as promised, I've got blue light here on your left and orange light on your right. And now it turns out that these two lights are again complementary colors. So I can mix them, get a white color. But we'll do something more interesting. Let's see if it works. Because this requires a little bit of practice and it doesn't work all the time. I'm going to add the orange color, which will be orange first, then white, then blue again. Okay, you see it's orange, white and blue again. I'll do the reverse one. Okay. So the orange color does not stay for a very long time. That's why it shows a bit of difference. I think I might have burnt my thumb with some friendly hydrogen peroxide. So let me wipe it out. Okay. And then the last two experiments will be with perylene, and you can take care of that. Close it and so this is the cyan color from perylene on your left, and on your right is the green color from tetracene. Okay? So therefore you can see that, and this is all cold flasks. Okay, I can hold it at the bottom. There is no heat generated because dichloromethane boils at 39 degrees, and clearly it's cold light, and chemical energy of hydrogen peroxide has been converted to light. So this color will stay for a long time. The green color will go. This violet blue color has nearly gone. Of course, the orange color is gone long back. But this blue color, because perylene is a very stable molecule, will remain for quite some time. Okay, so that was the last experiment that I wanted to show you, and I'm happy that mostly things have worked. I skipped one experiment. This was during one of my online talks. Coming back to this question, what is it? This is an ammonia reactor. I said that can you break high nitrogen-nitrogen bonds? This in fact is an ammonia reactor outside a German chemical company called BASF. It's the largest chemical company in the world. And this ammonia reactor, whose name is associated with ammonia synthesis. So this reactor was actually designed and built by Haber and Bosch. And this produced about 1 million tons of ammonia over 55 years. And this is kept as a monument outside the BASF factory in a place called Ludwigshafen in Germany. I have a video, but I don't think I have the time to play this one. I should finish in the next 4 or 5 minutes because you have another exciting presentation coming up. This is a person who got 2 unshared Nobel Prizes. Can you guess the name? Pauling. Somebody said Pauling, right? Yeah. So it is Linus Pauling, who is the only person so far who got 2 unshared Nobel Prizes. First one in chemistry, and the second one is peace. One of the things Pauling said is that, remember I showed you the picture of a alpha helix structure of a protein, which I said is held together by hydrogen bond. That structure was in fact determined, first Pauling came up with this idea. So he discovered the alpha helix structure, and he discovered it after making unsuccessful research for 11 years, and surprisingly he discovered it when he was in a hospital bed in Oxford. Okay, so the moral of the story is that never give up, like Pauling or like this frog here. Okay, the other message that I would like to pass on to you is that keep your eyes open, except when sleeping. The jokes apart, the point here is that nature presents a lot of interesting problems, interesting situations, and unless you are ready to move forward, you may miss an opportunity. That's why Pasteur many years ago said, chance favors the prepared mind. Okay? There's a bonus question here that's only for fun. Can somebody name this picture? What do you see on the bottom? Orange. What do you see on the top? So what is the CH3 group called? So what would you call this connection? Methyl orange, whose chemical structure is here. So whoever said methyl orange first deserves a chocolate. Okay? This is just for a bit of fun. Now I am coming back to the periodic table. How many of you have heard the periodic table song? Just a few. Then I must end with the periodic table song. Professor Ganguly, is that okay? That will take 2 minutes. Because I skipped the video, I skipped one experiment. So I think I deserve to play the periodic table song, and I still have 8 minutes left out of my 100 minutes as per the clock. So I think I'm okay. Periodic table song was created by a mathematician of Harvard University named Tom Lehrer. So he composed this song and sang it himself in 1954-55 based on the elements available known at that time. So I'm going to play the old version of the song. There's a version that is also from a video by Lehrer, recorded in 1969 in Copenhagen, but I will not play that, okay? If you are interested, you can, my computer is here. If you are interested, you can play that one, search for it, but let me play this one and make way for Professor Das.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Thank you. Thank you very much. But I just want to say that, I don't deserve any credit for putting it together, because this is all based on known experiments, known videos, which you can find from different websites. So I have come to the end, and I hope that I've been able to give you a glimpse of simple experiments, relatively simple experiments, by which you can learn, which can entertain you, and by which you can learn certain principles of chemistry. Because of the sort of time requirements, I could not show another experiment on SN1 reaction. This is something those who are in class 12 would know, that for SN1 reaction, a tertiary halide reacts faster than a secondary reacts faster than a primary. There's a very simple experiment that one can do to demonstrate that, but that requires about 6 to 8 minutes, so I chose not to do that today. But I do hope that the experiments, 7 experiments or 8 experiments I have shown, plus the videos have given you some idea about how chemistry can be exciting, chemistry can be fun. So before I end, I would like to have a few glimpses of pictures from other places where I have done the experiments. This was done in Cape Town as part of the IUPAC activity last year, and here is one in Bangalore with people from the local people. This was in Kuching, Malaysia earlier this year, again for school children. And the most recent one also was in Malaysia in a place called Bangi, which is north of Kuala Lumpur. And the question is, where do I go next? My personal preference is to do it on Mars. If you think I'm joking, here's my boarding pass. Okay. So in July 2026, there's a flight to Mars. You can also go to NASA website and register for that. Jokes apart, I would like to thank again all my volunteers. Please come to the center of the stage. Thank you very much, and thank you, the audience. Thank you. Can somebody take a picture so that I can add it to my next year's presentation? Thank you all. Thank you very much. I'll be happy to answer questions if there's time allowed. Yes, I need to organize things back into. This is a spare one, right? Yeah, I'll slowly pack these things together.
Any questions?
That you can throw.
Yeah, anybody has a question? Yeah.
Yeah, yeah. Back it later. Oh yeah, of course. Yeah, please.
सर
Yeah.
सर आपने वो वीडियो दिखाया था फेदर वाला, आपने बोला था आप बताओगे उस चीज का।
वेरी गुड। वो कैसे पेपर के ऊपर आ गया?
यस सर।
How did it come? Do you remember that when you buy these patakas, okay, if sometimes they do not ignite, what do? You keep it in the sun to dry it, right? Because water is a no-no for any kind of explosives, because water has a high specific heat, so when you ignite it, it takes the heat away. So you put the Ni3 in the form of an aqueous paste, put it on the filter paper, and then you run away when it gets dried up. Because you also feel that if you sneeze very hard next to Ni3, it can explode. Okay, I have not done that experiment, but it can be tried. When somebody has a bad cold, you can try it. So basically, when it is wet, it does not explode. Thank you for asking the question.
Yeah. Any other question?
I'll clear it up.
Sir, will the Ni3 explode if 4 or 5 people start clapping near it?
Yeah. I have not done this experiment, but it may happen that if they clap very close to that, it can be enough of a shock wave to ignite that. It's possible. If sneezing can explode it, perhaps, the sneezing experiment has also not been done, but I will give it a try sometime.
Good afternoon, sir.
Yeah.
Sir, there was a question, sir, in the experiment, sir, 2.2 liters of hydrogen, how much amount of water will come? You will say.
Your answer? 1.8 grams. Yes, that's right. Because this comes from gas law. Because 1 mole of hydrogen is 22.4 liters.
Sir, I assume 22 liters because 2.2 was there.
Well, yeah, 22 is also fine. So 2.2 I said as a rough volume because I have not measured the volume, right? So 1 liter of hydrogen is roughly 2.2 or 2.24 liter, 1/10 of a mole, right? So it will produce 1/10 of a mole of water. So each balloon roughly produced 1.8 grams of water. Altogether we made 7.2 grams of water, give or take 0.5 grams. Okay? Yeah.
Sir, you have said that you will say one recipe with us.
I will say what?
Recipe with us. Elephant.
Recipe for?
Elephant toothpaste.
Oh, for the elephant toothpaste.
Yeah.
That is very easy. You mix a paste of baking soda solution, mix it with soap, add vinegar. Yeah. Fountain, but if you want to make a foam, you have to add a little bit of soap to the baking soda or to vinegar.
Okay.
Sir, I had a doubt. In the experiment that you did with the balloon, when it exploded, when it came in contact with fire, what happened to the water that was formed in the reaction?
It will form water because what happens is really this reaction between H2 and O2 is again requires a little bit of a trigger in the form of a fire. So once you ignite it, it explodes and basically the water that is produced because of the heat, it becomes steam. So we didn't see that because it got mixed with the air.
So, sir, can we produce a lot of water by that reaction?
Yeah, but then that will be very uneconomical way of making water because that water will be very expensive.
Thank you, sir.
Greetings, sir.
Thank you.
I had a question about career. Like, if we want to do all these kind of things, then what qualification do we need? Like to legally do all these experiments?
Why would you just like to do the experiment?
No, to discover more things or research that has not been done yet. Then what qualifications do we need?
Well, then you have to study chemistry, BSc chemistry, MSc chemistry, or BSc and then integrated PhD chemistry. That is one way to get into.
You can also do chemical engineering. You can also do bioengineering. Yeah. Any last question?
Last question. After that, I will pack off.
Any question from a teacher? Yeah.
गुड आफ्टरनून सर सर SN1 रिएक्शन हम बोल रहे थे दिखाने के लिए हाउ टू शो दैट SN1 रिएक्शन
Okay. I can talk to you during the tea break.
Yes, sir.
Because that will require a little bit of discussion.
Yes, sir.
And I have some materials. I can pass it on to you. You
Yes,
can
sir.
actually do it.
Sir, I can
yourself.
show the students also, no?
Yeah.
That SN1, SN2 we have in class 12th chemistry.
But I will give you the materials.
Yes,
you
sir.
do it in your school.
Yes, sir.
I'll
Thank
give
you,
you
sir.
the procedure.
Thank you, sir.
Okay. Thank you.
Any other question from any other teacher or student? Last question before we start the next one.
Okay, sure.
Okay, then we thank Professor Uday Maitra for a very, very exciting
My
talk.
scholar here. And there was a black bag. Thank you. Thank you very much.
Yeah, I would like to request Professor Ashok Ganguly to felicitate speaker.
No. And don't forget that all my.
Oh, it's here, Sir. अच्छा अच्छा अच्छा
Samples.
You are ready? You are ready? So we are into the second one before tea. This is also going to be a lecture demonstration and based on chemical principles. So we have Professor Amlan Kumar Das. He is an excellent teacher and I know him because I did lot of outreach program in Rajasthan with him. So I have been to his university 3 or 4 times. The Indian Academy of Science organizes meetings in various places and I have chaired such meetings in many universities across the country. And we have, Professor Uday Maitra, myself have been to his place twice. And many others have gone to his place. It's a private university in Rajasthan where he is teaching. It's a girls' university and they have all kinds of engineering and everything. So Amlan Das is a very, very dedicated teacher and very, very interested in teaching students and has been in Sikkim Manipal University and also in this university at Rajasthan. So with him actually is also his wife who is going to help us, Snigdha, and she is also very interested in education. She works for an education foundation in Udaipur, but both of them started their career, actually they could have gone to bigger universities. They went into education development in one of the programs started by Professor Yashpal and others in Madhya Pradesh. It's called the Hoshangabad experiment. And she continues to do education development, setting up experiments, low-cost experiments, teachers training in rural areas, She has done a lot of work in Odisha also, I believe, but she has done a lot of work in Madhya Pradesh and other places. And Dr. Das, I have already told, I think, most of the things, but I don't know if anything else is remaining. Okay, let me read. So he basically did his PhD from BHU, and he has worked on experiments on oscillatory transport across membranes and their biological implications, etc. He has also worked at Bose Institute as a postdoctoral fellow and published several research papers on oscillatory phenomena across membranes. He has been associated with the NGO called Eklavya, Institute for Educational Research and Innovative Action, at Hoshangabad Science Teaching Program, which is an activity-based teaching and learning process. He is also a member of several scientific societies and faculty advisor of the International Student Chapter of American Chemical Society at Modi University. He has organized several workshops for education. So thank you, Dr. Das and Sigda, for this operation. So you have 1 hour around.
Thank you, Professor Ganguly, for the nice introduction. Good afternoon to everybody.
Not working. This, maybe you have to go closer.
Okay.
Exactly.
Hello. Good afternoon, everybody. Good afternoon. Okay, we had a very nice presentation, and after that, let's see how it goes. So my topic today is a joy of learning through science experiments. No, light is required. Just we will go. So I am from Modi University of Science and Technology, which is exclusively for the girls. This is in Rajasthan. This is the pointer. So we have seen the whole exciting experiment in the, okay. Okay, why do you do experiments? The answer already you have got. Say, what is the excitement in experiment? So in science, you have two ways of seeing things. You have a lot of hypotheses. You can read it. You have a lot of theories. You can read it. You can express it in exam and get pass, good marks. That's okay. But there is another way of learning is whatever hypothesis or theory you are learning. So can it be tested through experiment in laboratory? I mean laboratory or in a school environment. In all the time, it is not possible. Time restriction is there. So it is not possible to do all the experiments or to learn the hypothesis or any theory through experiments. So you have to find some time, if I have to find some fun, we have to find some excitement in doing experiments about learning the hypothesis or learning the theory through activity. So in the very first activity, it raises a lot of questions. You see you want to do this experiment. There is a candle experiment, and you will see the if what observation you have. In this case, the picture shows that there is a candle. Okay. There is some candle is over here, and there is some water over here. In water we have given food color, and it will be basically the candle will be lighted and candle will be burning, and on the top we will put a glass, then you see the observation. So light, please let us do the experiment, and you may have to see, I think all of, light please. The candle, yeah, just a minute. So we will first light one candle. There are 3 candles together. So we will first light one candle. Okay, now pour the glass. Let us see the observation. Can you see from your place? What you have seen? Water has risen to some extent. That is okay. So the questions will come to mind. Why the water rise up? So you take there is a graph paper or pasted on in, some level is around 1 centimeter, the water has risen up. So the question will come to your mind, so why the water has risen up, or then what could be the reason? Can you tell anyone? There is no chocolate from my side. What is the pressure? How the pressure difference is there? CO2. So CO2 has been formed probably. CO2 has not been consumed. The candle was burning. It has stopped burning. So you can say for burning oxygen was needed. So inside what the gas can be consumed? Oxygen is consumed. Oxygen consumed. Okay. So is there any relation of consumption of oxygen and the rise of water? You have another reason कि carbon dioxide has formed. Carbon dioxide may give pressure downward. That is also another reason. Then the temperature inside the air is also high because it was a candle was burning. So there may be expansion of air, that will be a downward pressure, that is also another reason. So there are several reasons. But if you directly connect it, the amount of water, amount of air in the, amount of oxygen in the air and the height of the water has level risen up. So you have to test. So this is 1 centimeter. Let us now light 3 candles together and let us see how much water is rising up. Let's see. Okay. Let's see. This is increase. So this is around to say I think it is around 3 centimeter from the another level. So 1 centimeter to 3 centimeter. So why does the increase is more? If you related the amount of oxygen in one air, say around 20%, 1/5, so then one candle is giving this much. 3 candle is giving this much. If you increase the number of candles, we have done this experiment several times, your water level is rising gradually. So it is not related to the how much percentage of oxygen in the air, 20% is around in the air. It is not related to that. Even if you say that all the oxygen has been consumed and that the water has been risen, that is the only reason we have tested this one. We say if you one agrabatti you can take and say suppose this is a big plastic bottle and plastic does not melt, and if you put agrabatti or lighted agrabatti in here, so lighted agrabatti will again glow, again catch up the oxygen. So inside there is still oxygen. So this is the experiment you can do at home and find out, and parameters you can change. You can change the this container also, take a circular one, and if you take more water, that is also a parameter. That is the height of the water reason. It will also vary. So this is the and another observation here is, if you look at the glass carefully, there is a white kind of material on the glass, white kind of material on the glass. So what could be the white kind of material in this? That is also one question to be answered. And this is why, so candle flame has consumed oxygen in the air available. Candle flame has produced carbon dioxide, which is again soluble in water also to some extent. Hydrogen, carbon dioxide insoluble in water, carbonic acid is created. So several reasons is able to and to be answered here to all these questions. So let us see now the carbon, the candle flame which has been basically extinguished. So let us take the carbon flame in the next experiment. So we will do the carbon flame candle flame experiment. So can you? Achha, okay. इसको चलाओ.
One person. Okay, you can come. 3 of you. Try it out. Yeah, come in here. They can do it. Yeah. Try any one of you.
सीधा करके. Yeah. What is rising?
Is it less or more than? More, ma'am.
More than single candle. So if we increase the candle, the water height of the water rise will increase. The several reasons, several variation you can do at home. This is very ना तीसरा वाला जला नहीं है. Okay.
Is it less?
2 candles.
Mark, right? To even compare, you need to actually calibrate that place. You need to put a mark. Every time you see the water rise, you need to put a mark there.
So there are a lot of variation. So that is we are going to the next experiment कि white kind of substance जो है वो क्या है, वो हम चेक करना चाहते हैं. ये अभी कैंडल जला. Next experiment we will check. Inside it.
Inside that we see some white dense type
Deposits,
of
okay.
yeah, deposits on the walls of the glass.
Okay.
Smoke.
What else?
Is it water? Water vapor?
Any other guesses?
Shouldn't it be black?
Carbon monoxide. No, candle is burning. Candle material, what is the candle material?
Wax.
Maybe that is wax vapor deposits, wax vapor deposits. So there are so many variations here. Do this experiment at home. Take the different container, pour the different water, first single candle, then second candle, then third candle, fourth candle. You will see the variation of the height of the water inside the glass level. So one thing is certain. It was in NCERT book. They are trying to relate this height of the water inside the glass with the percentage of oxygen in air, which is around 1/5. 1/5 they try to relate that, but after so many experiments it has come to notice that no, that is not the only reason. There are several reasons behind it. So that's why NCERT books has presently, I think presently they have removed this experiment for the proof of 1/5 of the oxygen in the air. This experiment has been removed right now. So you do this experiment and come to see what are the variation, and what we will connect to the second experiment is the white vapor inside the glass is what we will study the candle flame now in our next experiment. Let's see. Okay, thank you, beta.
Thank you, sir.
This is one experiment which is very unique in nature. Your candle flame light, please switch off. नीडल लेके लाना पड़ेगा ना? ना नहीं, मेरे पास है. Vaseline होगा क्या? You have one candle also. There are candle chemistry is there. There are basically 3 zones. You may not be noticed. Two zone you can easily understand. So outer zone, then there is a middle zone, and there is a inner side zone. So inner side zone is called basically the coolest one, the coolest zone, and that is contains wax vapor. And wax vapor is burning, and so wax first is this is an example of where you can see the physical change and the chemical change both. So chemical change you can understand. So through the wax vapor is burning, it will produce initially with the heat it will produce element carbon and hydrogen, and that with then further carbon and hydrogen will catch up the oxygen of the air, and finally forming carbon dioxide and water. This is the product, and there are 3 zones. Outer zone is the hottest zone, then the middle zone, and there's inside there is a zone which is basically wax vapor. That is, we are expecting that the deposits in the glass is a wax vapor. So I was tempted to check wax vapor. So there is a syringe I have taken. I will take out the wax vapor from this one. I am taking wax vapor, and the syringe there is wax vapor is white in color, deposits, then I am trying to catch the fire, how it burns or not. Let me try once again. Actually, air है ना. You can see, but sometimes it is burning. No, और एक बार लेते हैं. You can see the another flame. Oh, sometimes it is burning, sometimes it is not. That is, wind is something. No, it is not, right now it is not happening. What you can do is, that is some wind is there's too much wind, that's why it is not burning. Otherwise, you can try at home. AC का हवा से हो रहा है. Okay, let's put the, you can see here this syringe is, I have taken this one. In syringe is, in the syringe you can take the wax vapor, and that wax vapor separately can be basically burned in the flame, and wax vapor is burning in the with the flame. It can be done. This is air is coming. We are going to the next experiment. Wax vapor can be collected and burned separately. This is, there is some chemical reaction. It has been said by carbon dioxide so many times. So how easily you can prepare the carbon dioxide? That will be. So carbon dioxide is basically we are preparing from the जो खाने का सोडा बोलते हैं baking soda. So baking soda and vinegar, which is basically very much available. We are available in the home and kitchen. So with the help of these two, you are easily preparing carbon dioxide, and carbon dioxide is acidic or basic. Carbon dioxide acidic in nature, so it will basically with water it will give carbonic acid, and with the help of a litmus you can taste, or otherwise lime water it turns lime water milky, that can be tasted. Light on please. এটা দেখতে পাচ্ছেন না?
We are taking vinegar here.
ঘটালো ঘটালো। So vinegar has been taken and balloon in the inside of, just wait, inside balloon we have given taken the sodium bicarbonate, खाने का soda जो. Now I am putting, the reaction is very fast, so putting like this one. This is kitchen experiment, vinegar and आराम से आपको मिल जाता है.
Vinegar, how many of you have it at home? Yeah. So everyone has it. And baking powder or this, yeah. खाने का सोडा भी बोला जाता है ना? So it's, and washing soda is also there. You could actually take that also, but less of that. And you could do this experiment at home. But what all can you do in this experiment? You can actually take different amounts of baking soda, keeping the amount of vinegar constant, or reverse it and see how much of gas is formed. That is how you can do a simple set of experiments at home and make a journal of, actually record your observations and make a journal of it. Yeah. Thank you. Would you like to try this? So, anyone from there?
Slowly, slowly.
Inside the balloon we take sodium bicarbonate, because if you put sodium bicarbonate directly, the reaction is so fast, before after you put the balloon, all the carbon dioxide is gone. So inside balloon you are taking sodium bicarbonate. Lime water test, yes, lime water test you can show. Lime water रखा हुआ है क्या?
So how will you test it with lime water now?
Form a milky. Ma'am, when we will put that sample in the lime water, it will turn into a milky substance.
Clear lime. Yeah, clear lime water. What other tests can we do?
If we burn
It will extinguish.
sphincter, it will extinguish.
Should we try that? What else? Anything else? Any other way of testing it? You have litmus paper, no? You have blue and red.
Hello? Yeah. Any burning things can be brought near tea, it will be extinguished, that is okay. But we can taste the litmus taste or most rigid taste, acidic in nature. So this is.
Have you seen these in your school? Litmus paper. So what would happen with this gas? What will happen with this gas? It will turn blue litmus red. So let us have blue litmus, right? This one is the red one.
उसको थोड़ा सा भिगा लो थोड़ा सा भिगा लो.
Wet one or dry one? So let us wet it now.
Yeah.
And to test it?
No, पहले यहाँ उसको बंद करो.
So
Yeah.
how will we do it? Let us wait. Actually, we need to. Yeah.
So it is turning red. Yeah.
It's not very clear yet. You release it slowly on it. Let them do it. It is very simple to do. They can do it. See
Yeah,
the
it is
edges.
turning red, right.
See the
So this
edges.
way, a simple way you can taste this gas. Okay.
We could collect a little more gas and do it. You can actually try it out here. Would you like to try it out? Okay. So try it. Try it, and when it comes, you show it to everyone. Okay, we can go to the next one.
Next one. Okay, we can go to the next one. Next experiment. Okay, thank you, beta. Okay. Now.
Yeah, you can. And please show everyone from here. Hold it like this. Yeah, and take it out. How many of you have a lab at class 12?
Yes.
Do you have all this? They have it at home also.
You have your chemistry laboratory in your school. How many you have chemistry laboratory? As many. Okay.
And how many?
That's good.
How many of you do these experiments with your own hands? How many of you do it yourself?
This is a little less. So
Yes, the number has reduced to even less than half, right? So we believe that if schools have labs, then all the children should get the opportunity of doing these experiments with their own hands.
So this litmus became red, it is obvious, but the point we are trying to make is you can do it in school, possible in the laboratory, and if possible even some experiment we have chosen this experiment you can easily do at home. So from today's our aim has to inspire you to go for activity, and you learn theory or any hypothesis by doing some activity. That is the aim of this lecture, and we have tried our best to take that is one terminology, it is called कबाड़ से जुगाड़. आपके बाहर आसपास इतने सारे चीजें फेंके गए हैं, वहां से आप लेकर के सामान को लेकर के एक्सपेरिमेंट कर सकते हैं, उतना पैसा की जरूरत नहीं है. Next experiment we are doing for there are so many talk of hydrogen in the previous talk. Professor Maitro has done hydrogen, and let us how can easily we prepare hydrogen. And না ওটা ওটা তো আমরা দেখিয়ে দেবো ওটা एल्यूमिनियम फॉयल ले लिया. So we are taking a aluminium foil in a boiling tube, and then sodium hydroxide. So aluminium is a metal. We know that a metal basically which is placed above the hydrogen in the electrochemical series replace hydrogen from the acid. That is we know. But here we are doing two types of experiment. Aluminium foil we are taking, and but we are using sodium hydroxide instead of acid. First we are doing is sodium hydroxide. Aluminium is which type of metal aluminium is? But aluminium being amphoteric in nature, amphoteric material, it can replace hydrogen from sodium hydroxide, or it can replace hydrogen from acid HCl also. We are trying to produce hydrogen by using sodium hydroxide and aluminium. Aluminium foil is available at a house. Sodium hydroxide you have need to manage, and you can just we are putting aluminium foil and trying to check the whether hydrogen is produced or not. एबार इसको खोलो, इसको खोलो. ना बहुत गैस आ रहा है कहीं, इसको कॉर्क को टाइट करो, बीच में नहीं हुआ इतना जो यहाँ पर जा नहीं रहा है. ये काल वाला बना हुआ था, क्यों नहीं जल रहा है? नो नो नहीं 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 नहीं, इसमें जलाना नहीं है, इसमें जलाना नहीं, गैस आ रहा है और आग लग जाएगी. নিডিলটা তো খুলে গেছে ওখান থেকে. না নিডিলটা তো খুলে গেছে ওখান থেকে. সরাও সরাও. ভেতরের দিকে ঢুকাতাম না.
injection bottle. You get a cork there, we took a refill and we covered it tightly. Here we have taken a valve tube, a cycle valve tube. So this comes as a replacement of the rubber tube or the plastic tube. And then here is the injection. So I'll keep trying this. Once it becomes successful, we will show it. Because sometimes, mainly this particular vent is not helping us, because yesterday in the lab when we tried it, it was working very well. Even at home and even at different places, we have been doing it this way and somehow we could actually get it. But this is a prototype of the experiment setup that we use in labs. You could always have this kit with you. Oxygen की तैयारी.
ना वहाँ से गैस लीक हो रहा है. Okay, we proceed to next one. It can be tried at home, but now preparation of oxygen. This is also a simple process. We will be heating KMnO4 and that will give oxygen, and that can be collected by the downward displacement of water in a test tube, just like here the diagram. Let us try this one by heating potassium permanganate. अब आ जाओ वो यहाँ पर ऑक्सीजन पे करो. सीधा उठा छोड़ दो. और भी डाल दो. राइट. Switch on light, please. पानी बकेट टे टिके आना, बकेट टे टिके आना. आप इस साइड आ जाओ.
You need that small bottle. This one.
Now I have to put water. सावधान, careful. उसको छोड़ दो वहाँ पर बाल्टी में छोड़ दो. वो वाला छोटा वाला नहीं आया क्या? आज जो छोटा वाला कर रहा था? No, this one. इसको हीट करना. So gas bubble is coming and it is being collected by the downward displacement of water. हीट करो, आप हीट करो. We are heating KMnO4 and oxygen is collected. Yes, oxygen is coming out and it is being collected by the downward displacement of water. Okay, না দেখছি তো. Oh. नहीं, अभी आपने ट्यूब बाहर निकाल लो. Yeah, yes, oxygen it is just like, yeah.
Yeah, we have to do that again. So we have to repeat these experiments again.
No, that is sufficient. That is sufficient. We are collecting once again oxygen by heating KMnO4. उसको हिला हिला के, yeah, oxygen is coming out. इसको इसको आपने ओके अच्छा ओके
Has the gas collected? Yeah. Now maybe light off मत करो. हाँ. अगरबत्ती ready रखा? Don't keep your hand in front. Don't keep your hand in front. One. नहीं, ऐसे दिखेगा. 1, 2.
ah this is okay so we can do this experiment easily at a home also with the chemicals, only chemicals you require in KMN, potassium permanganate, easily available medicine shop. So next experiment is one, this is called ammonia preparation, and it is well known fountain experiment. We will try over here. It is very exciting experiment. You can see the idea of ammonia preparation is ammonium chloride and NaOH. That is, ammonia is evolved like this in inverted conical round bottom flask, and there is a syringe attached over here. From this syringe, what idea is, ammonia is highly soluble in water. So you put this water and ammonia is soluble, a vacuum is created. This is under atmospheric pressure. So when inside vacuum is created, through this tube, we have kept phenolphthalein solution over here. Phenolphthalein solution will go up, and ammonia is basic in nature. So phenolphthalein will be giving some color. क्या color देगा? Ammonia basic in nature. Phenolphthalein will give which color? Phenolphthalein will give which color over here? So this is the idea. You see how it goes. इसमें तो लाइट ऑन कर सकते हैं ना? हाँ, लाइट ऑन करो भैया, एक मिनट. ओके. So ammonium chloride has been taken and this is the sodium hydroxide. This is the hydrogen now burning. Yeah, the hydrogen is burning now. It's a homemade apparatus, cycle wall tube, खाली refill. वो आपने ये दिस इज द मेडिसिन बॉटल, मेडिसिन दुकान में आराम से मिल जाते हैं. उसमें आप अपना apparatus घर में आराम से बना सकते हैं और ये हाइड्रोजन को आप जला सकते हैं. दिस इज द हाइड्रोजन इज बर्निंग from aluminium and sodium hydroxide. Aluminium is producing hydrogen from sodium hydroxide. This is a homemade apparatus. घर में आराम से आप बना के ये टेस्ट कर सकते हैं. But be careful because hydrogen catches fire. ओ गैस निकल रहा है. इतना पानी काफी है. Be careful, be careful. इसको बेटा टाइट करना है ना पूरा बटन कर. Let's see how it goes. It was happening in the laboratory yesterday, but it no, अभी नहीं. इसके ऊपर उंगली लगा देना. जब पानी डालेगा ना उंगली लगाना पड़ेगा. So ammonium chloride and sodium hydroxide being heated, ammonia is produced. So we will put some water inside. The ammonia will be dissolved. A vacuum will be created, and through the pressure difference, phylloxanil will go inside. That is called fountain experiment. Let's see how it goes. पुट वाटर. उसमें उंगली मत छोड़ना, उंगली अंदर जाके छोड़ेगा. वाटर जा रहा है, डालो वाटर, डालो और डालो. ना ना नहीं, अभी वाटर डाल दो पूरा. निकल रहा. हाँ हो गया. यहाँ से क्यों निकल रहा है? This is the fountain is okay. Fountain is okay. थोड़ा सा प्रेशर को हटाओ. No, this yeah. Okay. Yeah, it is. Pink solution is going up. Ultimately, it is expected that it will go up to that, and there will be a fountain outside that. But if there is something gap, any leakage is there, then there is a problem. Here is in this case, yes, there is some leakage. So this is a very beautiful experiment. Again, it is rising, getting rising. Can you see this? One it is rising, rising. थोड़ा space दो, थोड़ा ऊपर, it's still ऊपर जा. Yeah. That is the expected. It will be a beautiful fountain. Actually, there is some leakage over here. Yeah. You see the. It's a beautiful experiment to demonstrate, but it will be difficult. There should not be any leakage from anywhere. So the science is very simple. You have created a vacuum by dissolving ammonia with the water and inverted it, and there will be a pressure difference. This is because this phenolphthalein solution under atmospheric pressure, and with the pressure the phenolphthalein will go up, and it will be react. Ammonia is basic in nature, so that will be pink in color. This is the idea, and we will go to the last experiment. Last experiment is this one, chemical traffic light. Chemical traffic light, this is always advised that whenever you cross a road, whenever you have to move, so you have to be basically directed by the traffic light. So this chemical traffic light has been designed. Let us try this one. इसका ऊपर कॉर्क देना, इसमें तो निकल नहीं जाएगा, नहीं, बट हमारे बॉटल में कर सकते हैं. बॉटल लेके आया. अब आपने ये दो बीकर लेके आओ. ये दिस इज द लास्ट एक्सपेरिमेंट बिकॉज दो फ्रेश बीकर ना. ओके, चिंता उतना আমাদের বটল हो जाएगा. एक में हाइड्रोक्साइड, सोडियम हाइड्रोक्साइड, और एक में यहाँ पर सोडियम हाइड्रोक्साइड. So we are taking the two beakers. In one there is glucose. Now bottle ওখানে sodium hydroxide. In one bottle we are dissolving sodium hydroxide and bas. Then glucose D from here. So this is the glucose D. बाजार में available है. पहले पानी dissolve कर लेते हैं. हाँ, ओके, थोड़ा सा पानी. So we are dissolving sodium hydroxide. और थोड़ा सा पानी डालो. बस. इंडिगो मैं लेके आया, मेरे पास है. नहीं, हमारे वाला करो. ये अच्छा है, मैं अमेज़न से लिया. So this is indigo carmine. This is available in Amazon. We have purchased it from Amazon. Okay. So this is indigo carmine. Is a compound of indigo disulfonic sodium sulfonate sodium salt is a कोई एक फ्रेश रॉड था, बहुत ही कम लेना है. इसमें एक पिंच डाल देता हूँ, एक पिंच लेना, एक ही पिंच चाहिए। नो नहीं होगा, नहीं होगा, इसके बाद कोई नहीं, मतलब बहुत ज्यादा हो गया। और एक भी कर लो सर, इसमें से थोड़ा सा इसमें डाल दो, थोड़ा सा ले लो। थोड़ा सा no, no. Okay, which color it is? Can you see this color? Which color? Okay, it is indigo carmine, compound of indigo or disulfonate sodium salt. So we will be taking this indigo carmine blue solution in the वो वाला कहाँ है? Okay. बस इसमें छोटा हो जाएगा दोनों का मिला के वाटर, बड़ा ले लो। We are taking indigo carmine solution, water soluble. ग्लूकोज डाल और थोड़ा सा डालना, बस डाल। ना 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 ठीक है, ठीक है, बस now we are adding, this is your glucose, glucon D and sodium hydroxide solution. We will be putting over here. What is the color now? Okay, okay, enough. Now let us wait. उसमें ढक्कन लगाओ, just wait, उसमें रखो। No, not sucking, not sucking. Now, any change in color you are observing? क्या डालेंगे? हाँ थोड़ा डालो, नहीं अभी हो रहा है। Any change in color you see? नो और एक बार ये लो, और कॉनिकल फ्लास्क लो, हाँ इसमें लो, इंडिगो कार्मिन थोड़ा डालो, बस 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 बस। Yeah, you can see that change the color. Change the color. It was from blue to green, then it is red, then finally see what happens. Now say, जोर से, again the third color came. Again red color signal not going, just like traffic light. Again say, a green color is a traffic light giving signal that you can go. Then again it is red color. Again say, There's a green color, this is the oxidized form, and when you go the glucose sugar reduces, then this red color comes. Again you shaking means you are giving oxidizing the things, oxygen, again it is green. So that is all from us. Green signal we have got, so we can go move. Thank you all, and I would like to thank Professor Ganguly for inviting me and giving this opportunity. So main aim was to inspire you for doing activity, for learning any hypothesis or any theory. So do activity and get fun of chemistry. What you have seen in the previous lecture also, it was a wonderful lecture. So I'd like to thank Professor Ganguly for inviting me. I'd like to thank Dr. Patra, organizing secretary, for arranging and good hospitality. And I'd like to thank all our volunteers here for their kind support and help. So thank you all. Okay, all the best. Thank you. Good luck.
Thank Professor Amlan for so much hard work they have done. They have brought chemistry lab to you. All these experiments actually we did in school when we were in 9th or 10th or something. All these oxygen production and many other things that he tried to show, and he has compiled all that. It takes time and lot of energy on his efforts, and showing with low cost things like cycle valve, etc., how you can make simple devices. So let's give him a big hand. And I think thanks Snigdha also, who has been working with Educational Foundation to improve. They train the teachers, they go to different schools and train the teachers. They also set up low-cost experiments, etc. So let us thank. If you have any one or two burning questions, you can ask. One or two questions. Professor Rajesh Prasad.
No, I want to thank Professor for giving a very nice demonstration, and many of the demonstration were initially not working.
Yes, sir.
Yeah. So that was also a very nice demonstration. I think students should take the inspiration.
Right.
That it's not easy to perform the experiment. जादू नहीं है कि एक लिया और मिलाया तुरंत हो गया. And you have to struggle, you have to work hard to get the right results. So that demonstration automatically happened because some of your things were not working as you expected.
Right, sir.
So,
if your drain gets clogged, you first use the plunger. If it doesn't work, what do? Drain-X. You use something called Drain-X, which is the more common one. That is nothing but a mixture of flakes of sodium hydroxide and aluminum shots. And that you can buy from stores and put it in water, it evolves hydrogen. That might make your life much easier than having to take sodium hydroxide, aluminum foil and mix it. You simply mix it and hydrogen comes out.
Thank you, sir. Thank you. We will try
next time.
And in return, sir, I want to give one thing you too.
Oh.
This is we look for phenolphthalein. Phenolphthalein. This is a Laxina tablet available in 10 rupees. It is gift to you, sir.
I'm not going to take it orally.
And actually you can prepare the phenolphthalein solution directly in water using this tablet. Just dissolve it in water and you can.
Okay, is there any student who wants any burning question? We'll close for tea, and then after that we have a talk by a very, very eminent personality, Professor Ram Gopal Rao. He is the Vice Chancellor of 5 Birla institutions, Birla in BITS Pilani, BITS Dubai, BITS Goa, BITS Hyderabad, and BITS one more somewhere. So he is the Group Vice Chancellor. He is an eminent electrical engineer and nanotechnologist. He has all the awards of India, including the Infosys Award. He was director of IIT Delhi and earlier from IIT Bombay. And he is going to speak to you on nanotechnology and other things. So you have a quick tea. You have 15 minutes. Please come back in 15 seconds. Please, 1 minute.
I would like to request Professor Ganguly to felicitate Professor Das first, and then we can have the break.
So please come back in 15 minutes after the tea. So we have the talk as scheduled at 5:30. So Professor Rao is already going to get.
Hold.
Professor Rao, another 5 minutes we'll start. Just give 5 minutes. Please settle down. We'll start in 2-3 minutes. Why don't you come to this side? Come to this side. Okay, please settle down. We're starting. So this is the last talk of the day, and really we are very happy to have Professor V. Ram Gopal Rao, who is the Group Vice Chancellor of BITS Pilani and former Director of IIT Delhi. So Group Vice Chancellor means he is the Vice Chancellor of 5 campuses of the BITS universities. They are located in different places in India, headquartered at Pilani, and then they have Goa, Hyderabad, and they have a campus in Dubai. And Professor Ram Gopal Rao is a very internationally acclaimed nanoelectronics researcher. He was director of IIT Delhi till 2022. Earlier he was a professor of electrical engineering at IIT Bombay. He is known for his work in nanoelectronics and in sensors. He has over 480 research papers and 50 patents, which include 20 US patents. 15 of his patents have been licensed to industries for commercialization. And his patent on CMOS-based technology has been developed in his group, is used in hundreds of millions of integrated circuits sold all over the world. Professor Rao is a co-founder of 2 deep technology startups at IIT Bombay, NanoSniff and SoilSense, which have successful commercial products in the market. Besides his education and research activities, Professor Rao is also well known for establishing major nanoelectronics programs in the country. For his research accomplishments, Dr. Rao has been elected a Fellow of IEEE, a Fellow of the World Academy of Sciences, the Indian National Academy of Engineering, and all the 3 science academies of the country. He has received the Shanti Swarup Bhatnagar Prize, which is the highest prize in science and engineering in our country. The Infosys Prize, which is the highest valued prize given by our country. The IEEE EDS Education Award, which is the highest international award bestowed by IEEE Electron Devices Society for Education. J.C. Bose National Fellowship given by DST, and many others. Dr. Rao has delivered over 200 plenary keynote and invited lectures all over the world. And apart from this, I know him personally. He has been a dynamic leader, and he is a dynamic leader, and he has very disruptive ideas which he brings to any institution that he serves. He has taken IIT Delhi to nearly the top position in our country. It is fighting hard with IIT Bombay. And I welcome Professor Rao to talk to us on ecosystem for deep tech innovations in academia. What is the role of interdisciplinary or multidisciplinary research? Professor Ram Gopal Rao.
Thank you very much, Mr. Dalvi, for the introduction. Let me share my slides. I think screen sharing is disabled.
Screen sharing allow kar do. You can try now, Professor Rao. So, you try. So, you have 50 minutes, then we'll take some questions. 45 to 50 minutes. Okay.
I think since it's mostly children, I will take less time. We will have a little bit more discussion. So, can you see my slides now?
Yes, yes, we can see.
Okay, thank you very much for the introduction. And as Professor Ravali mentioned, I served at IIT Bombay for 18 years, IIT Delhi for 7 years, and BITS Pilali now for the past, I would say, 8 months or so. So most of the work that I have done is from IIT Bombay and Delhi, mostly from IIT Bombay, but somewhat from IIT Delhi too. And so I will share with you what exactly is engineering. I think I know that many of you eventually want to become engineers. So therefore, before you get into engineering, before you even think of choosing your career, I think I will tell you, what exactly is engineering all about. What are you expected to do as an engineer, and what do we all do in IITs? We are all engineers in IITs, and what do we really do in IITs as engineers? I am an electrical engineer by my training. In all these institutions, I serve in the electrical engineering department. So engineering, first of all, is not about electrical, mechanical, civil, all these disciplines that we talked about. That's not what is engineering. These definitions have been evolved more for administrative purposes, but beyond that, engineering is all about finding optimal and sustainable solutions to society's current and future problems. So, therefore, engineering is all about finding solutions to problems. So, that's the reason why engineers are often seen as the gods, right? To create things where none existed. If you see a problem, you look up to an engineer to solve the problem. So, that is what engineering is all about. Other disciplines, other professions have other sort of similar objectives. Medicine, for example, is treating patients and that kind of thing. But engineering is all about solving problems. So that's what you must keep in mind when you think of an engineer. The software engineers also do something similar. So most of the jobs in India are for the software engineers. They write code, they make computers interact with humans, they make computers solve problems. I think that's a kind of a job which is very specialized in software engineering. But some of us are not software engineers. We actually create products and we I will show you soon. We try to solve some of these, pressing issues that you find the day-to-day kind of stuff. In India, for example, if you are looking at higher education, after you are 12, you will all enter the university. There are over 1,000 universities, 1,043 you may ask, check on the university website, out of which there are 135 institutions of national importance. So these 135 are the institutions like I said, one of those institutions of national importance. I showed in some of these institutions like Day-1. So these are all known as the institutions of national importance. ISER, IITs, IIMs, right, and NIPERs. So these are all they all under the institutions of national importance. And then if you also look at the higher education in terms of gender distribution, meaning how many boys are there, how many girls are there in our universities. One thing we should be happy about is it's actually 50-50. Right? There are as many girls as boys. Therefore, university education doesn't mean it's mostly boys or anything like that. When university education is 50% girls, 50% boys. So, which is a good sign. We have at least a good gender parity when it comes to our higher educational institutions. In all these in universities, we offer undergraduate programs, we offer masters and PhD programs. While undergraduate students learn and look for a job, it's the PhD students who actually do the research. And if you look at the number of PhD students, 2019-20, we had about 200,000 PhD students. So these are the people who actually do research and get their doctorate, doctor degree. And but it's also growing at 10%. So we currently have something like 250,000, almost 300,000 PhD students. Right now serving doing research in all our academic institutions. So these are the people who write publications, who discover new things, who keep on updating all the knowledge that exists in the world. And it's not just in India that we have these PhD students. Every country will have a large number of PhD students who will always be researching new things, making new discoveries, finding, understanding things that exist in the nature, and that is how all the textbooks and everything get rewritten, every 5 years or every 10 years. If you are looking at a textbook that was written 50 years ago, right, it will all be outdated now. You don't even want to read a textbook that was written 50 years ago, maybe except for one or two classic kind of textbooks. But all the modern textbooks are rewritten every 10 years, new editions come about. So how do those new editions come about? It's all the research done by these PhD students, who keep updating this knowledge year after year, new things are formed. Therefore, all these textbooks are continuously rewritten every 10 years. And that is how we are always abreast of whatever is happening in the world. So therefore, all the credit for new knowledge, new understanding, all of that goes to these PhD students and their supervisors. So every PhD student will have a supervisor, and all professors act as supervisors. In addition to our regular teaching activities, we also guide these PhD students. So therefore, all these PhD students work with faculty members, and they all together write papers and do research. That's how the research ecosystem is built in the country. India is actually doing very well. India currently ranks third in the world in terms of research. Now after China, then US, then comes India. Right? We do more research than Germany, Japan, Russia, whatever countries you name. We actually do more research than many of these countries. So we are ranked third in the world when it comes to research. And when you write a paper, others cite our papers, others refer to our papers. Therefore, oftentimes the quality of research is judged by how many people have cited our papers, or how many people have referred to our papers. So in terms of citations, we are ranked 7th right now. India now is not only publishing lots of papers, not only doing a lot of research, but we are also doing research which many people value and many people learn from what we do world over. Therefore, we are scientifically a very strong nation. We have a strong culture of doing research. But then if you look at the next number, which is 48 for innovation. Now, what is the difference between research and innovation? Research is all about, generate new knowledge. Research is all about understanding things where such an understanding does not exist, right? Whereas innovation is about using the knowledge to solve a problem. I might have, somebody has discovered Bernoulli's theorem for, how objects fly and how you can make objects fly and all of that. But using that theorem, somebody actually built aeroplanes, right? So therefore, that is innovation. So why do you have all these physical laws, lot of research that is being done? Some people who are mostly engineers who use that knowledge generated by scientists, right? And then apply that knowledge to solve a problem. Right? Somebody wanted to fly, therefore using all the physics that was available at that time, and people made aeroplanes and made those aeroplanes to fly. So therefore, that is what is innovation. Innovation is all about application of knowledge. Knowledge generation is what happens to the research, and application of that knowledge is what happens to the innovation. And it's a job of engineers who often find solutions to problems, but they always stand on the shoulders of scientists. Without good physics, without good mathematics, without good chemistry, there is actually no engineering. Engineering will be like, some black magic or something, without all these, nice sciences that are supporting the engineering. Therefore, science and engineering are equally important. There is nothing that, this is more important, that is more important, or anything like that. So, out of science will come engineering. Because scientists discover all these, understand the natural processes, understand, come up with theorems, come up with theories, and then engineers make use of that to actually apply it to a real life situation and develop a technology or product. And then these other things are not really, very important for you. But another thing is in the industry, academia collaboration, we are not doing very well. That is one major challenge that we face in India, which is why we are not taking innovation. If you notice, we are third for research, then we are doing a lot of research, but we are not applying our own knowledge to solve our own problem. That's why we are not yet of this. In all these countries, in between, learn from the research that we do in India, use that knowledge, develop new technologies, new products, and everything new, and sell it back to us. So that is one major challenge that we are facing, and that is what the is trying to improve on. So can we apply this knowledge to solve problems more effectively, more efficiently? So we want to be, if we are third from the research, we also want to be on the top 5 countries for innovation, which is unfortunately not true. The reason why it is not true is because academia and industry don't work with each other very well in this country. These are all, historical reasons, cultural problems. So industry works in its own way, academia does its own work, and they are not collaborating with each other. The countries which are very high on the innovation have very strong academia industry collaborations. But in the absence of that, unfortunately, India, doesn't develop enough technologies, and we tend to import a lot of these consumer electronics, these consumer products, and all of that because the academia and industry are not working very closely together. So this is one thing government after government is trying to solve. We are all, talking about it, we are all writing about it, but it takes time. It's a cultural issue, that we need to overcome. And of course, I told you India ranks third in the world and all that, and India is also one of the fastest growing countries when it comes to knowledge generation. All of that is good, but like I told you, the biggest challenge is, how do we translate this knowledge into wealth, right? So when you generate new knowledge, you apply that knowledge, develop a new product, and people buy those products and pay money. So that is what is knowledge to wealth translation. So that knowledge to wealth translation is where we currently lack in the country. Like I told you, one of the biggest reasons why that knowledge to wealth translation is not happening with academia, lack of academia industry collaboration. Otherwise, in a country like US, which is one of the best, or rather the best in the world when it comes to academia industry collaboration, academia generates new knowledge, understands new things, industry comes and picks up that knowledge and using that knowledge they generate a product, they develop a product, and then they sell it to all over the world. So that is how US is able to take a lead in generating so many new-age companies which were not even existing before. In India, that process is beginning to happen now. But right now the knowledge to wealth translation is where we lack. Otherwise, we are as good as any country in the world when it comes to doing research. Now, having said that, as I told you, so I told you some of that. You also must be looking at all these startups. Now we solve the area of startups. Even in the schools now, many of you may have got ideas, may have even started companies. That's what is now becoming a very fashionable thing to do, having the startup kind of thing. And if you look at India, there are almost like 75,000 startups or something like that. But there is a term called unicorn. Unicorn is a startup which is valued at $1 billion, 8,000 crores. Any company whose valuation is 8,000 crores is called a unicorn. And India has 100 plus unicorns. Today that number is something like 108 unicorns. So 108 unicorns now, these are all new companies. Meaning they found a problem in the society, they started a company to solve that problem, and then by solving the problem, they were able to generate revenues, they were able to sell the solution to a large number of people, and they make money out of that. And so that sort of number of companies which have grown to 8,000 crores kind of a valuation, there are hundreds of companies like all of these are the kind of companies. You must be the Zomato you have heard about, and then the Zomato is one such unicorn, Swiggy is another unicorn, Big Basket is one such unicorn. So there are a lot of such companies you may be able to identify. Oyo is another unicorn. So there are a lot of such unicorns now in the country. So this is a new phenomenon. This was not there when we were children. This is something that has happened in the last, I would say, 20 years or so. In the last 20 years, maybe 2003, 2004 onwards, many young people such as you, thought, asked the question, if there is a problem, why can't we find a solution and then build a company to solve those problems? Once they started asking such questions, many of them have come forward and built these companies out of nowhere, from scratch, and then grown those companies to a level where now they are all valued at 8,000 crores or so. So that is there are 8 such companies right now in the country which are actually doing that. So that is a process. And then while we also write lots of papers, we also file many patents. Today what is very important is, if I have a new idea, I have an idea to solve, let us say, a pollution or measure pollution in Delhi, right? Or I have an idea to solve the air pollution problem in Delhi. If I have an idea, what do I do first? Of course, I do research on that. I find out how to solve the problem, how to measure air pollution, what do I need to do to solve the problem. So I try to identify solutions to that problem. And once I think that I have found a good idea, once I have got a good idea to solve the problem, I go and register that idea on my name. Meaning, then I can go and register to the patent office that I have this problem, I have a solution. So this solution I want you to be registered on my name. So once the patent is registered, on your name, then nobody else can copy that. If anybody else copies your idea, you can go and file a case against them. And then they have to pay you money, because they have copied your idea. So this is what is known as the intellectual property. Like you own, buildings, cars and land and all of that. Is today the generation of intellectual property. An idea which you have got for the first time, you immediately go and file a patent, register a patent, and that idea then belongs to you. Nobody can copy that idea. Anybody will copy that idea, will be sued by you. And you can, people who have made millions of dollars by suing people who copy that. Therefore, this is in the current age, it's very important for all of us to protect our ideas, to take. Like earlier mentioned, I have over 50 patents, right? And he also mentioned that I have 20 US patents, because I thought that my idea is also useful in the US, but the problem exists in the US also, which I am trying to solve. I also went to the US and filed a patent there. So now once I have a patent in the US, then nobody in the US can copy that idea. And because I have a patent in India, nobody in India but they cannot sell that idea either in the US or in India, because in these countries I have protected my intellectual property, my ideas, and today many startups, for example, file patents in 100 countries because they think that their solution may be useful in 100 countries. When they think that their solution is useful in 100 countries, they go to all these countries and file a patent. Right? And then what it means is, in all those 100 countries, they have protected their idea. Nobody in those 100 countries can copy their idea, sell it. So no one can do that. But many of us, very often we researchers, filing patents in 100 countries will cost a lot of money. So therefore we only file selectively patents in countries where we think there is a very high chance of somebody copying our idea. I don't want to copy, file a patent in Pakistan. Why would I care? Nobody in Pakistan will be able to, generate the idea that I have. Therefore, I don't care so much about, so many countries. But in some countries, I am worried that somebody can get the same idea, develop the same solution. So therefore, that is how this patenting process works. And India is also filing more and more patents. We need to file more patents than what we are doing right now. But now that awareness is there and many people are filing patents. And in fact, you can also file a patent. You don't need to be a doctor or engineer or anybody to file a patent. If you think you have an idea, right, you can actually file a patent. And it doesn't cost much money to actually cost a few thousand rupees to file a patent. And anybody can register their idea and then get a patent. And I will also tell you that it's very, very important to actually engineering, what it is all about. Engineering is all about creating new solutions, creating products, right? So that is what engineering is all about. Engineering engineers are the creators. Right? But if you look at the scientists, for example, they are the ones who discover new things. They generate the new knowledge. And then we engineers go and use that knowledge and then make a product out of it. And that's also the reason why, engineers, scientists file a lot of patents, because they have been discovering all the time a lot of new things as part of their work. If you look at this mobile phone, right? I mean, today you can buy this flexible phone, Galaxy Z Fold and all of them. You must have seen those advertisements now. If you look at these mobile phones, there are at least a dozen Nobel Prizes. Behind a mobile phone, which is an engineering marvel, right? The most complex thing ever created probably is a mobile phone, which is pretty complex actually to build. Now, but behind this mobile phone, there are 1 dozen Nobel Prizes. Now, Nobel Prizes are not given for engineering. Nobel Prizes are only given in chemistry, physics, those kind of areas, and biology, medicine. But there are no Nobel Prizes for engineers. Engineers that way don't get the Nobel Prizes unless they have worked on some science related kind of problem. But for this mobile phone, there are so many scientists who have worked on this mobile phone technology. The display got a Nobel Prize, camera got a Nobel Prize, wireless technology got a Nobel Prize, battery got a Nobel Prize, memory, processor, polymers, everything in this mobile phone has got a Nobel Prize. And then somebody, engineers have come together and put all of those innovations together, all of that knowledge together, and actually created a gadget which we all use currently as part of our day-to-day life. So that is a connect between science and engineering. So it is never that if you are doing science, you are superior, if you are doing engineering, you are superior. There is nothing like that. If engineering is about solving problems, the scientists are the ones who actually provide the knowledge for solving those problems. So these scientists and engineers therefore need to hand in hand. And if you are a good mathematician, you should become a great mathematician. If you like mathematics, you should become a good mathematician. If you like chemistry, you should become a good chemist. Instead of becoming a lousy engineer, it's always good to become good in whatever subject that you like as part of your school curriculum. So therefore, when you look at the problems now, there are many problems in India. Right? If you just look around you, right? There are so many people who are unemployed, and agriculture, some of you may be coming from agricultural communities. There are so many farmers who don't make enough money. Right? There are so many farmers who fight in many states, and that's because farmers are not making enough money. And then healthcare, diagnosis is a problem. So many people die because of heart attacks and things related to the healthcare related issues. Can we develop new diagnostic technology? For example, cancer. If I can develop a diagnostic tool which can detect cancer very early on, right? I can prevent a cancer. I can then help diagnose the cancer very early. Therefore, the treatment becomes possible. Otherwise, if the cancer spreads to all the organs of the body, then it becomes very difficult to save lives. And whereas if I have a diagnostic tool which can detect cancer very early, then I can save a lot of life. So developing those detection technologies, those diagnostic technologies, is again what engineers do. That is what we call the biomedical engineering. Biomedical engineering is an area where engineers go to develop such a diagnostic kind of technology. And then agriculture. Agriculture will require people with very different disciplines to come together because it doesn't fall under one single discipline. We often require electrical engineers, chemists, agricultural scientists, so many different kinds of people coming together to solve some of these kind of problems. And then the security, you see that when you go to airport, there are so many places to go to the security checks, even in railway stations, you see a lot of security. You see, the security people bringing sniffer dogs, right? The dogs also come and sniff, they are also sniffing people, the bag, to see if anybody is carrying anything suspicious. Because a sniffer dog has a very good sensitivity of smell, and it can sense things which are a million times better than the humans. So, and they train the dog to sniff explosives, or they train the dog to sniff narcotics. So that once you train a dog for one particular smell, and you can use the dog to actually detect the people, to find out if you are carrying any of those kind of materials. And another question you can ask is, why a dog? Can they develop an electronic nose, for example? So that is possible that we can develop an electronic nose which can actually do the sniffing, and that is what some of us are actually trying to do. Energy, right? And we need to have newer sources of energy, which are more renewable in nature. So and water, can you save water? Because India doesn't have enough water resources. We have 4% of the world's water resources, but 18% of the world's population. So we need to be saving a lot of water. So, but again, in agriculture, where a lot of water is used, can you reduce water usage in agriculture by putting sensors there? Whatever the crop needs, you put only that much of water, right? And you don't have to put any more water than what the crop actually requires. And that will require sensors. There you can sense the soil moisture and tell you that now I don't have to, I can turn off the pump because the soil moisture has already reached a level which is sufficient for that particular crop. So, but that will again require sensors, and that is again what engineers can develop in collaboration with scientists. So that is how we actually do things. So this is how I as an engineer have been working. I also do a lot of other things, but I have been looking at developing solutions to problems. Right? So now as an engineer, once along with my students, once I want to develop, once I decide to develop solution to a problem, then where are the problems? You need to also understand and identify the problems. So we identified one of our very first problems as developing a diagnostic kit for a heart attack. We asked ourselves the question because very often you find a lot of people dying because of heart attacks, or struggling because of heart attacks. So we asked the question, can you predict heart attack? If somebody is having a chest pain, right? Can you do some simple blood test and then say that this person might have a heart attack sometime soon? Or if somebody is facing feeling uneasiness and all of that, can you do some simple test using the blood sample and say that this person might actually have a heart attack in the next 1 month or in the next few days or even in the next few hours. So if you can predict heart attack, based on the uneasiness and all the symptoms, you can actually save a lot of life. Because once somebody has a heart attack, it becomes becomes very difficult because then you need to take the person to the hospital in the shortest possible time and all of that becomes tough. But if I know that somebody might have a heart attack, then you go and get admitted in the hospital so that they can actually prevent the heart attack from occurring. That is what was the kind of technology that we wanted to develop in Bombay. And then how do you detect heart attack? The way to detect heart attack is there are certain proteins in the blood, right? By measuring these proteins, you can actually know, when somebody is going to have a heart attack. These proteins are troponin I, CKMB, myoglobin kind of markers. If somebody is undergoing any heart-related problem, right? These markers, these protein concentrations rise like that. And then by monitoring these proteins in the blood, you can actually tell whether somebody is going to have an attack. So that is what we started to work on. But how do we develop it? So once the problem is decided that I want to predict heart attack, like a few hours before or a few days before, then I start to look at what do I need to do to actually detect that protein in the blood, with which I can diagnose the heart condition of the heart. I take the blood sample. I filter the blood sample because blood contains no need for detecting those proteins. But so many things can interfere with the protein detection. So you filter out all those red blood cells, white blood cells, and all of that in the plasma. We need a filter on the chip. Right? It has to take in the blood. It has to review that plasma, and then you have the biosensors. So for different proteins, you could develop different sensors, integrate them. Now this entire thing needs to be disposed of. So this is a chip where you put a drop of blood, wait for let's say a few minutes, and then there is a small tabletop instrument into which to insert this chip right after a few minutes, and then this tabletop instrument will display the concentration levels for those markers, which doctors can say that your troponin is high, you better get admitted, or something seems to be wrong with the heart. We need to observe your heart condition. That is the kind of a decision that the doctors will be able to take based on this disposable technology. So we started working on it. What is the platform that we work on? We developed this tiny cantilever structure. These cantilevers are exactly like cantilevers, fixed at one end and free to move at the other end. Where the lever is something which is reached at this end, and then this cantilever can meet at the other end. Right? You make this tiny cantilevers, you put now receptors here which can bind the protein in the blood. Right? What are these receptors? These are typically antibodies. You put antibodies on this cantilever, and then these antibodies can bind to the corresponding protein. So when I immerse this entire chip in the blood solution, right, in the plasma or serum solution, then those antibodies will bind the corresponding protein. So there is a reaction happening on the surface of the cantilever. Now, how small are these cantilevers? You can't even see them with the naked eye. If I were there, I would have brought for you those chips and show you. You actually need a microscope to see those cantilevers. What is the total length of this cantilever? The total length of this cantilever will be the diameter of human hair. These are like 50 micron, 60 micron. In fact, we even make 5 micron, 10 micron long cantilevers, meaning 1/10 the diameter of human hair, not the length of human hair. The diameter of human hair, 1/10 of that is the entire size of this cantilever. So they are also tiny. And when they bind this protein, the reaction occurs, and when the reaction is occurring, there is a stress that gets developed, the cantilever bends. When the cantilever bends, we actually put a piezoresistor there. What is a piezoresistor? When the bending happens, the mechanical force, it converts that mechanical force into an electrical pickup, a change in resistance. Therefore, when the binding is happening here, the binding is what we detect as a deflection. The deflection is converted into an electrical pickup. So, anytime there is a binding happening here, we detect it electrically as a change in the electrical current. So, that is the kind of a cantilever. So, you make these tiny cantilevers, you can see with the naked eye, and we functionalize them with antibodies, and when they bind to the protein, then we detect the reaction using electrical kind of instrument. So, that is what we do with the platform that we develop, and then we do a lot of research on developing that platform, binding it to proteins. So, a lot of things we do here. So, this is all research, right? So, whenever I do research, I publish papers. As you can see, the Journal of Applied Physics is one of the top journals. So, I published a paper here. But I also, if there is a good idea there, I also file a patent. So I file a patent, I also publish a paper. So once I file a patent, right, even if I publish, nobody can copy my idea. Therefore, we first file a patent and then we write the paper. So that's how we do research. And a lot of research has happened there, and a lot of papers we wrote, a lot of patents we filed, and finally we developed a technology where this is how the prototype looks like, and this is actually the instrument that we developed which can detect these artifacts. So this is how the chip looks like, where you put a drop of blood, and this is the instrument to which the chip connects to. And as you can see here, this is how the protein concentrations are increasing with time, and that's because somebody has a heart condition is getting worsened, and that is what this actually signifies. And that is how doctors can diagnose the heart condition and save patients. That was one project we did. And then how do I commercialize it now? I work as a professor in an IIT. How do I commercialize it? So we started a company, right? In now we are so Government of India policies and IITs policies. So we can start our own company. So I started a company myself. We are along with my students called Nanoscale Technologies, and we transfer the technology to them for the further commercialization. So this is how some of these technologies do like. And then once I developed the platform, one of the problems that happened around that time when I was working on this was, so there was a bomb blast in Pune, right? And there was a terrorist security problem, and somebody put a bomb, which exploded, and then some people died. And that is when some security people came to me and said, can you develop a sensor to detect explosions, to track explosions? If somebody comes and puts a bomb in a bus or in a plane, can you develop a sensor which will immediately tell me that there is a bomb there? Right? How do you do that? The way to do that is like a dog. A dog can smell explosives. In fact, at airports and all of that, even in railway stations, if there is an unidentified baggage, if there is a bag which is with nobody claiming that, then security people immediately get a dog, right? And make the dog to sniff what is there in the bag, and if that bag contains explosive material, the security people immediately evacuate the entire railway station or the airport, then open them and distribute the bomb and do all of that. What the security people basically told me was, can you develop something like an electronic nose, an e-dog, right? An electronic kind of a dog, which can smell things, right? And which can tell us if something is present in the bag or not. And they can use the dogs, but finding that simple dog all the time is pretty difficult. They are all living beings, they have their own needs, and it's not easy to get those simple dogs. They are also very expensive to train and maintain. What the security people often require is a simple electronic device, which is like an electronic dog or electronic nose kind. And if you even look at a mobile phone, right? Any mobile phone you look at, what does the mobile phone have? Mobile phones have captured many of the sensors that we have. We can see things, mobile phones also can see things. They have excellent cameras. We can hear things, mobile phones also can hear things. They have excellent speakers, microphones. We can, therefore we can touch things, mobile phones also can touch it and feel. They also have captured that sensor that we have in the humans. What are the two sensors that mobile phones don't have, which we humans have? One is smelling things, right? They cannot smell it. Mobile phones cannot smell things, right? The second thing, they cannot, what is the other thing that a mobile phone cannot do? They cannot taste anything, right? The taste and smell are the two things electronic gadgets still cannot do. Whereas the other three sensors they are able to pick up very well, like we. So our goal was to see whether you can make the mobile phones smell things. For electronic mode kind of platform. Once I can make mobile phone to smell, I can train the mobile phone to smell the explosive and then call the security person, call the security person every time somebody places a bomb in a bus. Some mobile phone will pick it up and then call the security person and then help save it. So that was a kind of technology that we worked. And so we started to use a similar kind of platform. So we worked on it for a very long time. We did a lot of research on that. Right? So one of the ways this is how this electronic nose platform, the exchange looks like, right? The way that it takes in the air and looks for the presence of explosives, and when it finds explosives, it can actually give an alarm. We call it exchange. And another idea we had around that time was, what is the property of an explosive? Property of an explosive is to explode, right? So what we do is we physically collect a few particles, 10 nanograms of particles, few particles from the vapor, right? Or from the spike. If somebody has carried explosive, some particles will be stuck to the body on the hand. If somebody has handled explosive, shook hands with somebody. So these particles get transferred. So you basically take a spike, right? And then when you take a spike, even if there are 2 or 3 particles stuck to the body, you take those particles, you actually cause an explosion. You explode those particles. And if it is an explosive, it has a certain thermal signature. Explosives are exothermic reactions. They will have a certain thermal signature. They burn in a certain way because these are all high energy materials, unlike the normal materials which usually burn. But their burning characteristics are very different from explosives, which are like a very rapid conversion. So they are high energy materials. So what we basically do is we collect those particles from the soil or from the ambient, if somebody is carrying that, and then we explode those few particles, and then when we explode, we look for the thermal signature, right? Based on the thermal signature, we can tell whether something is explosive or non-explosive. So that is how we actually developed this platform. I have a small video which actually shows you how it works. Let me see if I can. Are you seeing the audio? Okay.
Yes, it's okay.
Every luggage out person passing through the security checkpoint is tested by the security officer to check whether they have traces of explosives on their surface, skin, or hair. Nano's network probably claims to be the first explosive trace detector in the world using microsensor technology. The microsensor Nano's network is made using micro-electromechanical system, MEMS technology, in setting the conductor valve. The sensor uses fabrication techniques such as lithography, etching, deposition, spin coating, and finally released to the microsensor. The core technology is protected by patents in the US and Europe. All of our actions leave trace behind, which is then screened by the security personnel. The security has to concentrate on the sampling areas that are likely to be touched by hands. In the case of a bag, this would include handle, buckle, and zipper. Post-sampling, the swine is inserted into the system, where microheater subjects the particles into rapid heating. In case of explosives, this triggers exothermic reactions, which are picked up by the integrated temperature sensor of the microheater, thereby having each compound in its own thermal signature. The algorithms use these signatures to distinguish between explosives and non-explosives. Further analysis of the algorithms help in categorization into the appropriate class of explosives. The follow-on view house network features. It is the first microsensor-based EDD. It detects and identifies explosives in less than 10 seconds. Identifies and categorizes explosives into different classes. Can detect energy quantities of explosives traces. It detects all classes of military, conventional, and homemade explosives. It is portable and affordable. It gives visible and audible alerts with sunlight readable color display. Nano's network, explosives trace detection technology can be deployed at airports, railway stations, malls, metro stations, corporate parks, hotels, and tourist spots. The goal is to intercept and prevent access of explosives trafficking. Nano's network is 100% made in India product.
So this technology we developed, because almost 10 years to develop this, and it was launched in the market. This was on being a Minister of Education in Delhi launched the product, because it was developed in an IIT, and then now it's as you can see, the government of India has funded this project, and we now many airports have it, and 11 airports in the country are currently using this technology to screen passengers, for security applications. So now we are working on this technology to miniaturize it further. We are developing a small, matchbox kind of a thing with the same technology, and then we want to put it in each one is now a production device. So we want to put such devices in buses, right? Trains, multiple such devices in buses and trains, so that nobody can place such bombs in the buses and trains. But how do you power them? They're all electronic devices. They need a battery. We generate power from the vibrations. In the buses and trains, there are always vibrations. We put piezoelectric state, that mechanical energy we convert it to electrical energy, and that electrical energy is what we use to charge the battery. And but what are those materials known as? They are known as piezoelectric. So we did a lot of research on piezoelectric. We wrote a lot of papers on piezo, and you can use such technologies even to network, around Taj Mahal and other places where no security, where people cannot carry such bombs and other such things. So in buses and trains, we generate power from vibrations, and for that we work on technologies, materials which can actually develop a good piezoelectric. This is the work done in chemistry department, this is the work done in physics department, but we as an engineer, I collaborate with them, I use their help to develop these things and integrate it into these sensor nodes. For the past 6 years, I have been working on agriculture applications, and I am now developing sensors for all these micro and macro nutrients like soil health monitoring. With a little bit of soil, with a little bit of soil, it can actually test the soil quality, right? What all it has, what is deficient, so that the farmers can put only what is required in the soil. So we are working on the technology between IIT Delhi, IIT Bombay. We started a major project, and we developed the technology. In fact, last year I started my second company called Soil Sense, and this company has launched this product called MULTIDISCIPLINARY. So this is actually a soil gluconate. It can detect multiple parameters of the soil with the soil solution. It can actually detect nitrates, phosphate, potassium, pH, electrical conductivity in the soil. So this is already available in the market now, and we are staying in village people. So this is how what we do as engineers. So we identify a problem, and then we all work as a team, scientists and engineers coming together, and then we develop solutions, and then we market them to the startups. And so many of these startups are doing very well now. And Nanosynthesis was my first startup, which has the explosive detector, just supplying it to all the airports. And Soil Sense is my second startup, which is serving the needs of farmers in many states, and all these technologies are available. So therefore, when you look at it, every problem is an opportunity. So when you see a problem as an engineer, your goal is to solve that problem. And how do you solve the problem? For that, you need to do research. And much of that research is done by the PhD students. So I have guided 53 PhD students, and all the work that I showed you, a lot of them contributed to that research. So that you generate that knowledge, you understand the problem, you understand how that problem can be solved, and then we put it all together, that research, that knowledge, and then we develop finally a product, and then we start to sell it. Therefore, this is the kind of work that the PhD students do in engineering sort of disciplines, and this is what most of the engineers always want to do, to solve the problem. I will stop here. Thank you.
Thank you, Professor Rao. I don't know whether I am visible to you. Am I visible? You can hear me. Okay, fine. So, is there any question you would like to ask on innovation and all? Okay, there is one question, Professor Rao wants.
I can see you now.
Virtuous evening, sir. How can we improve the success rate of research to reach the top of the innovation table?
Not every project you do can be successful, just as not all startups will be successful. The success rate can be 20% or 30%. So 2 out of 10 might succeed, 3 out of 10 might succeed. But you have to keep working at it. Right? You launch a product that did not succeed, people found many problems in that. Then you go back to the lab, you keep improving that. The one product, that explosive detector, which is now being used in the airports, is spent for 10 years to actually work on that. The nanostic, the company which we incubated, they did most of that work. So they raised a lot of money and ultimately it succeeded. But some of the other things they did, some of the other things we did not succeed. That's part of the life. Not everything you do will be successful, but you need to keep doing things and keep learning also. When you fail, you know why you have failed, and then you keep improving that. Now my success rate is pretty high, but when I started, it was not so. The same happens to many companies, even with nanostate. Now they know how to develop products.
Thank you, sir.
Is there any other question? Okay.
सर लाइक आपने कहा कि आपने हार्ट अटैक से बचने के लिए उसके सिम्टम्स को पहले ही डिटेक्ट करने के लिए आपने एक मशीन बनाई थी सो उस समय मतलब उस थोड़ी बायोलॉजी चाहिए होती है सो दैट इज़ नॉट योर डिपार्टमेंट सो उस समय आपको चैलेंजेस महसूस हुए कि ये मेरा डिपार्टमेंट नहीं है फिर हम कैसे रिसर्च कंटिन्यू रखें
प्रोजेक्ट्स बताए उसमें ऑलमोस्ट 7 डिपार्टमेंट्स इन्वॉल्व है बायोलॉजी से बहुत सारा फैकल्टी मेंबर्स इन्वॉल्व थे हमने एक ग्रुप बनाए तो ग्रुप में देयर आर पीपल फ्रॉम बायोलॉजी पीपल फ्रॉम फिजिक्स पीपल फ्रॉम केमिस्ट्री पीपल फ्रॉम इलेक्ट्रिकल इंजीनियरिंग ऑफ कोर्स आई वाज देयर पीपल फ्रॉम मैकेनिकल इंजीनियरिंग so there are all these disciplines which we formed a group and then we worked on one single problem we knew what we wanted to do and then we all contributed to each one of them contributed to the blood to plasma separation one of them contributed to developing microfluidic solution one of them contributed to understanding the antibodies and their coding one of them contributed to reading the electronics the signal delta R the electrical parameter signal product development is always a multidisciplinary activity. No single engineering discipline, no single science discipline can do everything. So therefore, learning to work as a team is very important. And the two things which are important in all of this is asking the right questions. Right? If you don't ask questions, there is nothing left. So then you accept the way things are, then nothing will ever improve. So therefore, asking the right questions, why I cannot solve this problem. Why, what kind of solution I need to develop. So asking the right questions and then working as a team, developing a solution is how it is. So I don't understand much of biology or much of any other discipline. I am electrical engineer. So my part as a team leader was to put all of that together and also contribute my part.
Sir, and how did you get funding and people for your research?
So this is all funded by various government agencies. Many of them were funded by DRDO, by the Department of Science and Technology, and Ministry of Electronics and Information Technology. And then the private investors. We raise a lot of money from private investors too. Once you have a product, then you take money from the private investors. Because private people don't fund something at a very early stage. So they want to get the returns for their investment. And once you start a company, they take equity. They take 10% of your company, right? And then for the 10% they give you some amount of money based on the valuation of your company. If your company they believe is worth, let us say 100 crores, then they will give you 10 crores for 10% of the company. So you negotiate with them, and then so once you start a company, then you have a lot of investors who will come and fund you for the equity that they take.
Thank you, sir.
Good morning, sir. So, if you have created a device to detect the heart attack, future heart attacks, why the rates of heart attack is not decreasing in India? Still there are many heart attacks in India. The rate is still high. So
there are so many detectors for explosive, but still so many people are dying because of terrorist attacks. So that's how it is. I mean, once the solutions are all there, it is a large country. What you can save are people in bigger cities and towns, where you are close to a hospital and all that. But in many places, people actually don't go to get any test done. Many people often are carried to the hospital after they have a heart attack. But before a heart attack, not many really even go for the test. So the preventive care, that health checkups at regular intervals are all very important. And if somebody has a history of any heart-related thing, they should go to the hospital and actually get this test done at regular intervals. Often, the people think, nothing will happen to me. That is when all the wrong things.
So there are various reasons for the heart attacks, like the blockage of arteries. So these devices can found these arteries blocked or like anything.
It has nothing to do with the blocking. Heart attack can be any reason. But what we detect is once the blood circulation is restricted, then the heart muscles start to die. And when they die, they release certain proteins into the blood. So what we are detecting is what the heart muscles release, when they are beginning to die. That is what doctors call the myocardial infarction. So we are actually diagnosing the myocardial infarction. So that is when these proteins get released. Some proteins get released very early. Some proteins get released very close to a heart attack. Therefore, by monitoring different markers, you can actually predict a heart attack early.
I think we will stop here. This last question was very important, that even though things are known why people are dying. So I must tell you one thing. In India, many people don't even show their teeth till toothache comes. The more you become knowledgeable, you should know that every year you should take whole body test. Many people don't do any tests, right? And these are very specialized tests. People don't even do common tests in our country, right? Many people cannot afford it. Many people, and these are very specialized tests. So what you said is, so many things are known. Yes, many things are known, but people in India are dying of very simple infection. That is because people don't even have the amount of money to do simple tests, like blood test. Every year, you should do whole body examination. Lungs, kidney, liver. How many people do it? Very few people do it. Unless you have a toothache, you don't go to the dentist. But in USA, every child has to go to the dentist every day. The school will make you go to the dentist. And you have to have a dental examination, even at 4 years, 5 years, 6 years. Because what is happening in your tooth, you will come to know at 18, suddenly one tooth has been, but it doesn't happen in one day. So point is, you have to take care of your body, not when something happens. From childhood, you should make a point to take an annual test. We do at a late age nowadays, many of us do once we are 45, 50. We take what is called an executive medical checkup. That means they do everything, whole body checkup. Still, there are many tests they will not do because they are expensive tests. Like he's talking of markers and all. They are expensive. You have to grow antibodies. So you have to pay money to do those tests. So specialized tests means you have to pay special money. In India, many things are available. You go to private Apollo hospital in Delhi or in Hyderabad. You can do all kinds of tests. How many people do those tests? Very few. Basic tests may be within 500,000 rupees, 2,000 rupees. But there are lots of expensive tests because you have to develop markers for them. The developing markers is done in laboratories. So those companies who develop them will take a lot of money. I think, Professor Rao, I am right what I am saying, that many things happen even though the technology is known. But how many people have access to that technology? Because it costs money. You have to pay money for that. Okay? So anyway, I think with that very good talk by Professor Rao, we come to the conclusion of this talk. You learned basically how from science to engineering to device and to commercialization. It is a long road ahead. And there are a lot of different players at different segments. And that is what the talk was all about. Thank you, Professor Rao. You have a small memento. I will take that memento for you and I will deliver it IIT Delhi at your residence. Okay? So we have a Kunark Chakra from here, from Odisha. So thank you very much. Thank you for joining. We know you are very busy, but thank you for joining. I'll see you sometime in Pilani or Delhi. Okay. Bye-bye. Bye-bye. So we are now closing. Thank you for being with us. It is unusual that we have till 6:30, but all of you, really I'm telling you, you will not hear this kind of talk so easily in many places in our country. So the large number of people who have come to Berhampur personally, so it's a great asset, and Professor Rao joined online. He's so busy. So anyway, thank you all of us, and we'll meet tomorrow morning. Thank you. 9 a.m. 9 a.m. tomorrow.